Hey there, and welcome to our exciting course on building AI agents using reinforcement learning. Throughout this course, you'll dive into the fascinating world of AI, where you'll develop practical skills in coding, particularly in Python. You're going to learn how to create intelligent agents that can navigate dynamic environments. So, get ready for some hands-on coding exercises. And don't forget to check out the GitHub repository linked in the description. There, you'll find all the code you'll need. Stick around until the end for a final project that will test everything you've learned, which you can also find in the repo. So, are you ready? Let's get started. To represent text in artificial intelligence, we need to tackle some unique challenges that text presents compared to other data forms like images or structured tables. You see, unlike those concrete visual elements, language is, abstract, variable, and highly context-sensitive. There's just no direct correlation between the meaning of a word and its written representation, which makes it quite the puzzle for computers to decode. So, how do we effectively navigate this complexity? Well, let's unpack it together. First off, we must consider the nuances of human language, with all its idioms and expressions that can change meaning based on context. Imagine trying to teach a computer about humor. It's like asking it to solve a riddle. Additionally, we have to think about how language varies across different cultures and regions. So, as we dig deeper into this topic, we'll explore how to represent text in a way that allows AI to understand and interact with it more like a human would. All right, let's dive deeper, shall we? Now, let's implement the following code to generate word embeddings using the Word2Vec model from the GenSim library. First up, we need to import the required modules, specifically Word2Vec and NLTK. Now, NLTK is fantastic for natural language processing tasks, so let's make sure we've got the Punkt tokenizer downloaded and ready to go. This tokenizer is key because it helps us break down our sentences into manageable tokens, which is a crucial step before we train our model. Next, we'll define a list of sentences. That's where the fun begins, making sure each one is tokenized into words using nltk.wordTokenize. This creates a structured format that our Word2Vec model can work with smoothly. Now, moving ahead, we're going to train the Word2Vec model. Just pass those tokenized sentences to it, and don't forget to specify some important parameters. For instance, there's vector size, which decides the dimensionality of the embeddings, and then we've got window, which defines the maximum distance between the current and predicted word within a sentence. Once that's done, we save our model to a file for future use. Finally, let's demonstrate how to access the vector representation for a specific word. How about artificial? This will illustrate just how we can leverage our embeddings for various NLP applications, showcasing the power behind it all. Now, let's implement the following code to load glove embeddings for our NLP projects. The first step is to define a function called loadGloveModel, which takes a file path as an argument. Inside this function, we initiate an empty dictionary, GloveModel, where we'll store our word embeddings. Next, we open the specified Glove file in read mode. With each line in the file, we split it into separate components, where the first element is the word and the remaining elements represent the corresponding vector values. We then convert these vector values into a NumPy array for efficient numerical operations. Each word and its vector gets stored in our GloveModel dictionary for quick access. After defining our function, we can call it with the file path of a Glove dataset, like glove.6b.50d.txt. This will populate the GloveModel dictionary with embeddings that we can use throughout our NLP tasks. Finally, we can effortlessly access specific word embeddings by referencing the dictionary, allowing for efficient retrieval of vector representations needed for various applications. Now, what's interesting here is the clear ascending pattern that shows a progression from the sparse, high-dimensional, and semantically naive representations, think of one-hot encoding, toward increasingly informative and dense vector representations like Word2Vec. So, what can we conclude from this? Well, one-hot encoding, while the simplest, offers the lowest representational complexity and, unfortunately, lacks any semantic relationships. Now, when we move to the bag of words method, it adds some frequency information, but it still discards the order of words. Then we have TF-IDF, which increases representational nuance by weighing words according to their importance in the entire corpus, helping us to distinguish those truly informative tokens. And finally, Word2Vec takes the cake, representing the highest complexity shown here, providing dense, learned embeddings that really capture those semantic similarities and contextual relationships between words. This ordering highlights an important trade-off between simplicity and representational power. You see, simpler methods can be computationally cheaper and sufficient for smaller or more constrained tasks. But for tasks that require a deeper understanding of meaning and relationships, more complex embeddings like Word2Vec deliver a richer semantic structure, which ultimately motivates the move to even more advanced contextualized models. Now, let's see how we can implement BERT for contextualized embeddings. First, we're going to import the necessary classes from the Transformers library, which gives us access to pre-trained models like BERT that are super easy to use. Next, we'll load the BERT tokenizer and model specified as BERT base uncased. The tokenizer, well, it processes our input text by converting it into tokens that the model can understand, ensuring that our text is in the right format for BERT. Now let's tokenize the input text, which describes how AI is reshaping industries. By using this tokenizer, we prepare our data for the model, returning it as tensors suitable for PyTorch. Once our input is ready, we proceed to get the embeddings. Here, we use the model to process our tokens without tracking gradients, which is great for efficiency when we're just after outputs. After running the BERT model, we'll obtain the last hidden states, which are the contextualized embeddings for each token. These last hidden states are crucial as they encapsulate rich semantic information that reflects the surrounding context of each word. This nuance is invaluable for tasks like sentiment analysis and conversation modeling. Finally, we'll print these embeddings to visualize the contextual representations that BERT so wonderfully provides. Now, let's implement a text pre-processing function that will clean and prepare our text for analysis by an NLP model. The process starts by importing the necessary libraries. We need RE for regular expressions, and then there's NLTK's stop words and WordNet lematizer for filtering and normalizing words. Oh, and don't forget, we also need to download those required stop words and WordNet resources for lemmatization. Next up, the pre-processed text function begins by converting the input text to lowercase to maintain uniformity. This is crucial, you know? Following that, we use a regular expression to whisk away any punctuation or numbers, ensuring we're focusing solely on alphabetic characters and spaces. Once we've cleaned that up, we split the cleaned text into individual tokens, allowing us to work with each word separately. In the next step, we filter out common stop words. Those are the words that often carry little significance for our analysis, using NLTK's built-in stop words list. Finally, we apply lemmatization, which reduces each word to its base form, enhancing the model's ability to generalize. The function then returns a cleaned string, which, trust me, significantly improves the readability and quality of text input for further NLP tasks. For example, this function will process the sentence, "Natural language processing is vital for AI advancements to yield a more meaningful representation for analysis." Now, let's see how we can implement TSNE for visualizing word embeddings. First, we're going to import the necessary libraries. So we'll bring in TSNE from sklearn.manifold for the dimensionality reduction, and don't forget matplot.pyplot for creating those visual plots that help us see things clearly. Now, let's prepare our dataset by extracting the words and their corresponding embeddings from the Glove model, which we've already loaded. Got that? Great! Next, we'll fit and transform our high-dimensional word embeddings into 2 dimensions using the TSNE algorithm. Now, we specifically set the number of components to 2 here because this allows us to visualize our data in, you guessed it, a 2-dimensional space. And just a heads up, parameters like perplexity and n-iter can really influence the quality of our visualization. They'll help balance our view between local details and global structure in the data. After we've reduced that dimensionality, we're ready to create a scatter plot. Think of it as a map where each point represents a word vector in our 2D plane. The plot's dimensions are based on the distances between those word vectors, so nearby points indicate words that are semantically similar. To make our plot readable, we'll annotate each point with its corresponding word. This gives us a clear picture of the semantic relationships within our embedding space. Finally, we display the plot using plt.show, and there you have it. You'll gain valuable insights into how words relate to one another in a visual format. As we reach the end, it's essential to understand the growing importance of continuous research and development in the representation of text for artificial intelligence. The evolution of models and techniques signifies not just an improvement in technological capabilities, but a broader understanding of human language's nuances and complexities. Each advancement allows AI to deliver better results. Whether that's in understanding textual sentiment, generating coherent responses in conversation, or translating languages with a higher level of accuracy. We live in an exciting time. As practitioners and learners of AI, we have the opportunity to harness this power and make meaningful advancements in the field. So, as you continue your journey with NLP, remember that every word carries weight. Every phrase has context, and every sentence tells a story. The way we represent these can unlock various applications that improve and innovate our interactions with technology. Keep exploring, learning, and applying these concepts. Understanding word embeddings is a crucial piece of the puzzle in natural language processing, especially within artificial intelligence. These vectors, they really capture the meanings of words in a way that helps machines grasp the context in which those words are used, making them absolutely indispensable for tasks like sentiment analysis, translation, and text classification. Now, up to this point, we've touched on the unique challenges of representing text in AI, emphasizing the abstract nature of language itself. We've also explored some techniques for translating text into numerical embeddings, things like Word2Vec, Glove, and those contextualized embeddings from models like BERT, which really underscore the necessity of considering word context. Don't forget, we also talked about the critical role of text pre-processing in optimizing the performance of our NLP models. This includes clever visualizations that help us understand word relationships within embedding spaces. Just think, continuous research and advancements in text representation are going to keep enhancing AI applications across a variety of linguistic tasks. So, let's dive deeper into word embeddings and their applications. We're going to explore how they offer a more distributed representation of word meanings, setting them apart from traditional sparse representations. It's quite fascinating, isn't it? Now, let's dive into how we can implement the Word2Vec model to create word embeddings using the GenSim library in Python. First, we start by importing the necessary modules from GenSim, and don't forget to download the NLTK tokenizer. It's essential for breaking down our text into individual words. After that, we'll define a list of sample sentences that highlight concepts relevant to artificial intelligence and natural language processing. Next up, we proceed to tokenize these sentences. This means we're converting each sentence into lowercase and splitting it into individual words, which results in a structured format that the Word2Vec model can easily process. Now, let's implement the Word2Vec model training by providing the tokenized sentences. The parameters we set for the model, like vector size and window size, really influence how the word embeddings are created, capturing those contextual relationships between words. Once the model is trained, we can explore the resulting word embeddings. By querying the model with specific words, we get to see the vector representations for terms like artificial and language. This allows us to understand just how these words are encoded in high-dimensional space. This practical implementation really exemplifies how word embeddings facilitate a deeper understanding of language in AI applications. The bar chart titled Effectiveness of Different Word Embedding Techniques displays effectiveness ratings on a scale from 0 to 100 for 4 popular methods. Word2Vec scores 80, Glove sits at 75, BERT leads the pack at 90, and TF-IDF comes in last with a score of 70. Now, let's break down what we see here. First off, BERT's impressive rating of 90 suggests it has a significant advantage, particularly because of its contextualized, transformer-based approach. Meanwhile, the static methods like Word2Vec and Glove are surprisingly close, with Word2Vec edging out Glove by just 5 points, scoring 80 compared to Glove's 75. And then we have TF-IDF, bringing up the rear at 70. This really drives home the limitations of traditional, sparse bag-of-words models when stacked up against the denser embeddings. From these insights, we can draw some practical conclusions about choosing the right model. If you're dealing with tasks where understanding the context is key, BERT-like embeddings are certainly the way to go. On the other hand, if you're short on computational resources or facing latency issues, both Word2Vec and Glove are solid alternatives. And while TF-IDF might just cut it for simpler tasks, it generally underperforms when it comes to capturing semantic meaning. Finally, the chart's detailed axis labels and numeric annotations on each bar make it super easy to see the relative performance gaps. So, as you analyze these methods, keep these points in mind for your modeling journey. Now, let's dive into how we can load Glove embeddings using Python, shall we? We've got this handy function called load Glove model, which takes the file path to your Glove text file as an argument. First off, it initializes an empty dictionary to hold the embeddings. As the function reads through the file line by line, it splits each line into the respective word and its vector representation. So this is pretty clever. It takes that first element as the word and then transforms the remaining space-separated strings into a NumPy array of floats. By doing this, we're effectively storing each word alongside its vector in the dictionary, creating a neat little structure that allows for quick access to those embeddings. All right, once we've defined our function, we move on to loading the Glove model by supplying the specific file name for the Glove embeddings. Now, it's super important to make sure that this file is accessible in your working environment. After we load the embeddings into our dictionary, retrieving the embedding for any word, say technology, is as easy as referencing the corresponding key in our dictionary. This method really showcases how Glove beautifully blends both statistical relationships and contextual information to enhance word representation in natural language processing tasks. Now, let's see how we can implement BERT using the Hugging Face Transformers library, which really makes working with pre-trained models for natural language processing tasks a breeze. First up, we start by importing the necessary classes, so that's BERT Tokenizer and BERT Model, and we'll also bring in the Torch library for those tensor manipulations. Now, the next step is to load our pre-trained BERT model along with its tokenizer. We do this using the FromPretrained method, and we're specifically going to specify the model name as BERT-base-uncased. This way, we're tapping into a robust, widely used version of BERT that's perfectly capable of generating those all-important contextualized embeddings. After that, we'll set up our input text, which is basically a sentence where we want to dig into the contextual meaning of the words. We can then proceed to tokenize this input using our tokenizer, converting our sentence into a format that BERT can make sense of, and ensuring it's returned as a tensor. To grab those embeddings, we're going to run the model within a context manager that disables gradient computations for a little boost in efficiency. The model will then output a structure from which we extract the last hidden states, which represent those contextual embeddings for each token in our input sentence. And it's really fascinating how these embeddings dynamically adjust based on context, reflecting how BERT captures those rich semantic relationships in language. Now, let's implement a pre-processing function to ensure our text data is clean and suitable for embedding models. The first step is to import the necessary libraries. This includes R for regular expressions, as well as NLT case tools for handling stop words and lemmatization. So make sure you download the required NLTK data first. After that, we define our function pre-process text. This function starts by converting the input text to lowercase to maintain uniformity. Next, we use a regex operation to remove any punctuation and numbers, which means we're focusing solely on alphabetical characters and spaces. This is super important because it helps eliminate some noise that might mess with our model training. After that, we split the clean text into tokens, which are essentially individual words. Now, to further refine these tokens, we filter out any that are identified as stop words. These are common words like and or the that don't add much meaning. Then, we employ the WordNet lemmatizer to convert words into their base forms, which really helps standardize the linguistic variations we encounter. Finally, we join the tokens back into a single string. This clean text is essential for ensuring higher accuracy when we're feeding data into our embedding model, allowing us to achieve improved performance in later NLP tasks. Now, let's implement the following code to visualize word embeddings using TSNE. First, we need to prepare our words and their corresponding embeddings by extracting them from the Glove model, okay? So, we're going to store the words in a list and convert the embeddings into a NumPy array for efficient processing. This setup is really vital as it organizes our data for the upcoming dimension reduction technique. Next up, we'll apply TSNE, and we'll specify the parameters like n_components = 2 for our two-dimensional visualization. We'll also include a perplexity value and the number of iterations to ensure that we achieve effective convergence. This key step reduces those complex high-dimensional embeddings into a lower dimensional space, which allows us to represent the relationships between words more intuitively. After we get those reduced embeddings, we'll move on to creating a scatter plot using Matplotlib. Let's define the figure size for better clarity and plot those reduced embeddings. Each point on the plot will represent a word positioned according to how similar its embedding is to others. Finally, we'll annotate these points with the respective word labels, making it super easy to identify terms and visualize their relationships in this two-dimensional context. This whole process enhances our understanding of the semantic similarities between words in our embedding space, and it's a really exciting step in your data exploration journey. In conclusion, word embeddings are a cornerstone for more advanced applications in natural language processing. Their ability to encapsulate semantic meaning in a distributed manner has truly transformed how machines understand language. From Word2Vec and Glove to BERT, each type of embedding offers unique qualities and capabilities that adapt well to various NLP tasks. Continuous research is enhancing these techniques, paving the way for even more intelligent AI systems. Now, as we delve deeper into the world of word embeddings, it's vital to remember they're not merely a technical necessity. They're like a bridge connecting our communication with machines. This bridge provides a richer understanding of human language, which can significantly enhance how we interact with and utilize technology. So, I encourage you to explore, experiment, and really let the power of word embeddings elevate your AI projects to new heights. Word2Vec is an incredibly powerful tool in the field of natural language processing, designed to convert words into continuous vector representations based on their context within a sentence. In this lesson, we're going to dive into the underlying principles of Word2Vec, how it works, and how you can implement it in real-world applications. So far, we've covered the foundational concepts of word embeddings and touched on various techniques like Glove and BERT, which emphasize just how critical it is to capture relational semantics in language. Now, let's dig deeper into the mechanics of Word2Vec, understanding how it predicts words based on their context. So, imagine this. Word2Vec uses a very clever approach, predicting a word based on the words that surround it. And in doing so, it learns to understand the relationships between words in an incredibly intuitive way. It employs two main models, the continuous bag of words and the skipgram model. The former predicts target words from context words, while the latter does the reverse. It's all about those word associations. Just think about how much this impacts applications like chatbots or search engines, where understanding context is key. So, the next time you're chatting with a bot, just remember, there's a lot happening behind the scenes, with Word2Vec making those conversations feel more human. To understand Word2Vec, let's first grasp the intuition behind it. Imagine you have a set of sentences where context plays a crucial role in determining meaning. Word2Vec operates on this fascinating principle that words appearing in similar contexts will carry similar meanings. This idea is rooted in something called the distributional hypothesis. For instance, think about the words king and queen. They often pop up in similar contexts, right? So, their vector representations, which are just their numerical forms in a mathematical space, will also be located close to one another in what's known as the embedding space. In essence, Word2Vec transforms words into numerical data, which makes it much easier for algorithms to analyze and make predictions. Pretty cool, huh? Now, let's implement the first step by installing the GenSim library. This is essential for working with Word2Vec. You can easily do this via the command line using pip. Just type pip install GenSim and hit enter. After the installation, we'll import the necessary modules to begin our implementation. This includes GenSim as well as the Word2Vec model for creating those amazing word embeddings. Oh, and don't forget to import NumPy for all those numerical operations we might need later. Next, we will define our dataset. Here, we're using a simple list of sentences, and each sentence is represented as a list of words. This structure is super important because the Word2Vec model expects input in this format to truly understand the context in which those words are used. By preparing this dataset, we really set the stage for training our Word2Vec model, which will analyze all the relationships between those words based on their co-occurrences in these sentences. This foundational setup allows us to effectively build semantic representations of words using the skipgram architecture, which is just like a fantastic approach. So let's dive in and see how it all comes together. Next, let's dive into initializing and training our Word2Vec model using the skipgram approach. To kick things off, we'll create an instance of the Word2Vec class from the Gensum library. And check this out, we'll pass in our pre-processed sentences as the input data. Now, we need to specify a few parameters that influence how our model trains. First up, the vector size is set to 10. This defines the dimensionality of our word vectors, right? Higher dimensions can capture more nuances, but remember, they also need more data to train effectively. Next, we set the window size to 2, which means for each target word, the model will look at 2 words on either side to truly understand the context. By setting min count to 1, we're ensuring every word in our dataset gets included during training, no matter how often it appears. Now, when we choose SG equals 1, we're enabling the skipgram model, which focuses on predicting context words based on our target word. Finally, we'll set the number of epochs to 100. This tells our model how many times it should iterate over the training dataset. More iterations can lead to more accurate word embeddings, which is exactly what we want. Now that our model is trained, we can access the word embeddings by querying the model with a specific word. For instance, let's retrieve the vector representation of the word cat and print it out. This will let us observe how the model expresses this word in numerical form, capturing its contextual relationships within our dataset. Now, let's dive into how we can implement the functionality to find similar words using our trained Word2Vec model. So, here's the gist. We're going to leverage the most similar method from the Gensum library. This nifty little tool allows us to query the model for the words that are closest in meaning to a specific target word. In our case, that word is cat. By passing cat as the first argument and setting top n equals 3, we instruct the model to return the 3 words that most closely relate to cat based on their vector representations in the embedding space. Now this operation relies on cosine similarity. Basically, it's a mathematical measure that evaluates the angle between 2 vectors. Smaller angles indicate a higher degree of similarity. So, the results from this query are stored in the similar words variable, which will then print out to display our output. This technique really showcases the power of Word2Vec in uncovering semantic relationships, and it also validates all our earlier work in creating meaningful word embeddings. By applying this implementation, we can gain valuable insights into how words like cat relate to others within the given context, enriching our understanding of language representation in computational models. Now, let's implement the function to visualize our word embeddings. We begin by defining the visualize words function, which takes our trained Word2Vec model as an argument. Inside the function, we create 2 lists, one for the labels of the words and another for their corresponding embeddings. We iterate through the words in the model's vocabulary, populating these lists with both the words and their vector representations from the model. Next, we employ the TSNE technique to reduce the dimensionality of the word vectors from a high-dimensional space down to 2D. This reduction is crucial for visualization as it translates those complex relationships into a simpler format that we can plot. We create a scatter plot using matplotlib, where each point represents a word's vector position in this 2D space. To enhance interpretability, we annotate each point with its respective word. This helps us see how closely related words cluster together semantically. When we call the Visualize Words model function, it generates a graphical representation of the word embeddings, providing us insight into the model's understanding of word relationships based on context. And let me tell you, this visualization is a powerful tool for interpreting our embeddings and assessing the performance of the Word2Vec model. The accompanying scatter plot, titled Word2Vec Word Similarity Scores, displays individual words along the x-axis, while their computed similarity scores are plotted on the y-axis. Each point is thoughtfully labeled with a qualitative category, making key patterns immediately visible. For instance, we see Apple sitting spectacularly at the top with the highest similarity score of 0.95, labeled as highly similar. Right behind it, we have King at 0.9 and Queen at 0.85, both tagged as most similar. This indicates that there's a strong semantic relationship among those terms. Now, if we look at cat at a score of 0.7 and dog at 0.6, they're positioned roughly in the middle, sporting the label moderately similar. This suggests a moderate semantic closeness, a bit expected since both are animals you'd often find in similar contexts. On the lower end of our spectrum, we find car at 0.4 and bike at 0.5, both labeled as less similar, showing that these transportation-related words don't quite align in similarity with our fruit and royalty pairs. So, what can we conclude from all these values and labels? Well, Word2Vec tends to assign higher similarity scores to words that share strong semantic pairs, like apple and orange, or king and queen. It gives moderate scores to words that are related but distinct, like cat and dog, while lower scores are assigned to words that show less contextual overlap, such as car and bike. The numeric range we see, from 0.4 to 0.95, really showcases the model's dynamic ability to rank word relatedness. And those annotated categories, high, most, moderate, and less, are incredibly useful for validating or calibrating applications further down the line, like synonym selection, analogy resolution, or candidate ranking in retrieval tasks. Now, let's implement a simple pre-processing step using the NLTK library for text tokenization. We'll start by importing the necessary modules from NLT. The first thing we need to do is download the tokenizer model, which is essential for breaking down sentences into individual words or tokens. For our example, we'll use the sentence, "The quick brown fox jumps over the lazy dog," and we're going to tokenize that for analysis. Next, we'll lowercase the input text to ensure consistency in our word embeddings. This makes it so much easier to compare words without worrying about case sensitivity. Then, we'll apply the word tokenize function to split the lowercase text into its constituent tokens. This process not only simplifies our data, but also enhances the quality of the embeddings generated by the Word2Vec model by removing irregularities in the input. Next, let's print out the tokenized words so we can visualize the result of our pre-processing step. This foundational procedure is really critical for improving the model's performance, as high-quality, clean data leads to more accurate and meaningful word embeddings. Beyond pre-processing, let's dive into some key parameters like vector size, window size, and the number of training epochs. Finding the optimal values for these can really make a difference in how well your model performs. It's crucial to run multiple experiments and evaluate the quality of your embeddings during this phase. Now, in real-world applications, you'll often be dealing with much larger datasets, and you might want to integrate Word2Vec into a more extensive pipeline. This could mean building custom data loaders, leveraging GPU for quicker training times, and exploring other architectures like Glove or FastText. They were tailored for certain challenges that Word2Vec doesn't handle as well. As we wrap up this discussion, it's essential to acknowledge that while Word2Vec has impressive strengths, it also has its limitations. For example, Word2Vec looks at words in isolation and doesn't really take into account the nuances of phrases or sentence structure. However, the insights gleaned from Word2Vec laid the groundwork for even more sophisticated models like the Transformers architecture, which tackle these limitations by considering the full context in which words appear. In summary, Word2Vec is a transformative approach within the field of natural language processing, enabling us to encode words as vectors based on their contextual relationships. We began by covering the intuition behind Word2Vec and its architectures. Moving forward, we demonstrated how to implement and visualize embeddings, while emphasizing the importance of pre-processing and parameter selection in model training. With this foundation, you are now well equipped to explore further into the realm of word embeddings and their integral roles in advancing AI and natural language understanding. So, next week we're going to look at advanced models that have built on the Word2Vec framework, such as BERT and GPT, to see how these innovations are shaping the future of AI interactions. Understanding and optimizing word embeddings is crucial for enhancing the performance of natural language processing models. One of the popular tools in this domain is Word2Vec. It simplifies the creation of word embeddings, all while ensuring efficiency and accuracy. In this tutorial, we're going to dive deep into the intricacies of Word2Vec and see how it elegantly transforms the complex task of determining contextual relationships into a straightforward binary classification problem. So, if you're ready, let's unpack this fascinating process together. So far, we've learned about Word2Vec, a powerful tool that transforms words into vector representations based on their contexts, highlighting the distributional hypothesis that similar contexts yield similar meanings. We've discussed the two main architectures, continuous bag of words and skipgram, focusing on how to implement the skipgram model using the Gensim library. We also dove into the significance of pre-processing text data and the importance of parameter experimentation to enhance the model's performance. Finally, we touched upon the limitations of Word2Vec and explored how it laid the groundwork for more advanced models like BERT and GPT. Now, let's shift gears and talk about how to optimize these embeddings for real-world applications. At the heart of Word2Vec is this fascinating concept of predicting context words based on a target word, or vice versa. But we can actually optimize this in a couple of key ways. One method is transforming the prediction task into a binary classification task. It's pretty straightforward. You would essentially ask the question, is this contextual word necessary for this target word, instead of trying to predict the whole context of a word. This approach allows us to focus our efforts more effectively and can improve the overall efficiency of our model. Now, let's implement the following code to create our logistic regression model for predicting the relevance of context words based on their embeddings. We begin by importing the logistic regression class from sklearn.linearModel and also bringing in NumPy to help us handle our numerical data. Next, we're going to define a dictionary to simulate word embeddings for a few sample words. Each word will be associated with a NumPy array that represents its vector representation. In this example, we have embeddings for king, queen, man, and woman. Now, let's specify king as our target word and prepare our training data. We'll initialize two lists, X for the features, which will hold the embeddings of our context words, and Y for the labels, where we'll indicate whether each context word is relevant or not. We'll iterate over a predefined list of context words, appending their embeddings to X and labeling them with 1 for relevant words, like queen and man, and 0 for irrelevant words, like cat. After we've prepared our dataset, we fit our logistic regression model using the fit method. And lastly, we can predict the relevance of a new context words embedding, showcasing how our trained model classifies relationships based on these embeddings. The results will provide us with insights into how effectively our model captures the context of the target word. Now, let's implement a function that generates negative samples to enhance our Word2Vec model efficiency. This function, which we'll call generateNegativeSamples, takes two inputs, a target word and the number of negative samples you'd like to create. To simulate this, we'll define a dummy vocabulary filled with various words. The function starts by initializing an empty list. This will hold our negative samples. Now, here's where it gets interesting. We use a loop to randomly select words from our vocabulary. But we have to be careful. Inside the loop, we check to ensure that the word we've chosen isn't the same as our target word. We want to avoid including the target itself as a negative sample. Once we have a valid word, we simply add it to our list of negative samples. Now, after we define the function, we can actually call it to generate negative samples for the word king. This will help our model to better distinguish between relevant and irrelevant words during training, as it provides a balanced subset of context words. Finally, when we print the results, we'll see the randomly selected negative samples for king, which really helps illustrate how negative sampling works in the context of training the Word2Vec model. This process is crucial for making efficient updates during training, since it narrows the focus to a subset of words rather than the entire vocabulary. The bar chart titled Optimizing Word Embeddings, Relevance Scores of Context Words displays 8 context words along the x-axis. Those are king, queen, man, woman, cat, dog, apple, and orange, with their corresponding relevance scores shown on the y-axis, which ranges from 0 to 1. Now, if we look closely, the highest relevance scores, highlighted here, are for queen at 0.85 and king at 0.8, both marked as relevant. Then we see words that fall into a middle zone. Those are woman at 0.75, dog at 0.65, and man at 0.6. These are noted as moderately relevant, indicating a clear middle band of semantic closeness. Lower down the scale, we have orange at 0.5, cat at 0.40, and apple at 0.30, each one labeled as not relevant. The vertical arrangement of these scores really makes the separations explicit. There's a distinct gap between those top 2 relevant words and the next group, plus another clear divide from the moderately relevant words to those less useful. So, from this distribution, we can draw some helpful conclusions about which words should be treated as strong positives. Those are queen and king, while woman, dog, and man are potential positives that might need a bit more context for accurate usage. And then we have reliable negatives for sampling purposes, which are apple, cat, and orange. Understanding these categories is really important because they help inform how we select positive and negative examples, especially when we apply binary classification and negative sampling strategies, as outlined earlier. Now, let's dive into implementing PCA with our Word2Vec embeddings to help reduce their dimensionality for visualization purposes. First off, we'll start by importing the necessary libraries. We need PCA from sklearn.decomposition for doing that dimensionality reduction, and matplotlib to plot our results. Once we have our libraries in place, we'll create a list of labels that represent our words and convert the corresponding embeddings into a NumPy array. This is all setting the stage for applying PCA effectively. Next, we fit the PCA model to our word embeddings, where we specify n components equals 2. This allows us to reduce our data down to 2 dimensions. Why is this important? Well, it lets us visualize those high-dimensional embeddings in a 2D space, crucial for interpreting and understanding the semantic relationships among the words. Following the PCA transformation, we kick off a plotting figure and scatter the PCA results. This really helps us visualize how the word's embeddings relate to each other. As we iterate through our labels, we annotate each point on the scatter plot with its corresponding word, giving us clarity on which word each point represents. To wrap things up nicely, we add titles and axis labels to our plot, which enhances our visual understanding of how words cluster together within this reduced dimensional space. This shows us how well our embedding model is performing. Now, it's important to continually evaluate the performance of these embeddings based on specific tasks, as different applications may demand different optimizations. For instance, if you're diving into sentiment analysis, you might prioritize embeddings that really capture those emotional nuances in the text. On the other hand, when we focus on information retrieval or search, optimizing embeddings for relevance against a keyword becomes more critical. So, in conclusion, optimizing word embeddings through methods like binary classification, negative sampling, and dimensionality reduction significantly enhances their effectiveness in natural language processing tasks. We've explored how Word2Vec simplifies context prediction, allowing models to focus on what truly matters. Understanding these optimizations truly paves the way for tackling more complex NLP challenges while still relying on those solid foundational techniques. The tools and techniques we're discussing today can really bolster your understanding of word representations. Thank you for joining me on this journey into optimizing word embeddings. Remember, the world of AI is vast, and with each step, we're inching closer to building smarter systems that interact seamlessly with human language. In our next video, we'll shift gears and explore the latest advancements in models like BERT and GPT, and how these are leading the frontier of AI and language understanding. Stay tuned.
Text representation is a critical aspect of preparing data for deep learning models, particularly in natural language processing, NLP. Raw text in its natural form cannot be directly fed into these models, which rely on numerical data for computation. In this session, we will explore various techniques that transform text into numerical representations suitable for machine learning models. So far, we learned about optimizing word embeddings and techniques like Word2Vec, focusing on architectures that improve model performance. Now, we will cover text representation techniques, diving deeper into methods such as bag of words, TF-IDF, and advanced embeddings like BERT and GPT. Now let's take a look at how we can implement the bag of words model using Python's scikit-learn library. We begin by importing Count Vectorizer, a powerful tool that converts a collection of text documents into a matrix of token counts. Next, we define a list called documents, which holds several phrases related to programming. Each document in this list will serve as a sample text for our analysis. We then initialize the Count Vectorizer, which will automatically create a vocabulary of unique words found in our documents. By using the fit-transform method on our list of documents, we generate a sparse matrix representation where each row corresponds to a document and each column corresponds to a word from the vocabulary. The entries in this matrix indicate the frequency of each word in the respective document. Finally, we utilize getFeatureNamesOut to print out the vocabulary generated by Count Vectorizer. Additionally, we convert our sparse matrix to a dense array format and display the bag of words representation. This transformation allows us to structure the text data into a numerical format that can be easily processed by machine learning models, setting the stage for further analysis and model training. Now let's see how we can implement the TF-IDF technique using Python and the scikit-learn library. First, we import the tfid vectorizer class, which is designed to convert a collection of raw documents into a matrix of TF-IDF features. We initialize an instance of tfid vectorizer, which allows us to transform our text into a format that captures the importance of words in the documents. By calling the fit-transform method on our list of documents, we generate the TF-IDF matrix. Each row in the matrix corresponds to a document, while each column represents a word from the vocabulary we've built. The values in this matrix indicate the TF-IDF score for each word in each document, shedding light on the significance of the words in context. Finally, we can retrieve and print the vocabulary using getFeatureNamesOut, which shows the unique words identified during the fitting process. The TF-IDF representation gives us a compact view of how the words relate to the documents, enhancing our analysis and understanding of the text data we are working with. The displayed horizontal bar chart titled Comparison of Text Representation Techniques in NLP ranks 5 techniques: bag of words, TF-IDF, Word2Vec, BERT, and GPT by an effectiveness score on the x-axis. The chart shows a clear ascending pattern from bag of words score 20 to GPT score 100, with TF-IDF at 30 and Word2Vec at 40, indicating incremental improvements from simple frequency-based methods to shallow embeddings. There is a pronounced jump in effectiveness when moving from Word2Vec 40 to BERT 80, and another gain from BERT to GPT 100, revealing that transformer-based contextual models, BERT and GPT, provide substantially higher effectiveness scores than classical vectorizers and earlier embedding methods. The horizontal layout makes the ranking and relative gaps easy to compare. Traditional methods occupy the lower end, Word2Vec sits in the middle, and transformers dominate the top end. From this visual, we conclude that, according to the presented scores, moving toward context-aware, transformer-based representations yields the largest performance improvements. The numeric differences quantify how much more effective these advanced models are compared to BOW and TF-IDF in this comparison. Now let's see how we can create word embeddings using the GenSim library with Word2Vec. First, we define a list of tokenized sentences, where each sentence is represented as a list of words. This approach helps in creating a simple and effective dataset for training our model. Next, we initialize the Word2Vec model by passing the tokenized sentences along with specific parameters. The vector size parameter determines the dimensions of the word vectors. Here, we set it to 10. The window parameter defines the maximum context window size, meaning it controls how many words before and after the target word are considered for predicting its context. The min count is set to 1, which includes all words that occur at least once, ensuring no valuable data is wasted. After defining the model, we train it with the provided sentences. Once trained, we can easily access the word vector for any specific word, in this case, Python. By retrieving this vector, we can analyze how the model encodes semantic information, thus illustrating the foundational concept behind word embeddings. This method effectively captures relationships between words, making it a powerful tool for various natural language processing applications. Now let's implement the following code to utilize pre-trained BERT embeddings for generating word representations. First, we begin by installing the Transformers library, which provides access to various state-of-the-art NLP models, including BERT. After installation, we import the necessary modules, specifically BERT Tokenizer and BERT Model, and also import Torch for tensor operations. Next, we load the pre-trained BERT model and its corresponding tokenizer. The tokenizer is essential as it handles the input text, converting it into a format that the BERT model can understand. We then define a sample sentence, "I love programming with transformers," which we will use to demonstrate the extraction of embeddings. Using the tokenizer, we convert this sentence into input tensors. Once we have our inputs ready, we pass them into the BERT model to obtain the embeddings. A key aspect of BERT is the CLS token, which represents the entire sentence. We extract the embedding corresponding to this token from the model's output. Finally, we print the BERT embedding for the given sentence, showcasing how BERT captures the semantic context, which can significantly enhance the quality of downstream NLP tasks. Now let's implement the following code to fine-tune a BERT model for a classification task. We begin by importing the necessary class, BERT for sequence classification, from the Transformers library. This specific class is designed to handle classification tasks by building on top of the pre-trained BERT model. Next, we load the model using the fromPretrain method, specifying BERT base uncased as the pre-trained model version, which is suited for general text input and disregards case sensitivity. Additionally, we set the numLabels parameter to 2, indicating that our classification task will differentiate between 2 distinct categories. This setup prepares our model to interpret the embeddings based on the task-specific data we will train it on. Finally, this code snippet serves as a preliminary step before we proceed to train the model on our specific dataset. By initializing the BERT model in this way, we leverage its powerful contextual embeddings, thereby enhancing the overall performance and relevance of our model for the classification task at hand. This is a fundamental practice in modern NLP applications, ensuring that we tailor the model effectively towards our objectives. In summary, we have delved into diverse text representation techniques, ranging from classical methods like bag of words and TF-IDF to powerful embeddings provided by Word2Vec and BERT. Each method serves specific needs within NLP, with embeddings offering in-depth semantic relationships for better predictive capabilities. Understanding these techniques allows us to select the appropriate representation based on our task and the quality of the data we are working with. As we move forward, we will explore practical applications of these text representations in various tasks, discovering how to utilize them effectively in real-world situations. Whether you're building chatbots, search engines, or sentiment analysis tools, mastering text representation is key to unlocking the full potential of NLP technologies. So stay tuned, and let's continue our journey in the fascinating world of natural language processing. To effectively analyze text and unlock insights, we turn to deep learning models, which have revolutionized natural language processing, NLP. Today, we are diving deep into these models, outlining how they function and how we can leverage them for text analysis. By the end of this session, you'll have a concrete understanding of how to apply deep learning techniques to your text data, akin to how large language models like ChatGPT operate under the hood. So far, we learned about various techniques for text representation in natural language processing, including the bag of words model and TF-IDF, which help transform raw text into numerical data. We also explored embeddings like Word2Vec and BERT, which capture semantic relationships and contextual nuances. Additionally, we highlighted the importance of fine-tuning these models for specific tasks through transfer learning. Understanding these methods is crucial for applying NLP effectively in real-world scenarios. Now, we will talk about the deep learning models specifically designed for text analysis and how they work internally. Now let's see how we can implement a simple recurrent neural network, RNN, for binary text classification using Keras. We start by importing the necessary libraries, including sequential from Keras, models, layers for our model architecture, and pad sequences to ensure uniform input size for our sequences. Next, we define our sample data, where X consists of integer sequences representing tokenized words, and Y contains binary labels corresponding to these sequences. To prepare our data for the RNN, we use the pad sequences function, setting the padding to post, ensuring all sequences are the same length. Then we define the RNN model architecture. We instantiate a sequential model and add an embedding layer that transforms our integer input into dense vectors, capturing the semantic meaning of the words. After that, we introduce a simple RNN layer that will process the input sequences and learn n-gram dependencies. Finally, we include a dense output layer with a sigmoid activation function, which is ideal for our binary classification task. Once the architecture is set, we compile the model, specifying the optimizer, loss function, and evaluation metrics before fitting the model to our padded data for training. Now let's implement an LSTM model to enhance our text classification capabilities. We start by importing the necessary LSTM layer from Keras and defining our model using the sequential API. Similar to our previous RNN model, we first add an embedding layer that transforms input integers, representing words, into dense vectors of specified dimensions. This allows the model to grasp semantic relationships effectively. Next, instead of the simple RNN layer, we use an LSTM layer, which introduces a more complex architecture designed to handle long-term dependencies better than its predecessor. LSTMs contain gates that regulate the flow of information, thus preventing issues like vanishing gradients that standard RNNs face when trained on lengthy sequences. After adding the output dense layer with a sigmoid activation for binary classification, we compile the model using the atom optimizer and binary cross-entropy loss function. Finally, we fit the model to our dataset, training it over a specified number of epochs. This setup not only builds on our previous approach, but also significantly improves our model's ability to understand and classify text, making it a powerful tool for text analysis tasks. The displayed bar chart titled Effectiveness of Deep Learning Models for Text Analysis directly compares 5 model families, RNN, LSTM, GRU, Transformer, and BERT, using effectiveness scores of 50, 75, 70, 90, and 95 respectively. The pattern is clear. Basic RNNs sit at the low end, 50, gated recurrent variants show substantial improvements, LSTM at 75 and GRU at 70, with LSTM slightly ahead, and transformer-based architectures dominate, transformer at 90 and BERT at 95. Quantitatively, moving from RNN to LSTM yields a 25-point gain, GRU yields a 20-point gain, transformer improves another 15-20 points over gated RNNs, and BERT adds a further 5-point edge over generic transformer. These differences highlight two conclusions relevant to the lesson. First, architectures that better capture long-range dependencies and manage information flow, LSTM GRU, markedly outperform vanilla RNNs. Second, attention-driven, pre-trained transformer models deliver the largest effectiveness gains, with BERTs per training and bidirectional context producing the top score. From a practical standpoint, the chart supports prioritizing transformer-based approaches for tasks requiring the highest accuracy, while considering LSTM GRU when constraints make them preferable to vanilla RNNs. Now let's implement a transformer model using the PyTorch framework along with the Hugging Face Transformers library. First, we begin by installing the necessary library, which offers access to state-of-the-art pre-trained models like BERT, simplifying the process of working with advanced NLP techniques. Next, we load the pre-trained BERT model and its tokenizer. The tokenizer is essential as it converts our raw text input into a format that the model can process, effectively transforming words into tokens while retaining information about their relationships. By ensuring our inputs are formatted to PyTorch tensor standards with return tensors equals PT, we set up the model to accept the data seamlessly. After preparing our sample text, deep learning models are fascinating. We perform a forward pass through the model. Importantly, we do this within a TorchNograd context to deactivate gradient tracking during inference for efficiency, since we're not updating model parameters at this stage. Lastly, we obtain the logits, which serve as the raw output scores from the model. These logits can subsequently be converted to probabilities for classification tasks, laying the groundwork for various applications in sentiment analysis or other NLP tasks. Now let's implement the fine-tuning process for the BERT model, specifically targeting sentiment classification using the SSD2 dataset. To start, we load the SSD2 dataset from the Hugging Face datasets library, which provides an organized dataset for training and validation. Next, we define our training parameters with the training arguments class. Here, we specify key configurations such as the output directory for model results, the number of training epochs, and batch sizes for both training and evaluation. It's essential to include parameters like warm-up steps and weight decay, as they play a critical role in optimizing the learning process and preventing overfitting, respectively. Following that, we create an instance of the trainer class, which simplifies the training workflow significantly. We assign the model, training arguments, and datasets for both training and evaluation. With all components in place, we can call trainerTrain to begin the fine-tuning process. This step adjusts the pre-trained BERT model to effectively understand and classify sentiments based on our specific dataset, enhancing its performance for the given task. Now let's see how we can evaluate the performance of our fine-tuned transformer model. By calling the trainerValuate function, we leverage the built-in capabilities of the trainer class to automatically assess our model using the evaluation dataset. This function runs the model on the evaluation set and computes a range of performance metrics such as accuracy, precision, recall, and F1 score, which are crucial for understanding our model's effectiveness. After executing the evaluation, the results are stored in the variable results. This variable contains valuable insights into how well our model performs on unseen data, allowing us to assess its generalization capabilities. To view these insights, we simply print the results. This output enables us to make informed decisions about potential optimizations, adjustments, or further fine-tuning efforts based on the model's performance. Evaluating our model is a key step, as it ensures we do not just rely on training accuracy, but rather understand how well our model can predict outcomes in a realistic context. This step is essential as we move forward to tackle text analysis tasks confidently. In summary, we explored deep learning models designed for text analysis, starting from foundational architectures like RNNs and LSTMs to the transformative power of transformer models such as BERT. We delved into hands-on implementations, showcasing code examples that elucidate the operational mechanisms of these models, while underscoring the importance of fine-tuning for specific tasks. As we continue to develop our skills, remember that deep learning and NLP are vast fields filled with incredible potential to enhance our understanding and interaction with text data. As we move forward, we'll explore practical applications of this knowledge, introducing real-world projects that lean on these powerful techniques to solve pertinent issues. So gear up, because the world of deep learning is just getting started. In today's lesson, we're diving into the fascinating world of embedding vectors for word representation. This is a crucial topic for anyone interested in natural language processing, as it allows us to transform text into numerical representations that machines can understand. So far, we learned about deep learning models in text analysis, transitioning from foundational architectures like RNNs and LSTMs to powerful transformer models such as BERT. We highlighted the importance of fine-tuning these models for specific tasks and discussed practical implementations using libraries like Keras and Hugging Face. Now, we will cover how to normalize text to reduce the influence of highly frequent words and elevate the significance of terms that hold specific relevance to our documents. Now let's implement a normalization function to prepare our text for embedding. First, we import necessary libraries, including Ray for regex operations and NLTK for natural language processing. The NLTK download stop words line ensures we have access to stop words, which are common words that don't add much meaning to our analysis. Next, we define the normalize text function, where we start by converting the input text to lowercase, ensuring uniformity in our analysis. We then remove any special characters or digits using a regex substitution, leaving only alphabetic characters and whitespace. After that, we split the clean text into tokens for easier processing. The crux of the normalization happens when we filter out the stop words by comparing our tokens against the predefined set from NLTK. This step is vital as it helps reduce noise in the data, allowing our model to focus on words that carry more semantic weight. Finally, the function returns the normalized text as a space-separated string. To demonstrate its effectiveness, we can apply this function to a sample sentence, stripping away the unneeded words and presenting a cleaner input for further analysis. Now let's see how we can implement the Word2Vec model using the Gensim library. First, we need to provide some sample sentences for training the model. In this case, we've created a small dataset with 3 sentences, each containing a few words that provide context for word relationships. Next, we instantiate the Word2Vec model by passing our list of sentences. The vector size parameter is set to 100, indicating that each word will be represented as a 100-dimensional vector. The window parameter is set to 5, which determines how many words before and after the target word we take into account during training, essentially defining the context size. The min count parameter is set to 1, allowing the model to consider all words in our small dataset, and SG is set to 0, indicating that we will use the CBOW architecture for prediction. After training the model, we can easily retrieve the vector representation for a specific word using the model's word vector capabilities. In our case, we obtain the vector for the word cat and print it. This allows us to visualize how the model encodes the semantic meaning of the word based on its context within the training sentences. Now let's see how we can implement vector arithmetic using Word2Vec embeddings to uncover semantic relationships. First, we retrieve the vector representations for the words king, queen, man, and woman from our trained model. These vectors allow us to conduct meaningful operations that reflect relationships, such as gender, based on their relative distances in the vector space. Next, we perform a simple vector arithmetic operation where we subtract the vector for man from king, and then add the vector for queen. This manipulation results in a new vector that approximates the woman vector, demonstrating how these word embeddings can capture and reflect semantic relationships. Finally, to validate our calculation, we use the similar by vector function to find the closest word in the vector space to our calculated vector. By examining the output, we should see queen or a similar word, indicating that our model effectively understands the relationship between these terms. This showcases the power of Word2Vec in capturing nuanced meanings and relationships in natural language. Now let's implement the GloV embeddings, which capitalize on global word co-occurrence statistics to capture broader context than local methods like Word2Vec. We start by ensuring we have the glove library installed, which allows us to train our GloV model efficiently. Next, we prepare our data by creating a corpus instance and fitting it using our tokenized sentences. This fitting process constructs a global word co-occurrence matrix, which is essential for training the GloV model. After preparing the data, we instantiate the GloV model, specifying the number of components for the vector representation and the learning rate. We then train the model on the co-occurrence matrix for a set number of epochs, leveraging multiple threads to speed up the process, which is particularly helpful for larger datasets. After training, we add the corpus dictionary to the GloV instance, mapping words to their indices. Finally, we can retrieve the GloV vector for specific words by indexing into the model's word vectors using the corpus dictionary, allowing us to explore the embeddings generated for these words. Now let's implement the necessary steps for performing sentiment analysis using Keras with Word2Vec embeddings. First, we ensure that Keras is installed in our environment. Then, we define a simple dataset comprised of sentences that express both positive and negative sentiments. Each sentence is classified with a label, 1 for positive and 0 for negative, which allows the model to learn from these examples. Next, we create an embedding layer that utilizes our pre-trained Word2Vec embeddings. This layer maps the input words into dense vectors of fixed size using the weights from our Word2Vec model. The trainable option is set to false, letting the model leverage the existing knowledge in the embeddings without modifying them during training. We then construct our sequential model, stacking the embedding layer, followed by a long short-term memory (LSTM) layer to effectively capture patterns and sequences of words. Finally, we add a dense layer with a sigmoid activation function for binary classification. After compiling the model with binary cross-entropy loss and the atom optimizer, we prepare our input sequences by mapping the words to their corresponding indices and padding them to ensure uniform length. Finally, we fit the model to our labeled data for a designated number of epochs, allowing it to learn to distinguish sentiments based on the input. As we wrap up our exploration of embedding vectors for word representation, it's crucial to reflect on the relevance of normalization, embedding techniques like Word2Vec and GloV and their applications in real-world tasks. Properly normalizing our input text aids in reducing noise and increasing the efficacy of our embeddings. Furthermore, embeddings encapsulate not just meanings but context, relationships, and subtle nuances in the language. In summary, understanding how to implement and utilize these embeddings equips us with powerful tools for tackling various challenges in natural language processing, making us capable of developing smarter, more effective AI systems. As you embark on your projects, keep experimenting with different embeddings and techniques. There's always more to explore in this evolving field of AI. Next time, we'll dive deeper into how to fine-tune these models for specific tasks, further enhancing their capabilities. Happy coding! In this session, we're diving into the intriguing topic of contextual word similarity through neural networks. We'll explore how the relationship between words can be quantitatively expressed, allowing us to measure how likely one word is to appear in the context of another based on their embedding similarities. So far, we learned about embedding vectors for word representation, emphasizing their significance in natural language processing to convert text into numerical forms. We discussed deep learning models for text analysis, focusing on normalization techniques to improve the relevance of embeddings, and introduced popular models like Word2Vec and GloV for generating semantic meanings. Additionally, we explored vector arithmetic and practical implementations, including sentiment analysis using these embeddings with libraries like Keras. Next, we will delve into contextual word similarity, examining how we can train neural networks to predict these relationships. To understand contextual word similarity, we need to first grasp the concept of context itself in the realm of natural language processing. When we say that one word appears in the context of another, we're referring to the surrounding words that help provide meaning to that word. For instance, consider the word bank. In various contexts, it can refer to a financial institution, the side of a river, or even a place where fish are stored. Thus, to predict whether a word is similar or related to another, we analyze the words that frequently appear around it. By leveraging neural networks, specifically models designed for word embeddings, we can effectively learn these contextual relationships. The idea is to calculate a probability score that indicates how likely a word appears given another word in its context, aligning this probability with their embedding similarities. This means we're training our model not just to understand words in isolation, but to understand how they interact with one another within sentences or larger bodies of text. Now let's take a look at how we can prepare our dataset for training the neural network. We start by importing the required libraries, including NumPy, Pandas, Keras, and scikit-learn. Next, we define a small set of sample sentences that will serve as our corpus. To convert these sentences into a format suitable for our model, we utilize the Keras tokenizer, which tokenizes the text and creates a mapping of words to integer indices. After fitting the tokenizer on our sentences, we initialize lists for input and output words. We then loop through each sentence, converting it into sequences of tokens. For each token sequence, we extract n-grams, where the first two tokens form the input and the next token serves as the output. This allows our model to learn the relationship between words in a contextual manner. Finally, we organize our input-output pairs as NumPy arrays and split the data into training and testing sets using the train-test-split function. This prepares our dataset for the subsequent stages of modeling, where we'll develop and train our neural network to predict contextual probabilities effectively. Now let's see how we can implement the structure of our neural network model to predict contextual relationships between words. First, we define a sequential model, which allows us to build the neural network layer by layer. The initial layer we add is an embedding layer, where we specify the input dimension as the total number of unique words in our dataset. This layer transforms the input word IDs into dense vector representations, enabling the model to learn more meaningful relationships. Next, the output from the embedding layer is flattened to create a one-dimensional array, which we feed into a couple of dense layers. The first dense layer has 32 neurons with a RayLU activation function, which introduces nonlinearity, allowing the model to learn complex patterns in the data. Finally, we add another dense layer with a softmax activation function to generate probabilities across the vocabulary, so the model can predict the most likely output word corresponding to the input context pair. After defining the architecture, we compile the model using sparse categorical cross-entropy as the loss function, which is suitable for multi-class classification tasks. The Atom optimizer is chosen for its efficiency in handling various training scenarios. Lastly, we train the model with our training data over 100 epochs, monitoring the training output for performance metrics. This setup equips our model to learn from the input word pairs and make accurate predictions on context words. Now let's implement a function to predict context words using our trained model. The predict context word function takes an input phrase and converts it into a sequence of indices based on the tokenizer we set up earlier. This conversion is essential as our model understands numeric representations rather than raw text. Next, we ensure that the word sequence conforms to the expected input shape by using pad sequences, which pads the sequence to a maximum length of 2, corresponding with our model's architecture. After preparing the input, we use the model predict method to get the model's output probabilities for the input sequence. By applying NP argmax, we extract the index of the word with the highest probability, which signifies our model's best prediction for the context word. To retrieve the actual predicted word, we leverage the index word mapping from the tokenizer, allowing us to convert the predicted index back to its word form. Finally, we return the predicted word from the function. To test its functionality, we input the phrase, the cat, and the output reveals the predicted context word, demonstrating how our model interprets contextual relationships effectively. Now let's implement the function to calculate the cosine similarity between the embeddings of two target words. This function, getEmbeddingSimilarity, takes in two words, the model and the tokenizer. It first retrieves the index of both words from the tokenizer's word index, allowing us to access their corresponding embeddings from the model's embedding layer. Following this, we extract the embeddings for these words from the model, which contains the learned representations of words after training. To evaluate how similar these two words are, we apply the cosine similarity metric, which yields a value ranging from -1 to 1, where 1 means the words are identical in context. We return this similarity score for further analysis. To observe our model's effectiveness, we will use the previously defined words such as cat and the predicted context from our earlier function. By executing this code, we can obtain and print the cosine similarity score, which will give us insight into how well our model's contextual predictions align with the semantic meanings represented by their embeddings. This evaluation is crucial for validating the neural network's performance in understanding nuanced word relationships. It's worth noting that, while this is a simplified example, the concepts we've discussed scale to larger models and datasets. In real-world applications, you would leverage larger bodies of text to train more robust neural networks capable of understanding nuanced relationships between words across varied contexts. Furthermore, we can incorporate more complex architectures like recurrent neural networks, RNNs, or transformers that inherently understand sequences better than simple feed-forward networks. Additionally, incorporating attention mechanisms as seen in transformer-based neural networks can further enhance the model's ability to understand context by focusing on the most relevant parts of the input sequence when making predictions. This could allow for richer and more contextual word-similar relationships to be derived. As we wrap up, the journey of understanding contextual word similarity through neural networks reveals just how intricately language operates. By embedding words into a high-dimensional space and gauging their similarities based on contextual usage, we acquire powerful tools for natural language processing. We began with foundational concepts, transitioned into practical implementation with Keras, and explored how neural networks not just predict word relationships, but can be fine-tuned for broader applications in sentiment analysis and more complex tasks. Our model not only demonstrates the technical capabilities, but also accurately reflects linguistic principles, giving us deeper insights into how machines understand human language. In the future, we can continue to refine these models by incorporating more sophisticated architectures or larger datasets. Keep experimenting and expanding your understanding of natural language processing, as there's always more to discover. Until next time, happy coding. Recurrent neural networks, or RNNs, are a class of neural networks particularly effective for text processing and sequence prediction tasks. They excel at analyzing time series data and natural language by maintaining a memory of previous inputs, making them suitable for applications like speech recognition, language modeling, and sentiment analysis. Now let's see how we can implement a simple recurrent neural network, RNN, for sentiment analysis using TensorFlow and Keras. We start by importing the necessary libraries, including NumPy and several Keras components, which will facilitate model building and training. Next, we define our dataset consisting of a few sentences labeled as positive or negative sentiments. We tokenize these sentences, breaking them down into individual words, and create a dictionary that assigns a unique integer to each word. This numerical representation is crucial because RNNs operate on numerical data, allowing us to convert our sentences into sequences of integers. Once the sentences are encoded, we apply padding to ensure that all sequences have the same length, which is necessary for batch processing in the neural network. Following that, we split our dataset into training and testing sets to evaluate the model's performance later. Now we can build our RNN model by stacking different layers. We begin with an embedding layer that transforms our integer sequences into dense vectors, capturing important semantic relationships. This is followed by a simple RNN layer, which is responsible for capturing the sequential dependencies in our data. Finally, we add a dense layer with a sigmoid activation function to produce a binary output, indicating whether the sentiment is positive or negative. After compiling the model with a binary cross-entropy loss function and the Atom optimizer, we proceed to train it on our training set over several epochs. Finally, we evaluate its performance on the test data, providing a clear indication of how well our model can generalize to unseen sentiments. The displayed figure compares measured accuracy on a 0-1 scale for 4 model types, RNN, LSTM, GRU, and CNN, and includes error bars that indicate variability for each model. Key numeric values visible on the bars are RNN at 0.75, error plus or minus 0, 0.5, LSTM at 0.89, error plus or minus 0, 0.3, GRU at 0.85, error plus or minus 0, 0.4, and CNN at 0.8, error plus or minus 0, 0.6. From these values, we draw several conclusions. LSTM has the highest central accuracy, 0.89, and the smallest uncertainty range, 0, 86, 0, 92, indicating both strong performance and consistency. GRU is the next best 0.85 with moderate variability 0, 81, 0, 89, overlapping slightly with the lower end of LSTM's range, which suggests GRU is competitive but probably slightly less accurate on average. CNN sits at 0.8 with the largest error band 0, 74, 0, 86, implying greater variability in performance and overlap with both RNN and GRU ranges. The basic RNN shows the lowest mean accuracy, 0.75, range 0, 70, 0, 80. Visually, the tallest bar, LSTM, and the position of the labeled accuracy values make it clear that LSTM outperforms the others on average. GRU offers a close alternative, and CNN and RNN perform worse on this task with more overlap and uncertainty. These patterns reinforce the lesson's discussion about LSTM and GRU addressing RNN limitations and provide empirical guidance. Prefer LSTM when highest and most reliable accuracy is needed. Consider GRU when you want nearly comparable accuracy with potentially lower computational cost, and treat CNN or vanilla RNN as less accurate or more variable options for this type of text processing evaluation. Now let's implement the LSTM model, which enhances our sentiment analysis task by improving the handling of long-term dependencies. We begin by creating a sequential model and adding an embedding layer that transforms our input text into dense vector representations. This layer, sinputdim, is set to the size of our vocabulary, while outputdim is defined to control the size of the embeddings. Next, we add the LSTM layer with 32 units, replacing the simple RNN layer from our previous implementation. This layer is crucial as it allows the model to retain information over longer sequences, directly addressing the limitations of traditional RNNs. Following the LSTM layer, we include a dense layer with a single unit and a sigmoid activation function, which enables binary classification, determining whether the sentiment of a sentence is positive or negative. We compile the model, specifying the loss function as binary cross-entropy and opting for the atom optimizer for efficient training. Finally, we train the model using our training data, specifying the number of epochs to dictate how many times the model will go through the training dataset. After training, we evaluate the model's performance on the test set, obtaining the test accuracy to assess how well our LSTM model generalizes to unseen data. Now let's implement the following GRU model using Keras, capitalizing on its streamlined architecture. We start by importing the GRU layer, which will replace the LSTM we used previously. The model is constructed using the sequential class, allowing us to stack layers sequentially. We begin with an embedding layer that transforms our input data into dense vectors of fixed size, set to 8 in this case. The input dimension is determined by the size of our dictionary plus 1 to account for padding. Next, we add the GRU layer, which features 32 units. This layer is designed to capture dependencies and processes within the input sequences more efficiently than traditional RNNs, thanks to its gating mechanism. Subsequently, we append a dense layer with a sigmoid activation function, which is crucial for binary classification tasks like sentiment analysis. After defining the model architecture, we compile it using the binary cross-entropy loss function and the atom optimizer, metrics set to accuracy for performance evaluation. Now, it's time to move on to training the GRU model with our training data, ensuring we iterate over the dataset for 10 epochs to enhance its predictive performance. Finally, we evaluate the model using the test dataset to measure accuracy, printing the results to see how well it generalizes to unseen data. Now, let's implement a convolutional neural network, CNN, for text classification using Keras. We begin by initializing the model as a sequential object, which allows us to stack layers linearly. The first layer we add is an embedding layer, which transforms the sparse input of word sequences into dense vectors capable of capturing semantic relationships. Following this, we introduce a conv1D layer, which applies convolutional operations along the 1D input sequences, designed to discover local patterns in the text data. This is crucial for tasks like sentiment analysis, where word combinations greatly influence meaning. To reduce the dimensionality of the output from the convolutional layer, we implement a max pooling 1D layer, which retains the most significant features while discarding less important ones. Finally, we add a dense layer with a sigmoid activation function to produce a binary output, indicating the classification. After defining our architecture, we compile the model using binary cross-entropy as the loss function, with the Atom optimizer for efficient training. We then train the CNN on the provided training data for a predetermined number of epochs, allowing the model to adapt and learn from the data. Finally, we evaluate its performance on the test dataset, confirming its effectiveness in comparison to the previous RNN models. As we dive deeper into the world of sequence modeling and text processing, understanding the strengths and weaknesses of these architectures becomes critical. RNNs, while pioneering in handling sequences, face challenges with long-term dependencies. LSTMs and GRUs were developed in response to these shortcomings, empowering systems to retain context over extended inputs. However, CNNs introduce a different approach, leveraging their ability to efficiently capture and generalize patterns. Depending on the nature of the dataset and task, one architecture may outperform another. Thus, as practitioners employing these technologies, it's vital to conduct thorough experimental comparisons based on specific use cases. So far, we have covered the fundamentals of recurrent neural networks, their variants like LSTMs and GRUs, and touched upon the applicability of convolutional neural networks in text processing. As we approach the conclusion, we will now reflect on the overall architecture of these models and how we can utilize techniques like transfer learning and pre-trained embeddings, which significantly enhance models in real-world applications. Now let's implement the following code to integrate pre-trained embeddings into our RNN model. First, we assume that the pre-trained embeddings have been loaded into an embedding matrix. This matrix captures rich semantic relationships between words based on extensive training data, thereby enabling our model to leverage this prior knowledge effectively. Next, we build our sequential model, starting with an embedding layer. Here, we specify the input dimension based on the size of our vocabulary and set the output dimension to 8, which defines the size of the dense vector representations of the words. Crucially, we use our embedding matrix as the weights for this layer and set it to non-trainable, meaning that the embeddings will remain fixed during the training process, preserving the learned semantic information. Following the embedding layer, we add an LSTM layer, which is well suited for capturing dependencies in sequential data. Finally, we conclude our model architecture with a dense layer that employs the sigmoid activation function for binary classification tasks. After compiling the model with the appropriate loss function and optimizer, we fit it to our training data. This integration allows our model to enhance performance by accessing the nuanced relationships embedded in the pre-trained vectors. As we conclude this exploration of recurrent neural networks for text processing, remember that the choice of architecture is ultimately influenced by the characteristics of the data and the problem at hand. Whether using a simple RNN, a robust LSTM, a compact GRU, or a powerful CNN, each model has its place in the toolkit of a machine learning practitioner. In practice, it is advantageous to experiment with different architectures, fine-tuning hyperparameters and leveraging the potential of transfer learning to ensure the best results. As the field of natural language processing continues to evolve, staying up to date with advancements in architectures and techniques will empower us to tackle increasingly complex language tasks with confidence and innovation. Thus, keep learning, keep experimenting, and as always, keep coding. Sentiment analysis using deep learning is an exciting area where we can leverage powerful algorithms to understand emotions behind text data. This can help us determine whether a piece of writing is positive, negative, or neutral. By the end of this explanation, we'll know how to take a corpus of text and apply deep learning methods to analyze and extract sentiments effectively, which is fundamental for understanding how large language models like ChatGPT work. So far, we've learned about recurrent neural networks (RNNs) and their ability to manage sequential data, particularly in the context of text processing. We've also explored the limitations of traditional RNNs, such as vanishing gradients, and how newer architectures like long short-term memory, LSTM, and gated recurrent units, GRUs, tackle those issues. We further examined convolutional neural networks, CNNs, as alternatives for text classification and discussed the efficacy of pre-trained embeddings in improving model performance. Now, we will focus on optimizing these architectures specifically for sentiment analysis. Next, we will write the code to load the movie review dataset using the Pandas library, which simplifies data manipulation and analysis. We initialize by importing Pandas and the train test split function from sklearn, model selection, to prepare our data for training and testing. The dataset is read directly from a URL, and we then display the first few rows to verify its structure. This output gives us insight into the two important columns, one containing review texts and another indicating sentiment labels, with 0 for negative and 1 for positive. Now let's see how we can implement text preprocessing to clean our reviews for better model performance. We will use the NLTK library to remove unwanted characters, convert text to lowercase, and tokenize them into words. To achieve this, we define a preprocessing function that first eliminates special characters and digits. The text is then converted to lowercase, tokenized, and filtered to remove common stop words. This cleaning process ensures that the model focuses on the most meaningful words, thereby enhancing its learning capability. Once processed, we apply this function to the review column, creating a new column with the cleaned reviews ready for analysis. Now let's implement a tokenizer to convert our cleaned text reviews into sequences of integers. We begin by initializing a tokenizer from Keras, limiting our vocabulary to the top 5,000 words for simplicity. This prevents our model from being overwhelmed by rare or irrelevant words. After fitting the tokenizer on our cleaned reviews, we transform these reviews into sequences of integers, where each word is replaced by its corresponding index in the tokenizer's word index. Next, it's crucial to ensure that all input sequences are of uniform length for our deep learning model to process them effectively. To achieve this, we use the pad sequences function, specifying a maximum length of 100. This pads shorter sequences with zeros to meet the specified length, making our data consistent. Finally, we prepare our labels for training by extracting sentiment labels from the dataset and split our data into training and testing sets using train test split. This allows us to evaluate the model's performance on unseen data later. By following this process, we set up our data for the next stages of model building and training, ensuring that our input is ready for the deep learning algorithms we'll apply. The displayed pie chart titled Sentiment Distribution in Text Data shows three categories with clear proportions: positive sentiment occupying 60% of the dataset, negative sentiment at 25%, and neutral sentiment at 15%. The dominant slice is positive, more than twice the size of the negative slice and 4 times the neutral slice, immediately indicating a class imbalance toward positive examples. From this distribution, we can draw several practical conclusions for model development. First, a naive classifier predicting positive by default could achieve a high baseline accuracy, so accuracy alone will be a misleading metric. Second, the smaller negative and neutral classes may be underrepresented during training, potentially causing poorer recall on those classes unless we apply mitigation strategies such as class weighting, oversampling of minority classes, or targeted data augmentation. Third, evaluation should include per-class precision, recall, and F1 scores, and a confusion matrix to reveal whether the model systematically confuses neutral and negative examples with positive ones. Finally, this distribution suggests that threshold tuning and calibration may be necessary if we care about balanced performance, and that any downstream decisions, for example, flagging negative reviews for action, must account for the relatively smaller negative slice to avoid biased operational behavior. Now let's implement the model architecture for our sentiment analysis task using Keras. We begin by importing the necessary layers and model type sequential, along with embedding, LSTM, dense, and dropout layers. The sequential model allows us to build our neural network layer by layer. Next, we set up our embedding layer with the input dimension based on the size of our vocabulary +1 and an output dimension of 128. The input length parameter is set to max length, defining the maximum sequence length for our input data. After the embedding layer, we add 2 LSTM layers. The first LSTM layer has 64 units and is configured to return sequences, which is essential for passing the output to the subsequent LSTM layer. To mitigate overfitting, we include a dropout layer with a dropout rate of 0.5. The second LSTM layer has 32 units, followed by a dense output layer with a sigmoid activation function suitable for binary classification. Finally, we compile the model using binary cross-entropy as the loss function, the atom optimizer, and track accuracy as a metric. This setup allows us to train the model on our data effectively. Now let's see how we can train the model by fitting it to our training data, specifying the number of epochs, batch size, and a validation split. This step helps us observe how well our model learns during training and evaluates its performance on unseen data. Now let's evaluate our model's performance on the test set to determine how effectively it generalizes to unseen data. We'll do this using the model evaluate function, which takes our test features and labels as input. The output will give us the loss and accuracy metrics, allowing us to assess how well our model predicts the sentiment of movie reviews. The accuracy score will give us direct insight into the proportion of correct predictions. Next, we will visualize our model's training history to better understand its learning dynamics over epochs. Visualization is crucial for diagnosing issues like overfitting, where the model performs well on training data but poorly on validation or test data. We will plot both the training accuracy and validation accuracy on the same graph, labeling each line for clarity. This will allow us to easily track the model's progress and quickly identify potential problems. For instance, if the validation accuracy starts to decline while training accuracy continues to rise, it indicates that the model may be overfitting. This kind of analysis is vital in tuning our model for optimal performance. Now let's implement the function to prepare a new review for sentiment prediction. We start by defining a function named prepareReview that takes a review as input. Inside this function, we first pre-process the text using our previously defined preprocessText function, which sanitizes the review by removing unwanted characters and normalizing the text. Next, we use the tokenizer to convert the cleaned review into a sequence of integers that correspond to the words in our vocabulary. This will create a numeric representation of the review. Since the model requires input of a consistent size, we then pad this sequence using the padSequences function, ensuring it has the same length as the input data used during training, specified by maxLength. Following the function, we can define a sample review. This movie was fantastic. I really loved it. After preparing this review using our prepareReview function, we proceed to make a prediction using the trained model. The model provides an output, which is a probability score. We interpret this score to determine whether the sentiment of the review is positive or negative, using a threshold of 0.5. Finally, we print the sentiment result along with the probability score, which tells us how confident the model is in its prediction. In conclusion, we have navigated through the entire process of sentiment analysis using deep learning. From understanding the basics to preparing data and building an LSTM model, we've covered essential aspects that ensure a robust analysis of sentiments in text. By implementing these techniques, we not only build models that can analyze sentiments, but also grasp the underlying mechanisms that large language models employ internally. As we continue our journey into natural language processing, remember that mastering sentiment analysis opens doors to numerous real-world applications, from customer feedback interpretation to social media monitoring. Thank you for joining me in this exploration, and be sure to apply these concepts in your own projects. Happy coding! Now let's dive into the captivating world of deep learning models for text classification. In this discourse, we will explore how these models function, the techniques involved, and how to implement them practically. So far, we covered sentiment analysis in natural language processing, focusing on emotion recognition within text using datasets and LSTM-based recurrent neural networks. We learned about data preprocessing, vectorization, model training, and evaluation, ultimately achieving sentiment analysis. Now, we will cover the integration of various deep learning models to perform text classification across broader datasets and contexts. Now let's prepare our dataset for sentiment analysis using the IMDb Movie Review dataset. First, we will load the dataset while restricting it to the top 10,000 most frequent words, which helps in managing vocabulary size and computational efficiency. We utilize TensorFlow's built-in methods to achieve this seamlessly. Next, it's crucial to ensure that all input sequences are of uniform length for batch processing. Therefore, we apply padding to our sequences, restricting them to a maximum length of 500 words. This step is essential as it allows the model to handle the data consistently without encountering issues related to varying sequence lengths. Now let's proceed to build our convolutional neural network (CNN) model. With this foundation, we can leverage the embeddings to convert word indices into dense vectors, which the CNN will process. By applying convolutional and pooling layers, we capture local patterns within the text effectively. Finally, through a dense layer, we apply a sigmoid activation to classify the sentiments observed in the reviews, preparing the model for training. This structured approach ensures that our model is ready for effective sentiment analysis on the given dataset. The displayed bar chart titled Key Concepts in Deep Learning for Text Classification summarizes 5 concepts on the x-axis: local features, CNN, global context, transformers, quantization, pruning, and zero-shot classification, with their corresponding performance percentages on the y-axis. The highest bar corresponds to global context, transformers, at 90%, indicating that models leveraging self-attention and full-sequence context achieve the top performance among these concepts. The next tallest bar is zero-shot classification at 85%, showing strong generalization ability, likely due to large pre-trained models that can transfer knowledge without task-specific fine-tuning. Local features CNN registers 80%, demonstrating that convolutional approaches capture salient local patterns effectively, but yield slightly lower performance than full-context transformer approaches. Pruning and quantization at 75% and 70% respectively appear lower than the modeling-focused approaches. These compression techniques retain much of the core performance while reducing model size or computation, but the chart makes clear there is a measurable trade-off in accuracy versus full, uncompressed models. Data labels above each bar explicitly show these percentages, and the y-axis grid lines help visualize the relative gaps. Transformers outperform quantization by 20 percentage points, outperform CNNs by 10 points, and exceed pruning by 15 points, while being 5 points higher than zero-shot. From this visualization, we can conclude that prioritizing architectures that capture global context tends to maximize classification performance. Zero-shot methods are highly competitive for transfer scenarios. CNNs remain strong for local pattern-driven tasks, and pruning quantization are valuable deployment strategies with predictable, moderate reductions in performance, insights that directly inform the design choices discussed in this lesson. Now let's implement our convolutional neural network (CNN) model for sentiment analysis. First, we start by importing the necessary layers from TensorFlow's Keras library to build our model. The sequential model allows us to stack layers linearly, beginning with the embedding layer, which transforms word indices into dense vectors of fixed size, 128 in this instance. This serves to map our input words to a continuous vector space, enhancing the understanding of semantic relationships. Next, we add a conv1D layer that applies 128 filters of size 5. This configuration helps capture local patterns in the text data, which is crucial for identifying sentiment-based cues. Following this, the max pooling 1D layer downsamples the output from the convolutional layer, reducing dimensionality while retaining only the most important features. To prepare the output for our classification task, we flatten the feature map and connect it to a dense layer with a sigmoid activation function. This final layer outputs a value between 0 and 1, indicating the probability of the input belonging to the positive sentiment class. After building the architecture, we compile the model using the Atom optimizer and binary cross-entropy loss, preparing it for training. Next, we will train this model on our prepared dataset for 5 epochs with a batch size of 64, allowing efficient processing of the input data while monitoring its performance. Now let's assess our model's performance on unseen data using evaluation metrics that provide insights into its classification capabilities. We begin by generating predictions for the test dataset based on the model's output. Specifically, we use a threshold of 0.5 to convert the model's continuous output into binary predictions, which are cast to integers for compatibility with our classification framework. Next, we utilize the confusion matrix to obtain a summary of the model's prediction outcomes. This matrix highlights how many instances were correctly and incorrectly classified for each category, helping us identify any areas where the model may struggle. To delve deeper, we also generate a detailed classification report. This report encompasses essential metrics including precision, recall, and F1 score, providing a comprehensive assessment of how the model responds to each class. By analyzing these results, we gain important insights into not just overall model accuracy, but also its performance in distinguishing between specific categories, which is crucial for improving our model in future iterations. Finally, it's essential to consider the limitations of CNNs, particularly their struggle with long-range dependencies, which can guide us in exploring further advancements, such as transformer-based models. Now, let's implement the necessary libraries to begin our work with BERT and prepare our dataset for text classification. We start by installing the Transformers library, which provides pre-trained models and tokenizers essential for using BERT. After installation, we import the BERT tokenizer and BERT4 sequence classification from the library, along with necessary PyTorch and data handling modules. Next, we utilize the BERT tokenizer to process our text data effectively. The tokenizer converts our input sequences into a format that BERT can handle, applying truncation and padding as needed. This ensures that all sequences are of uniform length and are correctly formatted as input tensors. We also create attention masks, which allow the model to differentiate between the actual words and the padding in our data. Next, we transform our labels into PyTorch tensors and create tensor dataset instances for both training and testing datasets. This structured approach makes it easier to manage the data during training and evaluation. We then use Data Loader to create iterable data loaders for both training and test datasets, enabling batch processing and shuffling for the training data to enhance the model's learning process. Now let's implement the evaluation of our BERT model using the test dataset. Here, we begin by setting the model to evaluation mode, which is essential as it informs the model that we are not training it anymore, and to deactivate any components specific to training, like dropout layers. We initialize two empty lists, predictions and true labels, where we will store the predictions from our model and the actual labels from the dataset. Next, we iterate through the batches of the test data. For each batch, we extract the input HIDs, attention mask, and labels. The attention mask is crucial for the BERT model, as it tells the model which tokens to focus on and which tokens are just padding. We perform a forward pass through the model within a torch-no-grad context to ensure that no gradient calculations are made, thus saving memory. After obtaining the model's output logits, we identify the predicted class for each input by taking the argmax of the logits over the specified dimension. We then detach and convert these predictions, along with the true labels, into NumPy arrays. Finally, we concatenate all the predictions and true labels and print the confusion matrix along with the classification report, providing insights into the model's performance on the test set. In conclusion, deep learning models for text classification encompass a plethora of techniques and architectures that cater to the vast and complex nature of human language. From CNNs grasping local features to transformers modeling global contexts, the evolution of text classification approaches continues to advance. The knowledge you've gained today sets a solid foundation for you to explore deeper aspects such as fine-tuning hyperparameters or experimenting with different neural network architectures. As you venture into implementing these models, remember, it's not only about achieving high accuracy, but also interpreting the model's predictions, understanding its limitations, and ensuring ethical standards in AI are upheld. We look forward to exploring more intriguing aspects of AI in future lessons. Happy coding and keep pushing the boundaries of what AI can achieve. Understanding word embeddings and contextual similarity is a pivotal aspect of natural language processing. Today, we're diving deep into how words relate to each other through context, based on the distributional hypothesis, which suggests that words with similar meanings often appear in similar contexts. This concept serves as the foundation for many modern NLP models, enabling them to recognize and understand the nuances of language. So far, we learned about deep learning models for text classification, focusing on practical implementations using CNNs and transformers. We explored sentiment analysis with the IMDb dataset, covering data preprocessing, model training, and evaluation techniques. We fine-tuned BERT for improved long-range dependency understanding while also examining CNNs for local feature capture. This foundation equips you to apply these models across various text classification tasks in natural language processing. Now, we will explore word embeddings and how they contribute to understanding contextual similarity in language. Let's start by understanding what word embeddings are. Word embeddings are dense vector representations of words. Unlike traditional one-hot encoding, which assigns high-dimensional, sparse vectors to words, where most values are 0, word embeddings capture semantic meaning in lower-dimensional spaces. This allows models to grasp relationships and similarities between words effectively. The beauty of word embeddings lies in their ability to encode context. Words that share similar meanings or usage patterns are placed closer together in this vector space. Consider the word king. In a one-hot encoded format, it would have its unique vector with a value of 1 in one position and zeros elsewhere. However, in a word embedding space, its representation could be something like 0, 2, -0.1, 0.5, Words like queen, prince, and monarch might occupy adjacent positions, illustrating their contextual similarity. This proximity in the vector space reflects their semantic relations, which is vital for numerous NLP tasks. To create word embeddings, we can use techniques like Word2Vec, GloVe, or fast text. Let's dive into Word2Vec, a widely used technique developed by Google. Word2Vec utilizes two architectures, continuous bag of words, CBOW, and skipgram. In CBOW, the model predicts a word based on its surrounding context, while in the skipgram model, it does the opposite by predicting surrounding words given a specific word. The displayed figure is a group bar chart titled Performance Metrics of Various NLP Techniques that compares 5 techniques: Word2Vec, GloVe, Transformers, Fast Text, and Clip. Each bar is labeled with a performance percentage, and the y-axis ranges from 0 to 100, enabling direct comparison. From the chart, Transformers register the highest value at 95%, followed by Clip at 92% and Word2Vec at 90%. GloVe appears lower at 85%, and Fast Text is the lowest among the 5 at 80%. The clear pattern is a ranking of effectiveness under the plotted metric: Transformers, Clip, Word2Vec, GloVe, Fast Text. These numeric labels and the y-axis gridlines make the relative gaps explicit. Transformers lead by a narrow margin over Clip and Word2Vec, while GloVe and Fast Text trail by larger differences. The conclusion drawn from this visualization is that, on this metric, modern transformer-based approaches, represented here by Transformers and the multimodal Clip, occupy the top performance positions, with classical embedding methods, Word2Vec, GloVe, Fast Text, showing varying but generally lower scores. Word2Vec remains strong in the middle. GloVe and Fast Text show reduced performance in this comparison. This summary complements our prior discussion by quantifying relative strengths among these techniques as presented in the chart. Now let's see how we can implement word embeddings using the Gensym library. First, we begin by installing Gensym if it's not already available in your environment, ensuring we have the necessary tools for creating and managing word embeddings. Next, we import the required libraries, including Word2Vec from Gensym and the Brown corpus from NLTK. To start working with the Brown corpus, we download it using NLTK's download function, which allows us to access this valuable text data. Once the corpus is ready, we load the sentences from it, forming the basis for our Word2Vec model training. Now we will train the Word2Vec model using the Brown corpus sentences. We specify parameters such as vector size, which determines the dimensions of our word vectors, the window size that influences the context range for our predictions, a minimum word count threshold to filter out infrequent words, and the skipgram approach to predict context words based on the given word. Finally, we save the trained model for later use, allowing us to retrieve the word embeddings at any point. This process encapsulates how we can efficiently create semantic representations of words based on their contextual usage. Now let's implement the following code to explore the word embeddings we just trained. First, we load the Word2Vec model from the file we saved earlier, which contains the learned word vectors. This is essential as it allows us to access the semantic relationships captured during training. Next, we're interested in finding words that are contextually similar to king. Using the most similar function from the model's Word2Vec interface, we can fetch the top 5 words that share similar contexts with king. This function works by measuring the proximity of word vectors in the embedding space, allowing us to identify semantically related words based on their usage in surrounding contexts. By printing the results, we can observe which words are closest to king, providing insights into how the embedding captures relationships. For instance, we might expect to see words like queen and monarch, demonstrating the model's ability to encapsulate semantic meanings. This exploration illustrates the power of word embeddings in understanding language dynamics and contextual functionality. Now let's implement the following function to load GloVe vectors into our program. The function loadGloveModel takes a file path as an argument and initializes an empty dictionary called GloveModel. We open the specified GloVe file in read mode, ensuring we handle it with UTF-8 encoding for compatibility. As we iterate through each line in the file, we split the line into individual components, with the first part representing the word and the remaining parts being the vector values. We convert these vector values into a NumPy array, which makes them suitable for efficient mathematical operations in subsequent analyses. By storing each word along with its corresponding vector representation in the dictionary, we create a comprehensive mapping of words to their embeddings. Finally, the function returns this populated dictionary. Once we define this function, we can call it to load our pre-trained GloV vectors. For demonstration purposes, we will load the vectors from the glove 6b100d txt file, which contains 100-dimensional embeddings, enabling us to leverage the power of GloV for analyzing word similarities and relationships in our NLP tasks. Now let's implement a function to compute cosine similarity, which will help us assess how closely related different word vectors are within our GloV model. We start by defining the cosine similarity function, which calculates the cosine of the angle between two vectors, providing a measure of similarity from -1 to 1. A score closer to 1 indicates that the vectors are very similar, while a score close to -1 suggests they are quite dissimilar. Next, we retrieve the vector representation for the word king. This vector serves as our reference point for comparison. We then iterate through all the words and their corresponding vectors in the GloV model, calculating the cosine similarity between each vector and the king vector. To ensure we're not comparing king to itself, we exclude it from our similarity calculations. After gathering the similarity scores in a dictionary, we sort the results to identify the top 5 most similar words, thus revealing words that are contextually linked to king. This approach allows us to see how the GloV model captures semantic relationships, echoing the findings we'd expect from the Word2Vec model, where words like monarch and queen emerge as closely related terms. Next, we will write the following code to create a domain-specific Word2Vec model using financial text. In this example, we define a small corpus consisting of sentences that include finance-related words. This serves as the training dataset for our Word2Vec model, which will allow us to observe how the term bank relates to other words in the finance context. We initialize the Word2Vec model with our defined sentences by setting the vector size to 100, deciding on a window of 2 to indicate how many surrounding words will influence the prediction, and specifying a minimum count of 1 to include all words present. The skipgram architecture is used, indicated by the sg=1 parameter, which learns to predict the context words given a target word. After training the model, we utilize the most similar function to retrieve the top 5 words that are most similar to bank based on their embeddings. This exploration reveals how context can shape the representation of words, providing insights that are particularly valuable in tasks like financial sentiment analysis or domain-specific chatbot development. As we conclude this exploration of word embeddings and contextual similarity, it's important to reflect on how these techniques impact machine understanding of language. The way models like Word2Vec and GloV encode meanings as vectors in a space fundamentally changes how algorithms process text. With embeddings, the richness of language is captured in a format that machines can understand, ultimately enabling them to perform complex tasks such as translations, text summarization, and more. Always keep in mind the importance of the distributional hypothesis and contextual similarity when you're working on NLP projects. The ability to encode meaning through embeddings opens many doors for innovation in AI, enhancing how we interact with language in various applications. In our next lesson, we will explore more advanced techniques such as transformers and attention mechanisms, diving deeper into how they build upon the foundational concepts we've discussed. Get ready for an exciting journey into the heart of modern NLP. In today's lesson, we will explore text normalization techniques, which are crucial in preparing textual data for effective analysis in natural language processing. Text normalization transforms raw text into a standard format, ensuring consistency before any further processing occurs. So far, we covered word embeddings, diving deep into their role in capturing semantic meanings and relationships in natural language. Now, we will discuss how text normalization lays the foundation for these advanced techniques by standardizing the input data. Let's start with the primary idea of text normalization. Text normalization involves converting various forms of text into a consistent format. This process is essential in natural language processing because raw text data can vary significantly, from case sensitivity to the inclusion of extraneous characters. The objective is to reduce noise and make the text easier to analyze. For instance, hello world and hello world should be treated as the same entity in many analytical contexts. This consistency reduces the dimensionality of the vocabulary and improves the performance of subsequent models. The accompanying bar chart titled Text Normalization Techniques in NLP displays the relative effectiveness in % of 7 core normalization steps. Tokenization 70%, lowercase conversion 80%, punctuation removal 60%, stemming 65%, lemmatization 75%, stop words removal 50%, and whitespace normalization 85%. Key patterns are apparent. Whitespace normalization and lowercase conversion rank highest, 85% and 80% respectively, indicating that addressing trivial formatting inconsistencies produces large, immediate gains in downstream processing. Lemmatization, 75%, is shown as more effective than stemming, 65%, illustrating the benefit of context-aware root form reduction over crude suffix stripping. Tokenization, 70%, sits in the upper middle range, reflecting its foundational role, but also that its effectiveness depends on correct implementation. Punctuation removal, 60%, and stop words removal, 50%, exhibit lower effectiveness in this chart, suggesting that indiscriminate removal can provide modest improvements, but may also discard informative signals if applied without care. From these values, we can conclude that a prioritized pipeline focusing first on whitespace and case normalization, followed by careful tokenization and lemmatization, tends to yield the largest overall impact, while punctuation and stop word strategies should be tailored to the task to avoid unnecessary information loss. Now let's see how we can implement tokenization using the NLTK library, which is a fundamental step in text normalization. First, we import the necessary components from the NLTK library, allowing us to utilize its powerful text processing capabilities. We then define a sample text string that contains various sentences and punctuation. This sample text is essential as it gives us an example to work with. Next, we employ the Word2Vec function, which efficiently splits the text into individual tokens, each word and punctuation mark treated as a separate entity. This function allows us to capture the nuances of the text structure. After tokenization, we use the print function to display the resulting list of tokens. The output will include both words and punctuation marks, exemplifying the breakdown of our original text into its basic components. This preliminary step is crucial as it lays the groundwork for subsequent normalization processes, enabling us to better analyze and manipulate the text in later stages. Now let's see how we can implement the conversion of our tokens into lowercase, a crucial step in text normalization. By transforming each token to lowercase, we eliminate any discrepancies caused by different casing, allowing for uniformity in text analysis. This can be easily achieved using a list comprehension in Python, which provides a concise and efficient way to iterate over our list of tokens. In this snippet, we create a new list called lowercase tokens. For each token in the original tokens list, we invoke the lower method, which returns the lowercase version of that token. The list comprehension permits us to succinctly build this new list in a single line of code. When we print lowercase tokens, we can expect a consistent output where words such as hello and world are now represented as hello and world. This small yet powerful change significantly enhances our ability to analyze text by ensuring that variations in casing do not interfere with our data processing. Understanding how to apply this step is fundamental as we continue refining our text normalization techniques. Next, we will write the following code to remove any punctuation and special characters from our text. This step is crucial as punctuation can skew analysis, making it harder for models to interpret the meaning of the text accurately. In our approach, we first join the lowercase tokens into a single string, which creates a continuous representation of the text. This allows us to apply regex functions effectively. We utilize Python's ray module to leverage the ray sub function, which enables us to substitute unwanted characters with an empty string. The regular expression r\w\s specifically targets any character that is not a word character, alphanumeric, or whitespace, thereby filtering out punctuation. After the substitution, we print the clean text split into tokens. The outcome is a much more refined set of tokens, free from the extraneous elements that could distract from the underlying content. This cleanup enhances our dataset's quality, ensuring that we have a clearer basis for further analysis. Now let's see how we can implement stemming using the NLTK library. First, we import the Porter stemmer from NLTK stem, which provides a straightforward implementation of the stemming algorithm. By creating an instance of the porter stemmer, we establish a stemmer object that will help reduce words to their base form. Next, we prepare to process our cleaned text. We utilize a list comprehension that iterates over each token generated from our previously cleaned input, applying the stemmer to each token. This results in a new list called stem tokens, where words are modified to their stem forms. For instance, words like running would be transformed to run, thereby reducing various inflected forms into a more uniform representation. This step is crucial in text normalization, as it minimizes the diversity in the vocabulary, facilitating better analysis by grouping words with similar meanings together. Finally, we print out the stem tokens to observe the output, helping us visualize how stemming adjusts the tokens. This process aids in preparing the dataset for further analysis, improving model performance down the line. Now let's see how we can implement lemmatization, a more context-aware approach that enhances the normalization process. In this example, we start by importing the WordNet lemmatizer and postag from the NLTK library. The WordNet lemmatizer is designed to convert words into their base or root forms based on their meanings, making it more effective than simple stemming. After initializing the lemmatizer, we extract part-of-speech tags from the previously stemmed tokens using the postag function, which assigns a grammatical category to each word. This step is crucial because lemmatization relies on understanding the context of the word, which POS tags provide. Next, we create a new list of lemmatized tokens by iterating over the combined tokens and their respective POS tags. Here, we specifically use V as the default part of speech, which corresponds to verbs, to illustrate the lemmatizer's functionality. The output will show the transformed tokens, reflecting their logical root forms. This refined processing not only standardizes the vocabulary, but also preserves the intended meaning of words, enhancing subsequent analyses. Now let's see how we can implement the removal of stop words in our text processing workflow. In this code snippet, we begin by importing the stopwords module from the NLTK corpus, which provides a comprehensive list of common English stop words. After loading the stop words into a set for efficient lookup, we proceed to filter out any tokens from our lemmatized tokens list that appear in this stop word set. Using a list comprehension, we elegantly iterate through our lemmatized tokens and construct a new list, filtered tokens, containing only those words that are not classified as stop words. This approach not only streamlines the text data by eliminating non-informative words like the and is, but also enhances the efficiency of our text analysis. Finally, we print the resulting list of filtered tokens, which now contains more meaningful words for further processing, aiding our goal of creating a cleaner and more relevant dataset for analysis. Now let's implement the final step in our text normalization process by normalizing whitespace. This code snippet focuses on collapsing multiple spaces between words into a single space, creating a cleaner and more structured text output. We achieve this by using the join method, which allows us to combine all the filtered tokens, resulting from our previous processing steps, into a single string. This ensures that any unnecessary extra spaces that may have been introduced during tokenization or other steps are eliminated. By doing this, we not only tidy up the text but also enhance its analyzability. The outcome will be a well-structured string, where phrases are neatly separated by a single space, making it ready for further analysis or model training. This step is crucial because messy text data can lead to inaccuracies in natural language processing tasks. Thus, normalizing whitespace plays a significant role in ensuring that the data retains its original meaning while being presented in a much cleaner format. This small yet effective transformation lays the groundwork for any models or analyses you will conduct in the future. To summarize what we have covered today, we introduced text normalization techniques, starting from tokenization through to stemming, lemmatization, filtering stop words, and normalizing whitespace. These processes form the bedrock for more advanced techniques in natural language processing that we will certainly encounter as we progress further in our studies. In your next lesson, we'll be diving into advanced methods such as transformers and attention mechanisms, which build upon the clean, normalized input we've prepared here. Ensuring data quality via normalization will help in training effective models capable of understanding complex language structures and generating coherent responses. Keep practicing these techniques and see how they enhance your text data processing skills. In the world of artificial intelligence and natural language processing, we stand at an exciting crossroads where understanding the deeper semantic relationships between words is crucial. Today, we're diving into advanced word embeddings, which will help us generate vectors that are compact, composed of real numbers, and retain contextual information. So far, we learned about text normalization techniques essential for natural language processing, starting with tokenization and including processes like lowercase conversion, punctuation removal, stemming, lemmatization, and stop word filtration. These methods ensure raw text data is transformed into a consistent format, reducing noise and improving the performance of analytical models. In the next lesson, we'll delve into more advanced methods that leverage this foundational work. Specifically, we will cover how to create meaningful word embeddings that encapsulate the intricacies of language, allowing artificial intelligence to understand context and relationships deeply. To kick off our journey into advanced word embeddings, let's first explore what makes them so effective. Traditional methods of representing words, such as one-hot encoding, might give us a unique identifier for each word, but they fail to capture the essential relationships between them. Imagine king and queen. In one-hot encoding, they are treated as completely unrelated. However, word embeddings aim to represent these words as points in a multidimensional space, where the geometric distance between them reflects their semantic similarity. This allows models to understand context and relationships far better than simple numerical identifiers. Now let's see how we can implement a Word2Vec model using the GenSim library in Python, a powerful tool for natural language processing. First, we begin by importing the necessary libraries, which include Word2Vec from GenSim for embeddings and Word2Tokenize from NLTK for tokenizing sentences into words. After ensuring that the NLTK punct tokenizer is available, we then define a small sample corpus containing sentences about pets. Next, we prepare our text data by tokenizing each sentence, transforming all text to lowercase to maintain consistency. This is crucial for ensuring that the model treats words in a uniform manner. Once the corpus is tokenized, we proceed to train the Word2Vec model using the tokenized sentences. The parameters we set, the vector size, window, and min count, play vital roles in defining the characteristics of our word vectors. The vector size specifies how many dimensions we want each word vector to have, while the window controls the maximum distance between the current word and the context words, allowing the model to capture relevant context without introducing excessive noise. Lastly, we can access the vector representation of a specific word, such as cat, and print it. This step demonstrates how we can retrieve the generated embeddings reflecting the relationships and contextual information learned by the model. Now let's see how we can find the most similar words to cat using our trained Word2Vec model. We achieve this through the most similar method provided by the model's word vectors, which allows us to retrieve a specified number of words that are contextually close to the target word, in this case, cat. By setting the toppend parameter to 3, we are asking the model to return the 3 most similar words based on the learned embeddings. This function uses the geometric relationships between the vectors to assess similarity, effectively leveraging the context in which the words appear within our training corpus. After obtaining the similar words, we print out the results in a formatted string, making it easy to read and interpret. This output not only showcases how well our embedding captures the relationships between words, but also reinforces the connections between cat and other terms, such as pets or dog, which naturally emerge from the usage patterns in the data. Now let's see how we can implement the GloV model to generate word embeddings. First, we initiate the GloV modeling process by importing the necessary classes, corpus and glove, from the glove package. We then prepare our corpus by creating an instance of the corpus class, which will handle the co-occurrence statistics. Using the fit method, we pass our tokenized corpus and specify a context window size, allowing the model to learn which words typically appear together. Next, we create the GloV model itself by instantiating the glove class, where we set parameters such as the number of components for the resulting word vectors and the learning rate, indicating how quickly the model should adjust its weights during training. By calling the fit method on the GloV model with the constructed co-occurrence matrix, we start training the model over a specified number of epochs, which allows it to learn the relationships between words in our entire corpus. Lastly, we can access the vector representation for a specific word, in this case, dog. By indexing into the GloV model's word vectors with the corresponding index from the dictionary, we can effectively retrieve and print the dense vector that captures the semantic meaning of dog relative to other words. The displayed horizontal bar chart compares the hypothetical effectiveness of 5 advanced embedding techniques by percentage. Word2Vec 85%, GloV 90%, fast text 80%, BERT 95%, and Roberta 92%. Reading left to right along the x-axis, effectiveness percent, the chart shows BERT achieving the highest effectiveness at 95%, followed closely by Roberta at 92% and GloV at 90%. Word2Vec is lower at 85%, and fast text sits at 80%. Each bar is labeled with its exact percentage, making the ranking and the relative gaps immediately apparent. Transformer-based contextual models, BERT and Roberta, lead by a clear margin over static embeddings, with a 3-7-point advantage, while GloV remains competitive and sits between the transformers and traditional Word2Vec. Fast text is the lowest in this comparison, suggesting that subword modeling alone does not match the overall contextualization achieved by transformers in this effectiveness metric. From these values, we can conclude that when maximum contextual understanding is required and resources permit, transformer-based embeddings are preferable, whereas GloV or Word2Vec may be acceptable trade-offs where computational cost or simplicity is a concern. Fast text strength in handling morphology and out-of-vocabulary words may still justify its use in specific scenarios despite its lower overall effectiveness score here. Now you might be wondering, how do we decide which embedding technique to use? The answer depends on the specific application and the nature of the text. Word2Vec often excels in scenarios where the focus lies on word relationships in smaller windows of context, while GloV shines when a comprehensive understanding of the relationships across entire texts is necessary. Understanding these differences allows us to make informed decisions in our projects. Now let's see how we can implement fast text using the GenSim library, which allows us to train a model for generating word embeddings. We begin by importing the fast text class from the GenSim models module. Following this, we train the fast text model on our tokenized corpus, a sequence of sentences that have been preprocessed into tokens. To configure the training, we set several parameters. Vector size determines the dimensionality of the embedding space, essentially, the length of the vectors we will derive for each word. The window parameter specifies the maximum distance between the target word and surrounding context words, allowing the model to capture nuances in word meaning based on their co-occurrence in the sentences. The min count parameter ensures that only words meeting a minimum frequency threshold will be included in the training process, while the workers parameter optimizes the training by utilizing multiple CPU cores. Once the model is trained, we can access the vector representation for a word. In this example, we retrieve the embedding for fish and print it out. This allows us to observe how fast text captures not just the meaning of fish, but also its relationship to other words, thanks to its ability to incorporate subword information. Now let's implement the following code to evaluate the relationships our Word2Vec model has learned through analogies. This snippet utilizes the most similar function found in the Word2Vec model to test its understanding of word relationships based on vector arithmetic. Specifically, by providing a combination of positive and negative words, we can derive a new word that reflects the analogy we're testing. In this example, we input woman and king as positive terms while man serves as the negative term. The model will then search for the top 3 words that best fit the relationship articulated by these inputs. The expectation is that the model understands the analogy such that the relationship king is to man as queen is to woman will yield queen as a likely top result. This process reinforces the validity of our embeddings, revealing how well they capture the intended semantics of relationships beyond mere surface-level associations. Printing out the output allows us to directly assess the model's performance, providing valuable insights into its underlying understanding of word meanings and contextual relationships. Now let's see how we can implement the cosine similarity function to evaluate the similarity between word embeddings. This begins by importing the necessary functions from the NumPy library, specifically the dot function for calculating the dot product and norm function to determine the length of vectors. Next, we define a function called cosine similarity that accepts 2 vectors as arguments. Inside the function, we compute the cosine similarity score using the formula provided, which essentially calculates the dot product of the two vectors and divides it by the product of their magnitudes. This score will offer a value between -1 and 1, where 1 indicates perfect similarity, 0 indicates orthogonality, no similarity, and -1 indicates opposite directions. To see this in action, we then calculate the similarity score between the embeddings for the words cat and dog, extracted from our Word2Vec model. Finally, we print the similarity score, allowing us to evaluate how closely related these two words are within the context of their respective embeddings. This process not only enhances our understanding of word relationships, but also demonstrates the practical application of these mathematical concepts in natural language processing. As we continue to unveil the functionalities and capabilities of advanced word embeddings, it's essential to emphasize their applications. These embeddings are not just academic discussions. They are foundational in powering real-world applications, including sentiment analysis, machine translation, and recommendation systems. By grasping how to create and evaluate these embeddings, you arm yourself with the tools needed to tackle a vast array of problems in the realm of artificial intelligence. Before we wrap up our exploration today, let's review a crucial point. The representation of words in dense vector spaces fundamentally reshapes the landscape of natural language processing. The efficient capturing of semantic meaning and context significantly enhances how machines understand language, allowing them to engage in increasingly sophisticated tasks. As you experiment with the provided Python scripts and libraries, think of the various ways embeddings can enrich your projects and contribute to greater insights. In conclusion, our journey through advanced word embeddings has shown us the power of techniques like Word2Vec, GloV, and fast text. We have seen how these vectors can articulate relationships and meaning in ways that traditional encoding methods cannot. Now, as we prepare to move into more complex realms of AI, the knowledge you've gained about these embeddings will serve as an essential building block. In our next lesson, we will explore transformer models and attention mechanisms, which further harness these embeddings to understand context at an even more nuanced level. So, keep experimenting, keep learning, and let's continue this exciting journey together. Sentiment analysis is a powerful tool that allows us to understand and quantify emotions in textual data. Advanced techniques for performing sentiment analysis, particularly through deep learning, can yield more accurate results and richer insights into a given corpus of text. In this lesson, we will dive into these advanced techniques, exploring how they are implemented and how they form the backbone of large language models like ChatGPT. So far, we learned about advanced word embeddings, including techniques like Word2Vec, GloV, and fast text, which enrich our understanding of semantic relationships in language by representing words in multidimensional vector spaces. We explored how these methods provide contextual insights that traditional encoding approaches lack, enabling machines to engage more effectively with natural language tasks. Additionally, we discussed how to evaluate the quality of these embeddings through analogy tests and similarity scores. Now we will talk about deep learning approaches to sentiment analysis and how to leverage the power of neural networks for more effective emotion detection in text. Now let's see how we can implement the preprocessing steps necessary for our LSTM model. We start by importing essential libraries from Keras that will help us handle the text data. We define our sample data consisting of a small set of sentences, along with corresponding labels that indicate whether the sentiment is positive or negative. The next step involves tokenization, where we create an instance of the tokenizer class, which helps us convert the text data into numerical format. By calling the fitOnTexts method, we allow the tokenizer to learn the unique words in our sample texts and assign unique integers to each word based on their frequency. Following this, we generate sequences of integers using text-to-sequences, which transforms our text into lists of integers that can be processed by our LSTM model. To prepare these sequences for input to the model, we use padding to ensure all sequences have the same length. By computing the maximum length of our sequences, we call pad sequences with this maximum value. This function adds zeros to the sequences that are shorter than the maximum length, creating a consistent shape for our input data. Finally, we print the padded sequences to visualize the transformation. Now that we have our padded sequences ready, it's time to build the LSTM model. Let's see how we can implement this using the Keras library. First, we import the necessary components, the sequential model, which allows us to stack layers linearly, and the LSTM, dense, embedding, and dropout layers, which will make up our neural network. Next, we define some essential parameters. The embedding dim sets the size of the dense vectors that will represent our input words. We also calculate vocab size, which corresponds to the number of unique words in our dataset, adding one for padding to ensure uniformity in sequence length. Now let's build our model. We start by creating an instance of the sequential model and adding an embedding layer that transforms the integer-encoded input sequences into dense vectors. This is followed by an LSTM layer, which captures the temporal dependencies in the text. To combat overfitting, we include a dropout layer, which randomly disables a fraction of neurons during training. Lastly, we conclude with a dense layer using a sigmoid activation function, suitable for our binary classification task. Finally, we compile the model by specifying the loss function, optimizer, and metrics, allowing it to be ready for training. Next, we will implement the training of our LSTM model using the prepared data. We start by splitting the dataset into training and testing sets, which is critical for evaluating the model's performance accurately. Using the train-test-split function from the Sclearn model selection module, we designate 20% of the data as our test set, ensuring that the model will have unseen data to validate its predictions. This is important because it helps prevent overfitting by allowing us to assess how well the model generalizes. Once the data is divided, we will proceed to fit our model using the training data. By calling the fit method on our model, we specify the training inputs xtrain and outputs ytrain, along with parameters such as the number of epochs and batch size. Each epoch represents a complete iteration over the entire training dataset, during which the model optimally adjusts its weights to minimize the loss. Training the model over multiple epochs means it gets repeated opportunities to learn from the data, refining its ability to make accurate predictions on sentiment analysis tasks. After this step, we will be ready to evaluate the model's performance on the unseen test data. Next, we will evaluate the performance of our trained LSTM model on the test data to determine how well it can predict sentiment. We begin by using the model evaluate function, which takes in the test features xtest and the actual labels ytest. This method returns two important metrics, loss and accuracy. Loss reflects how well the model's predictions match the actual values, while accuracy tells us the percentage of correct predictions made by the model. Once we retrieve the accuracy score, we multiply it by 100 to convert it into a percentage format for easier interpretation. Finally, we print the results in a formatted string, showcasing the effectiveness of our model in understanding sentiment based on unseen data. A higher accuracy score indicates that our model has successfully learned the underlying patterns in the training data and can generalize its predictions to new examples. This evaluation step is crucial in assessing the quality and reliability of our sentiment analysis model. The figure displays a side-by-side comparison of 5 techniques: Word2Vec, GloV, fast text, LSTM, and transformers, using blue bars for accuracy, left y-axis, and a red line with markers for loss, right y-axis. Numerically, accuracies increase across these techniques from 0.78 for GloV to 0.92 for transformers ordering. GloV 0.78, Word2Vec 0.82, FastText 0.85, LSTM 0.88, Transformers 0.92, while losses decrease from 0.35 for GloV to 0.15 for Transformers ordering. GloV 0.35, Word2Vec 0.3, FastText 0.25, LSTM 0.2, Transformers 0.15. The plot shows a clear inverse relationship between accuracy and loss. Methods with higher bars accuracy correspond to lower points on the red loss curve. The accuracy range spans 0, 78, 0, 92, and the loss range spans 0, 15, 0, 35, indicating that the gains in accuracy are accompanied by substantial reductions in loss. From this visualization, we conclude that in this comparison, transformer-based methods achieve the best combined performance, highest accuracy and lowest loss. LSTM ranks second, FastText sits in the middle, and traditional embeddings, Word2Vec and GloV, show lower accuracy and higher loss, with GloV performing worst on both metrics. This visual comparison complements the earlier evaluation code by contextualizing how different techniques trade off accuracy and loss. Now let's implement the sentiment analysis using Hugging Face's Transformers library, which simplifies the process of leveraging powerful pre-trained models. We start by importing the necessary pipeline module from the transformers library. The pipeline function allows us to easily set up various tasks, in this case, sentiment analysis, enabling quick access to a state-of-the-art model. Next, we load the sentiment analysis pipeline, which automatically selects a pre-trained model that best matches our task. This model has been trained on a diverse dataset, providing it with a robust understanding of language patterns and sentiments. Once our pipeline is ready, we can pass in a list of texts. These are the sentences whose sentiments we wish to analyze. The model processes these inputs and returns predictions that include both the sentiment label, e.g., positive or negative, and a confidence score indicating the model's certainty in its prediction. Finally, we iterate through the input texts and the corresponding results. For each sentence, we display the predicted sentiment alongside its score, providing clear insights into the emotional tone of the inputs. This approach showcases the efficiency and ease of using transformers to achieve high-quality sentiment analysis with minimal coding effort. In summary, we have navigated the landscape of advanced sentiment analysis techniques, from understanding RNNs and LSTMs to integrating state-of-the-art transformer models. While LSTMs provide a robust architecture for sequential data, transformers simplify model building and can often achieve better performance on large datasets. As we progress through this course, these concepts will deepen our understanding of how large language models like ChatGPT operate internally. With this grounding in sentiment analysis, we are now better equipped to tackle various natural language processing tasks, paving the way for further exploration in deep learning techniques and their applications. Thank you for joining this session, and make sure to practice implementing these methods on your own datasets. Next time, we will delve deeper into transformer models and examine the attention mechanisms that make them so powerful. Let's keep the excitement going as we journey through the fascinating world of AI. In this section, we will explore the fascinating world of embedding applications in natural language processing. We'll discuss how to normalize text to minimize the impact of frequently occurring words and instead emphasize terms that are specifically relevant to particular subsets of documents. Understanding these concepts will help you articulate how embeddings enhance the effectiveness of machine learning models in understanding and generating human language. So far, we learned about the significance of sentiment analysis and the advanced techniques used in deep learning, particularly focusing on RNNs and LSTMs. We discussed the importance of preprocessing data and the architecture of LSTM models, including tokenization and padding, to prepare input for training. Additionally, we evaluated the model's performance using accuracy metrics and explored the advantages of transformer models in enhancing natural language processing tasks. Our understanding of these concepts lays a solid foundation for future explorations into AI and deep learning techniques. Now let's implement the Word2Vec model using the GenSim library to generate word embeddings from our sample corpus. First, we install the GenSim library to ensure we have the necessary tools for our task. Once installed, we can proceed to import the Word2Vec class from GenSim. Next, we define a simple corpus consisting of sentences, where each sentence is represented as a list of words. This small dataset will serve as the input for training our Word2Vec model. After constructing the corpus, we proceed to train the model by calling Word2Vec, where we specify key parameters such as vector size, which determines the dimensionality of the word vectors, and window, which sets the maximum distance between the current and predicted word within a sentence. The min-count parameter helps us filter out words that appear less frequently, ensuring that we focus on the more relevant terms in our corpus. Finally, once our model is trained, we save it to disk. This step is crucial as it allows us to reuse the trained model in future applications without the need to retrain it. With this foundational setup complete, we can now leverage the model for various natural language processing tasks. Now let's take a look at how we can utilize our trained Word2Vec model to find words that are semantically similar to natural. First, we load the saved model using the Word2Vec load method, ensuring that we can access the learned word embeddings we previously created. Once the model is loaded, we can leverage the most similar method to retrieve the top 5 words that exhibit the closest semantic relationships to natural. This method not only provides the words themselves, but also the similarity scores, reflecting how closely related these words are based on the learned context from our training data. Finally, we can loop through the resulting list to print each word along with its respective similarity score in a formatted manner, allowing us to analyze the model's understanding and representation of semantic relationships among the words. Next, we will implement TF-IDF normalization using the TFID vectorizer from the Sklearn library. To do this, we first define a collection of sample documents that encompass varying aspects of our topic. By applying the TFID vectorizer, we convert our text data into a TF-IDF representation, which prioritizes rare but meaningful terms by scaling them based on their frequency across the documents. After fitting the vectorizer to our documents, we create a TF-IDF matrix and display it as a data frame, facilitating a clearer understanding of the term relevance and importance across the provided texts. This structured representation is invaluable for enhancing our datasets before integrating them with the embeddings. The figure compares 5 embedding and modeling techniques, Word2Vec, GloV, fast text, LSTM, and transformers, across 3 metrics displayed together: accuracy, blue bars; TF-IDF score, orange bars; and loss, red line with markers. Reading the values directly from the visualization, transformers show the highest accuracy at 0.92 and the lowest loss at 0.15, indicating the strongest overall predictive performance and most stable training outcome among the techniques. LSTM is the next best performer with accuracy 0.88 and loss 0.2, while fast text attains solid accuracy 0.85, but a noticeably lower TF-IDF score 0.68, suggesting it captures semantic relationships robustly even when term frequency-based importance is lower. Word2Vec sits in a middle position with accuracy 0.82, loss 0.3, and TF-IDF 0.72. GloV shows the lowest accuracy at 0.78 and the highest loss at 0.35, despite a TF-IDF score of 0.75. Two clear patterns emerge. Accuracy and loss are inversely related across the techniques. Higher accuracy corresponds to lower loss, and modern contextual architectures, LSTM and transformers, outperform static embedding methods in both accuracy and loss. The TF-IDF bars provide complementary insight. Transformers and LSTM also score relatively high on TF-IDF, 0.8 and 0.76 respectively, implying that these models align well with term relevance measured by TF-IDF, whereas fast text's higher accuracy, yet lower TF-IDF indicates that semantic embedding strengths can compensate for lower term frequency prominence. Overall, the visualization supports the conclusion that transformer-based approaches deliver the best combination of accuracy, low loss, and strong alignment with term relevance, and it highlights how combining TF-IDF normalization with embeddings can reveal different facets of model behavior. Now let's see how we can implement a simple binary text classification model using Keras with the embeddings generated from our Word2Vec model. We start by importing the necessary libraries, such as NumPy for numerical operations and Keras for building the model architecture. Next, we define our sample labeled data comprising 4 sentences and their corresponding sentiment labels, where a value of 1 represents a positive sentiment and 0 represents a negative sentiment. To prepare the input for our model, we convert these sentences into vectors using our pre-trained Word2Vec model, effectively capturing the semantic meanings of the words in a dense vector format. Following this, we split our dataset into training and test sets, allowing us to evaluate the model's performance on unseen data. Then we build a sequential model in Keras, which consists of an embedding layer that further processes the input sequences into dense representations, followed by a flattening layer and 2 dense layers. The final layer utilizes a sigmoid activation function that outputs a probability, making it suitable for binary classification tasks. Finally, we compile the model with binary cross-entropy loss and the atom optimizer before fitting it to the training data over several epochs, aiming to optimize the model's accuracy in predicting sentiments. This structured approach helps us to effectively categorize the texts based on sentiment, leveraging the power of embeddings. The ability to effectively use embeddings facilitates even more advanced applications, such as machine translation and chatbot systems. In machine translation, embeddings are utilized to improve the conversion of sentences from one language to another by capturing the nuances of context and syntax. For example, models like Transformer have been fine-tuned to produce high-quality translations driven by embeddings. In chatbot applications, embeddings allow for better understanding of the queries presented by users, enabling precise responses. The chatbot can recognize synonyms and contextually relevant phrases due to the compact representation provided by embeddings. Using dialogue datasets, models can learn from conversational patterns, enhancing their capacity to generate coherent and relevant replies. To wrap things up, the world of embeddings is rich and multifaceted, forming the backbone of many natural language processing tasks. Normalizing text data is a critical component to ensure your machine learning models can zero in on the most meaningful words to provide accurate predictions. Techniques like TF-IDF help highlight important terms while reducing noise from common words, making your embedding spaces more insightful. As we integrate embeddings into our natural language tasks, remember that leveraging transformers and advanced neural architectures can enhance your model's performance dramatically. Techniques such as self-attention can further refine how we understand relationships in large datasets, allowing machines to understand and generate language more effectively than ever. In the next sections, we'll delve further into embeddings with a focus on more advanced implementations and consider how to optimize them for real-world applications. This will provide you with the knowledge needed to tackle complex natural language processing challenges confidently. Thank you for joining me today. Let's keep the momentum going as we explore the exciting world of AI and language models together. Understanding word embedding techniques is fundamental in the realm of natural language processing, NLP. In this video, we'll delve into how these techniques normalize text to reduce the influence of frequently used words while highlighting those that carry distinct meaning within specific documents. So far, we learned about the importance of embeddings in natural language processing and how they provide dense vector representations that capture word meanings and relationships. We discussed various techniques such as Word2Vec and TF-IDF normalization, which enhance the effectiveness of machine learning models by minimizing the impact of commonly used words. Additionally, we explored applications of embeddings in text classification, machine translation, and chatbot systems, emphasizing their role in improving model performance. Lastly, we highlighted the significance of advanced architectures like transformers in refining language understanding and generation tasks. Now, we will dive into word embedding techniques in greater detail, focusing on how to normalize data and utilize these embeddings effectively. Now let's see how we can implement TF-IDF normalization using the scikit-learn library. We start by importing the TF-IDF vectorizer, which is the component responsible for converting our documents into a TF-IDF weighted matrix. Next, we define a small set of sample documents, which will serve as our corpus for analysis. This limited dataset consists of sentences that feature common themes, allowing us to see how TF-IDF adjusts the importance of each word based on its frequency. After setting up our documents, we create an instance of the TF-IDF vectorizer. This instance will handle the transformation process as we fit it to our documents. By calling the fitTransform method, we compute the TF-IDF scores, resulting in a sparse matrix where each element represents the weighted value of a corresponding word for each document, based on its frequency across the corpus. Lastly, to make sense of this data, we convert the sparse matrix into a dense format, which allows for easier interpretation and visualization. We also print out the feature names associated with the columns of the matrix, providing insight into which words have been weighted. This implementation effectively demonstrates how TF-IDF highlights significant terms in our text while minimizing the impact of commonly occurring words. The accompanying bar chart titled Importance of Different Word Embedding Techniques presents numeric importance scores for 6 techniques: TF-IDF 0.1, Word2Vec 0.25, FastText 0.2, GloV 0.3, BERT 0.4, and TSNE 0.35. Each technique is shown along the horizontal axis with a vertical bar whose height corresponds to its importance score. The exact score values are displayed on top of each bar, enabling precise comparisons. From these values we can rank the techniques. BERT is highest at 0.4, followed by TSNE at 0.35, GloV at 0.3, Word2Vec at 0.25, FastText at 0.2, and TF-IDF lowest at 0.1. The largest absolute gap in the chart is between BERT and TF-IDF, 0.3, indicating a substantial difference in reported importance. Intermediate gaps, for example, 0.05 between GloV and TSNE, and and 0.05 between Word2Vec and GloV show more modest distinctions. This visual makes it straightforward to see which techniques are rated higher or lower by directly reading the bar heights and annotated scores, and to draw conclusions about relative importance among the listed methods. Now let's implement Word2Vec using the GenSim library in Python to generate word embeddings from our dataset. We start by importing the necessary Word2Vec model from GenSim. Our sample sentence data consists of several tokenized sentences that will serve as the input for the model. Now let's see how we can create and train the Word2Vec model. We specify key parameters, including the vector size, which determines the dimensionality of the word vectors, the context window that defines how many neighboring words to consider, the minimum count of words to include in the training, and the number of worker threads for parallel processing. Once we have trained the model, we can retrieve the vector representation for a specific word. In our example, we choose the word cat and display its corresponding vector. This step is particularly exciting because it allows us to explore how the model represents the semantics of the word in relation to others, setting the foundation for further analysis in various applications, such as sentiment analysis. By observing these embeddings, we can gain insight into how words with similar meanings cluster together in the vector space, reflecting their contextual relationships effectively. Now let's implement a simple text classification model using the embeddings generated by the Word2Vec model. We start by preparing our training data, where we extract the vector representations of the words cat and dog from the trained Word2Vec model. This is done using a list comprehension that fetches each word's embedding, and we reshape the resulting array into 2 dimensions suitable for model training. The labels for our training data are defined as a separate NumPy array, with 0 assigned for cat and 1 for dog, enabling the model to learn to distinguish between both classes. Next, we initialize a logistic regression classifier from the scikit-learn library. This model is commonly used for text classification tasks due to its simplicity and effectiveness. We fit our classifier with the training data, allowing it to learn the associations between the embeddings and their corresponding labels. After training, we can evaluate our model using a new input. In this case, we take the embedding for the word cat, format it as a single sample input, and pass it to the classifier's predict method. The resulting output provides the predicted class for cat, showcasing how seamlessly embeddings can be integrated into machine learning workflows for effective text classification. Now let's implement the following code to visualize the quality of our word embeddings using TSNE. First, we gather the words from our trained Word2Vec model and collect their corresponding vector representations. This process entails creating a list of words, which we then convert into a NumPy array of word vectors. Next, we apply the TSNE algorithm, specifying that we want to reduce our data to 2 dimensions for easy visualization. By fitting our high-dimensional word vectors to this lower-dimensional space, we can analyze how the words cluster based on their semantic relationships. After computing the TSNE transformation, we prepare to visualize the results. We set up a scatter plot using matplotlib, where each point represents a word's position in the reduced space. To enhance the visibility of our results, we annotate each point with its corresponding word so we can easily identify which words are closely related. Finally, we add a title to our plot and display it. This visualization allows us to interpret how well our embeddings capture the meaning of words, helping us see the learned relationships clearly. As we wrap up this lesson, we've traversed the landscape of word embedding techniques, delving into methods like TF-IDF and Word2Vec, while also exploring the practical applications of these embeddings in text classification models. We examined normalization and its significance in ensuring that our models focus on meaningful terms rather than frequently used trivial ones. Additionally, we touched upon the importance of visualizing our embeddings to assess their quality effectively. Understanding and utilizing word embeddings is an indispensable skill in NLP that enhances how machines process and interpret human language. As you continue to work with these techniques, remember to experiment with different models and evaluation methods, refining your understanding of how embeddings can enhance the performance of your natural language processing tasks. Thank you for joining me in this exploration of word embedding techniques. In this lesson, we will explore how to implement neural networks for sentiment analysis using deep learning techniques. By the end of this session, you will understand the mechanics behind sentiment analysis and the foundational concepts that help large language models, like ChatGPT, operate internally. So far, we learned about the fundamentals of word embeddings in natural language processing, focusing on techniques like TF-IDF and Word2Vec. We discussed the importance of normalization to ensure that meaningful terms are prioritized over frequently used words. We also explored how word embeddings can be integrated into machine learning models for tasks such as text classification and the significance of visualizing embeddings to evaluate their effectiveness. Now we will talk about the application of these concepts in building deep learning models specifically for analyzing sentiments in text data. The displayed bar chart titled Sentiment Analysis Accuracy of Different Techniques compares 6 methods and their accuracy scores. TF-IDF 0.65, Word2Vec 0.72, Fast Text 0.75, BERT 0.85, Neural Network 0.88, and Advanced RAG 0.92. The visual shows a consistent upward progression from the simplest method, TF-IDF, to the most advanced RAG, with each bar labeled by its exact accuracy and a y-axis scaled from 0 to 1 for direct comparison. Key patterns include a notable improvement when moving from static or frequency-based representations, TF-IDF, Word2Vec, Fast Text, to contextual and learned representations, BERT and Neural Network, and a further incremental gain for the advanced RAG approach. Quantitatively, the step changes are visible. TF-IDF right arrow Word2Vec plus 0.07, Word2Vec right arrow Fast Text plus 0.03, Fast Text right arrow BERT plus 0.10, BERT right arrow Neural Network plus 0.03, and Neural Network right arrow Advanced RAG plus 0.04. From these data, we can conclude that contextual models and retrieval-augmented strategies achieve higher accuracy on this sentiment task than traditional or static embedding methods, which supports the lesson's emphasis on adopting neural architectures for improved sentiment classification. Now let's see how we can load our dataset using TensorFlow datasets. We begin by importing the TensorFlow datasets library, which provides a convenient way to access predefined datasets, including the IMDb Movie Reviews dataset. Next, we will use the load function to fetch the IMDb dataset along with its associated information. By setting the asSupervised equals true flag, we ensure that the data is returned as pairs of input features, the reviews, and labels, the sentiments. This structured format is essential for training our model effectively. Once the dataset is loaded, we can separate it into training and testing sets, with trained data representing the training samples and test data, holding the data we will use to evaluate our model later. This step is crucial, as having a well-defined training and testing split allows us to train our model while also ensuring that we can assess its performance against unseen data, ultimately helping us build a robust sentiment analysis system. Now let's implement the text preprocessing using the text vectorization layer from TensorFlow. This layer is essential for transforming our textual data into a numerical format that our neural network can utilize effectively. Here we specify max features to define the vocabulary size, ensuring our model only considers the top 10,000 words based on frequency. The sequence length parameter sets the maximum length of the input sentences to 500 tokens. Next, we create the text vectorization layer, configuring it to output integer sequences. This transformation allows our model to handle raw text by mapping each word to a unique integer index. To prepare the layer for our dataset, we use the adapt method, which fits the text vectorization layer to the text data derived from our training set. Specifically, we extract the text from the training data, excluding labels, to ensure the layer learns the vocabulary directly from the textual content without any bias from sentiment labels. With our text now vectorized into integers, we can proceed to define our neural network architecture for sentiment analysis, leveraging the preprocessed text as input. Now that we have defined our model, the next step involves training it with our preprocessed training dataset. Here, we are using the early stopping callback, which will monitor the validation loss during training. This approach helps to prevent overfitting by stopping the training process if there's no improvement in the validation loss for 3 consecutive epochs, ensuring that we retain the best weights achieved during training. Next, we will implement the model training with the fit method, which takes our batch training data and validation dataset as inputs, specifying a total of 10 epochs. This will allow the model to learn from the training data iteratively while assessing performance on validation data to fine-tune its parameters. After training, we must evaluate the model using unseen test data to determine its accuracy and loss metrics. Thus, we will utilize the evaluate function, which calculates the test loss and accuracy, and subsequently display these results. This evaluation will give us insights into how effectively our model can predict sentiments from the reviews within the MDB dataset. Now let's take a look at how we can visualize our model's training progress through accuracy and loss plots. We start by importing the matplotlib pyplot library, which provides the necessary tools for creating visual representations of our metrics. Next, we set up a figure with a specified size to accommodate two side-by-side plots. The first subplot will display the training and validation accuracy over epochs, allowing us to observe how the model's performance evolves during training. We plot both the training accuracy and validation accuracy on the same graph, labeling each line for clarity. This visual comparison is essential, as it helps us identify any potential overfitting, which occurs if the training accuracy continues improving while validation accuracy stalls or worsens. Subsequently, we create a second subplot for displaying training and validation loss. Much like the first plot, we differentiate between the two lines, which enables us to see trends in how well the model is generalizing. Finally, we adjust the layout to ensure everything fits neatly and display the plots, making it easier to analyze how the model learned and determine areas for improvement in future iterations. Now let's implement the sentiment prediction function, which will allow us to analyze new texts using our trained model. We define a function called predictSentiment that accepts a string input representing the text we want to evaluate. The first step within the function is to pre-process the incoming text. This is done by passing the text through our existing text vectorization layer. Importantly, we convert the text into a tensor format to ensure compatibility with the model. After processing the text, the function utilizes the predict method of our trained model to generate a prediction based on the vectorized input. The output from this prediction will be a probability score, which indicates the likelihood of the text reflecting a positive sentiment. To make the output interpretable, we employ a simple conditional check. If the predicted probability exceeds the threshold of 0.5, we classify the sentiment as positive. Otherwise, we label it as negative. Following the function definition, we test its functionality by calling it with two example sentences, one expressing a positive sentiment and the other a negative sentiment. The predictions from these examples will demonstrate the model's ability to classify sentiments effectively based on the trained experiences. As we wrap up, let's reflect on the key aspects we covered. Throughout this lesson, we implemented neural networks for sentiment analysis, starting with data preparation and preprocessing. We defined a sequential model designed to capture sentiment from textual data through embedding layers and LSTM units. We trained and evaluated our model, visualized performance metrics, and employed it to predict sentiment in novel texts. Understanding how to leverage deep learning for sentiment analysis is not only a practical skill, but also unfolds insights into how advanced models process language. As you continue to explore these techniques, consider further improvements like utilizing different architectures, tweaking hyperparameters, or exploring transformer models, which have gained prominence in modern NLP. Keep experimenting, stay curious, and enjoy the exciting journey in the world of AI and deep learning. The Bag of Words BOW algorithm is an essential tool in the field of natural language processing for feature extraction from text. It simplifies the representation of the text data by converting it into a numerical format that maintains the frequency of words, making it easier for algorithms to analyze and understand. So far, we have learned about implementing neural networks for sentiment analysis, focusing on various deep learning techniques, including data preparation, preprocessing, and model architecture. We have also delved into the significance of word embeddings and how to structure our models with layers like embedding and LSTM. Now, we will cover the Bag of Words algorithm, how it functions, and how to implement it using Python to prepare text data for machine learning models. The Bag of Words model operates on the premise that the meaning of a text can be conveyed through the frequency of its constituent words. Essentially, it disregards the grammar and order of words but maintains account of each word's occurrences. For instance, given a simple document, "The cat sat on the mat," the Bag of Words approach would simply create a list of counts for the words in that sentence without considering their arrangement. This can be visualized in a frequency table or a vector space model. Now that we have scikit-learn installed, we can import the necessary modules and create our sample text. To begin, we import CountVectorizer from sklearn feature extraction text, which is the primary tool for implementing the bag of words model. Next, we define a list called documents, which contains our sample sentences. This list will serve as the input for our vectorization process. Now let's implement the CountVectorizer. This class is designed to convert a collection of text documents into a matrix of token counts, effectively simplifying the analysis of word frequencies while ignoring the order of words. Once we have our documents defined, we will create an instance of CountVectorizer and then apply it to our sample sentences. This will allow us to transform the textual data into a numerical format that machine learning algorithms can readily process. Finally, we can call methods such as fitTransform on our vectorizer instance to create our document term matrix. This matrix will represent how frequently each word appears in each document, providing a foundational step for further analysis and insights into the text data. Now let's implement the following code to utilize the CountVectorizer for transforming our sample documents into a matrix of token counts. First, we start by initializing an instance of CountVectorizer, which is a crucial step in preparing our text data for analysis. This class will handle the conversion of our textual input into numerical format. Next, we call the fitTransform method on our CountVectorizer instance, passing in the list of documents we've prepared. This method not only learns the vocabulary of the text, but also generates a document term matrix, capturing how frequently each word appears in each document. After transforming the documents, we retrieve the feature names using getFeatureNamesOut, which gives us a clear mapping of the vocabulary used. Finally, we convert the sparse matrix to a dense array format with Torre, so we can easily view the resulting counts in relation to each document. By printing the feature names and the document term matrix, we can analyze the word frequencies visually, laying the groundwork for further text analysis or machine learning tasks. The displayed figure is a horizontal bar chart titled Word Frequencies in Bag of Words Model, where the y-axis lists the vocabulary terms and are cat, cats, dog, dogs, log, mat, on, sat, and the x-axis indicates frequency. Each bar has the same length corresponding to a frequency value of 1, so the clear pattern is a uniform distribution. Every listed word appears exactly once in the aggregated corpus shown. From this visualization, we can directly observe the vocabulary size 10 terms, and that both singular and plural forms, e.g., cat and cats, dog and dogs, are treated as distinct entries, implying no stemming or lemmatization was applied. The presence of function words such as and, are, and on alongside content words like mat and log highlights that common stop words remain in the vocabulary. The main conclusion drawn from this chart is that, for this small sample, raw bag of words counts produce equal weight features. This uniformity underscores why techniques that adjust or reduce dimensionality, for example, stopword removal, lemmatization, or TF-IDF weighting, may be necessary to differentiate word importance in downstream models. In the document term matrix, each row corresponds to a document, and each column corresponds to a word in the vocabulary, which is derived from all the documents. The cells contain counts of how many times each word appears in the respective document. Notice how the text representation remains numerical, yet retains all the necessary word frequency information. Now let's discuss a few variations of the bag of words model. One common enhancement is the term frequency inverse document frequency, TF-IDF approach. While BOW only counts word occurrences, TF-IDF not only counts them, but also normalizes these counts based on how common or rare a word is across all documents. This provides further importance to unique words that may better indicate a document's context. Now let's implement the TF-IDF model using the same documents. To begin, we import the tfid vectorizer from the scikit-learn library, which is crucial for transforming our text data into a format that quantifies the importance of words within the document context. We initialize the tfid vectorizer to prepare it for processing our documents. Next, we fit and transform the documents with the fitTransform method, which computes the TF-IDF representation for each word in the documents. The resulting tfid matrix reflects how significant each word is based on its frequency across the collection of documents, allowing us to understand which words carry more weight in distinguishing between the entries. To delve deeper, we extract the feature names using the getFeatureNamesOut method, providing us with a list of words represented in the TF-IDF matrix. The TORE method converts this sparse matrix into a dense array, an easier format for inspecting the results. Ultimately, we print the feature names alongside the TF-IDF matrix, which highlights the importance of each word and shows how they contribute to the overall model performance in various applications, such as text classification or clustering. Now let's take a moment to talk about the limitations of the bag of words model. One significant downside is that it cannot capture the context or semantics behind the words because it treats each word independently. For instance, the phrases goodbye and bye will be treated as entirely different features, despite their meaning overlap. Additionally, the model generates a high-dimensional feature space, which can lead to sparsity and, in many cases, curse of dimensionality in machine learning models. To mitigate some of these issues, we can implement techniques such as n-grams. An n-gram is a contiguous sequence of n items, words, from a given sequence of text. By using n-grams, we can consider combinations of words instead of individual ones, which helps in capturing context better. Now let's implement the following code to incorporate bigrams into our bag of words model. We begin by initializing the count vectorizer with the parameter n-gram range set to 2, which specifies that we want to capture two-word combinations or bigrams from our documents. Next, we fit and transform our list of documents by calling the fitTransform method. This process not only builds the vocabulary of bigrams, but also creates a matrix that represents the count of each bigram across the documents. After fitting, we can retrieve the names of the bigrams generated through getFeatureNamesOut, which helps us identify which bigrams are present in our dataset. To analyze the results further, we convert the bigram matrix into a more manageable array format using TORE. This array provides a clear view of the count of each bigram for every document, allowing us to understand the presence and frequency of these two-word combinations. Finally, we print out both the feature names and the bigram document term matrix, facilitating a deeper insight into how bigrams contribute to understanding the text's context and meaning. So far, we have discussed the fundamentals of the bag of words algorithm, learned about implementing it using Python's scikit-learn, and touched upon the advantages and disadvantages of this technique in text processing. As we move forward, it's critical to explore how to utilize these features extracted from raw text in machine learning algorithms, applying them to real-world problems like sentiment analysis, text classification, and recommendation systems. First, the next step involves preparing our text data with the bag of words, or TF-IDF representations we created earlier. We can then feed these representations into various machine learning models offered by scikit-learn. Overall, the bag of words algorithm serves as a powerful foundation for many further advancements in natural language processing. While it comes with its trade-offs, the utility in simplifying complex text data makes it an invaluable tool in any data scientist's arsenal. In this lesson, we will explore the exciting world of deep learning models for text classification, demonstrating the power of the techniques we have learned so far. So far, we learned about the bag of words BOW algorithm, which is crucial for feature extraction in natural language processing, converting text into numerical formats that reflect word frequencies. We implemented BOW using Python's scikit-learn, creating a document term matrix that highlights word occurrences. Additionally, we examined the limitations of BOW, such as its inability to capture context and proposed enhancements like the term frequency inverse document frequency, TF-IDF, and n-grams for better semantic understanding. This groundwork prepares us for applying these techniques to real-world machine learning problems. Now let's implement the command to install the necessary libraries for our deep learning text classification project. We will begin by using pip to install TensorFlow and scikit-learn, which are pivotal for model building and evaluation, ensuring we have the appropriate tools at our disposal. TensorFlow provides robust capabilities for constructing and training neural networks, while scikit-learn offers valuable utilities for data preprocessing and model validation. Next, we will import essential libraries that will assist us in processing data and building our model. Specifically, we'll utilize NumPy for numerical operations and pandas for data manipulation. The train test split function from scikit-learn is crucial for splitting our dataset into training and testing subsets, which helps in evaluating the model's performance on unseen data. We will also import text feature extraction tools such as CountVectorizer and tfid-vectorizer to transform our text data into numerical formats suitable for input into the neural network. Finally, we will bring in the necessary components from Keras, specifically the sequential model and various layers like dense, embedding, and LSTM to construct our text classification model. This foundation is essential for moving forward with our deep learning implementation. Now let's prepare our dataset for the text classification task. First, we create a dictionary that comprises two keys, review and label. The review key holds a list of product reviews, while the label key associates each review with a binary value indicating sentiment, 1 for positive reviews and 0 for negative ones. We then convert this dictionary into a pandas data frame, which allows for convenient handling and manipulation of our data. Next, we need to split the dataset into training and testing sets to evaluate the model's performance effectively. We will separate the reviews and their corresponding labels, assigning them to variables x and y, respectively. Using the train-test-split function from Sklearn, we divide our data into training and testing subsets, allocating 20% of the data for testing. This split ensures that the model can generalize well when predicting sentiments on unseen reviews. Now let's implement the TF-IDF vectorizer to convert the textual data into numerical vectors. We first instantiate the TF-IDF vectorizer and fit it to our training data, which captures the importance of words in the reviews. Finally, we transform both the training and testing sets into TF-IDF vectors, setting the stage for feeding this numerical representation into our deep learning model. The adjacent figure titled Sentiment Distribution of Product Reviews depicts a pie chart that partitions the dataset into two labeled segments, positive reviews and negative reviews. The chart shows that positive reviews occupy 2/3 of the distribution, while negative reviews occupy 1/3. Specifically, the counts underlying the chart are 4 positive and 2 negative reviews, yielding approximate percentages of 66.7% positive and 33.3% negative. From this visual, two key patterns emerge. First, the dataset is skewed toward positive examples, a 2:1 ratio, and second, the absolute sample size is very small, which makes these proportions sensitive to the addition or removal of only a single review. The practical conclusions to draw for model building are that class imbalance needs to be addressed, for example via stratified splitting, class weights, resampling, or augmentation, to prevent biased predictions favoring the majority class, and that model evaluation should account for the small sample size by using robust validation strategies, cross-validation, careful test splits, or acquiring more labeled data to avoid overestimating generalization performance. Next, we will write the code necessary to build our deep learning model using Keras. We start by creating a sequential model, which allows us to build the network layer by layer. The first layer we add is an embedding layer, which is crucial for transforming our sparse input from the TF-IDF vectorization into a dense representation. We set the input dim parameter to the number of features in our TF-IDF matrix, ensuring that the model understands the size of the input. The output dim is set to 128, indicating the size of the dense embedding, while the input length matches the number of features, maintaining consistency in input size. Following the embedding layer, we introduce an LSTM layer with 64 units. This layer is vital for capturing sequences and learning patterns from our text data. Lastly, we append a dense layer with a sigmoid activation function for binary classification, allowing the model to output probabilities between 0 and 1. Once the model structure is established, we compile it using binary cross-entropy as our loss function, the atom optimizer for efficient training, and track accuracy as our metric. This compilation step sets everything in place for training our model effectively. Now let's implement the training of our deep learning model using the prepared data. We will use the fit method to train the model, specifying the training data along with the number of epochs and batch size. Here, we set the epochs to 10, which means the model will iterate over the entire training dataset 10 times, allowing it to learn the patterns present in the data. The batch size is set to 4, meaning the model updates the weights after processing each group of 4 samples, enabling efficient gradient descent. Additionally, we provide validation data to monitor the model's performance on unseen data during training. Once training is complete, it's crucial to evaluate how well our model performs on the test dataset. This is achieved using the evaluate method, which returns the loss and accuracy metrics. By printing the test accuracy, we get an indication of the model's generalization capabilities. A high accuracy on the test set is encouraging, but we must remain cautious and consider whether the model has truly learned to generalize beyond the training data or merely memorized it. This dual step of training and evaluation is essential for ensuring our model is reliable in real-world applications. Now let's implement the following code to evaluate how well our trained model can predict sentiments from new, unseen reviews. We begin by defining a list called nreviews, which contains 2 sample reviews for testing. These reviews are intended to represent real user experiences with a product, allowing us to assess the model's performance in a realistic context. Next, we apply the same TF-IDF vectorizer we used in our training phase to transform these new reviews into numerical data, making it suitable for the model's input. This ensures consistency in how our data is represented, as the vectorizer will convert the text into the same format as our training data. Once we have the transformed data, we use the model to predict the sentiment of each review. The model outputs a prediction score between 0 and 1. In the final step, we loop through each review alongside its corresponding prediction, printing a statement that indicates whether the sentiment is classified as positive or negative based on a threshold of 0.5. This approach allows us to see firsthand how effectively our model has learned to interpret sentiments from the given data. Now let's take a look at how to add a dropout layer to our existing LSTM model, which is an essential step to help prevent overfitting. We start by importing the dropout layer from the Keras library. This layer will be incorporated into our model after the LSTM layer and before the output layer. Next, we'll update our model structure accordingly. The first layer remains an embedding layer, designed to handle the input's sparse representation and transform it into a dense format. After the embedding layer, we add our LSTM layer, which retains the capacity to learn sequential patterns from the text data. Following this, we introduce the dropout layer with a dropout rate of 0.5. This means that during each training iteration, the layer randomly disables 50% of its neurons, effectively preventing the model from becoming too reliant on any specific neurons. This technique encourages more robust learning and enhances generalization. Finally, we conclude with the dense output layer, which uses a sigmoid activation function to produce class probabilities for our text classification task. By leveraging dropout, our model can potentially achieve better performance by avoiding overfitting to a limited dataset. Finally, we must remember that the dataset we use can significantly impact the performance of our models. More extensive and diverse datasets can help improve generalization and enable our models to learn more nuanced patterns in language. Scraping data from online sources or utilizing existing datasets from libraries like NLTK or Hugging Face can provide richer training material. In conclusion, deep learning models for text classification are powerful tools in the field of machine learning and natural language processing. We've merely scratched the surface in this lesson, exploring LSTMs and TF-IDF for understanding and classifying text data. The potential applications are massive, and the ability to classify text can open the door to automating various tasks that rely on text data. So with the techniques learned, it's your turn to experiment with different datasets, tune your models, and enhance your text classification skills. Let your creativity and curiosity lead the way, and remember that the world of AI and machine learning is vast and full of opportunities. In this session, we're diving deep into advanced text processing techniques, a crucial area in natural language processing. We'll explore the distributional hypothesis, which states that words with similar meanings are often found in similar contexts. This principle serves as the backbone for many NLP applications, and understanding it will enhance our text processing capabilities. So far, we learned about deep learning models for text classification, starting with the bag of words BOW algorithm and its limitations, enhancing our model with TF-IDF, and then building an LSTM model to classify sentiments in product reviews. We discussed dataset quality and its importance in machine learning. Now we will cover advanced text processing techniques, emphasizing the distributional hypothesis and how it can improve our models and applications. One of the core concepts foundational to advanced text processing is the distributional hypothesis itself. This hypothesis suggests that words occurring in similar contexts tend to share similar meanings. To utilize this principle in practice, we can leverage word embeddings, numerical vector representations of words that capture contextual relationships. Two of the most popular word embedding techniques are Word2Vec and Glo-v. Now let's implement a Word2Vec model to generate word embeddings using the Gensim library. First, we begin by importing the required libraries, Gensim for the Word2Vec implementation and NLTK for tokenization. It's essential to ensure that the library is ready for tokenizing text, so we download the necessary tokenizer components. Next, we define a few sample sentences that will serve as the training data for our Word2Vec model. This training dataset is crucial as it provides the context from which the embeddings will be derived. We then tokenize these sentences into words, transforming each one into lowercase to maintain consistency. This step is vital for ensuring that variations in case do not affect our model. With our tokenized sentences ready, we proceed to train the Word2Vec model by specifying parameters such as the vector size and window size, which dictate the nature of our embeddings. Finally, we retrieve the vector representation for the word language, illustrating how the model captures the contextual nuances that are essential for understanding meaning in natural language processing applications. This vector will be pivotal for downstream tasks that require an understanding of word relationships in context. Now let's see how we can implement the Glo-v method to retrieve word embeddings. We begin by downloading the pre-trained Glo-v embeddings from the Stanford website. This is accomplished with a simple command that uses wget, followed by unzipping the downloaded file to access the embedding text file. Next, we establish an empty dictionary called Embeddings Index to store our word vectors. By opening the Glo-v file in read mode, we can loop through each line, where each line contains a word followed by its associated vector values. We split the line into individual components, extracting the word and converting the vector values into a NumPy array for efficient numerical processing. Each word and its corresponding vector are then added to the Embeddings Index dictionary. Finally, we can easily access the embedding for any specific word, in this case, processing, by simply indexing into our dictionary. The resulting glove vector can be printed to the console, providing us with a dense representation of the word that encapsulates its meaning based on the broader context captured in the original corpus. This approach significantly enhances the performance of any text processing model by integrating a comprehensive understanding of word semantics. Now let's see how we can implement a neural network for text classification using the Keras library. First, we define our sample data, which includes some sentences and their corresponding binary sentiment labels, where 1 represents positive sentiment and 0 for negative. To prepare our data for training, we tokenize the sentences, converting them into sequences of integers that uniquely represent each word. Since our model requires uniform input lengths, we pad these sequences to ensure they all have the same maximum length. Following this, we split our dataset into training and testing sets to evaluate the model's performance effectively later. Next, we create a sequential model that begins with an embedding layer. This layer is critical, as it transforms our integer word representations into dense vectors based on pre-trained word embeddings, capturing semantic meanings. We then add an LSTM layer, which is instrumental for processing sequential data, allowing the model to learn from the order and context of words. The final layer produces a single output with a sigmoid activation function, suitable for binary classification tasks. Now we compile the model using the Atom optimizer and binary cross-entropy loss. Lastly, we fit the model on our training data for a specified number of epochs, after which we evaluate its accuracy on the test set. This process will yield a trained model capable of predicting sentiments based on the input texts. Now let's implement the following code to utilize BERT for a sentiment classification task. We start by importing the necessary components from the Hugging Face Transformers library, including the BERT tokenizer and model specifically designed for sequence classification. After loading the pre-trained tokenizer and model, we define our sample data, which consists of several sentences paired with corresponding labels indicating their sentiment, either positive or negative. Next, we need to prepare our input data for BERT by tokenizing the sentences, ensuring they are padded and truncated to meet BERT's input requirements. We achieve this by using the tokenizer's built-in functionality, which conveniently converts our text data into a format suitable for the model. To facilitate the training process, we create a custom dataset class that inherits from PyTorch's dataset. This class organizes the tokenized inputs and their respective labels, allowing for efficient handling during training. We then define our training arguments, specifying parameters such as the output directory for model checkpoints, the number of training epochs, and the batch size. Lastly, we initialize the trainer object with our BERT model, training arguments, and the dataset, which streamlines the training cycle for our model. Once this setup is complete, we can start the training process and watch our model learn to analyze and classify sentiment based on contextual embeddings. Now let's take a look at how we can evaluate the performance of our LSTM model using classification metrics. First, we need to generate predictions on the test set by passing our test features to the trained model. The output of the model will be probabilities indicating the likelihood of each review being positive. We transform these probabilities into binary outcomes, labels of 0 or 1, by applying a threshold. In this case, we're using 0.5, meaning any probability greater than this will be classified as positive sentiment 1, while probabilities below will be classified as negative sentiment 0. Next, we'll utilize the classification report function from the scikit-learn library, which provides a comprehensive overview of our model's performance. This function not only returns the accuracy, but also details precision, recall, and the F1 score for each class. Precision reflects the accuracy of the positive predictions, while recall indicates how well the actual positives were captured. The F1 score serves as a balance between precision and recall, making it a crucial metric for evaluating classification tasks. By analyzing these metrics, we can identify strengths and weaknesses in our model's predictions, guiding potential improvements for future iterations. In summary, we've explored various advanced text processing techniques, particularly emphasizing how the distributional hypothesis informs our use of word embeddings, contextual embeddings, and how these elements integrate into deep learning models. Using models like Word2Vec, GloV, and BERT, we harness the power of meaningful numerical representations of language, vastly improving our text classification capabilities. As we wrap up this session, remember that the landscape of natural language processing is continually evolving, with new methods and techniques emerging regularly. Understanding and implementing these advanced techniques will equip you to tackle increasingly complex language tasks with confidence. So far, we delved deep into text processing techniques, from word embeddings to advanced contextual models like BERT. In our future lessons, we will continue exploring other domains and approaches within the wider spectrum of natural language processing, ensuring you have a comprehensive toolkit at your disposal. Thank you for your attention, and I look forward to seeing you in the next session. In this video, we are going to explore the fascinating applications of embeddings in natural language processing. These techniques have revolutionized how we represent and understand text data, opening the door to advanced applications that were once thought to be purely the realm of science fiction. So far, we learned about advanced text processing techniques, emphasizing the distributional hypothesis, which underlies the use of word embeddings such as Word2Vec and GVE. We explored practical applications of these embeddings in neural networks for text classification, and how contextual embeddings from models like BERT enhance understanding of language. Lastly, we discussed evaluation metrics to assess model performance in classification tasks. Now we will cover how to effectively use these embeddings in various applications like sentiment analysis, machine translation, and more. Now let's implement the following code to load and pre-process the IMDb dataset for our sentiment analysis task. We begin by setting parameters that define how we will handle our text data. Specifically, we limit our model to consider only the top 10,000 most frequently used words and restrict our sequences to a maximum length of 100 tokens. This helps ensure that our input data remains manageable while still being rich enough for analysis. Next, we load and automatically split the dataset into training and testing sets using the IMDb load data function. This function takes care of transforming the text into numerical format, where each word is represented by an integer based on its frequency in the dataset. Once we have our training and test data, we utilize the padSequences function to standardize the input lengths. This is a critical step because many neural network architectures require uniform input sizes to function correctly, enabling us to effectively feed the data into the model for training. By padding shorter sequences with zeros, we ensure a consistent format that our neural network can process. Next, we will write the following code to build a simple neural network model tailored for our sentiment analysis task. We begin by importing the necessary components from Keras, including the sequential model, as well as the embedding, LSTM, and dense layers. The sequential model allows us to stack layers linearly, making it straightforward to build our architecture. Now let's implement an embedding layer, which transforms our integer-encoded words into dense vectors of size 128. This layer is essential as it provides a way to convey the relationships between words in a continuous vector space, capturing semantic meanings. Following the embedding layer, we add an LSTM layer that captures the sequential nature of the text data. The LSTM helps the model remember previous information in the sequence, which is crucial for understanding context in language. Finally, we introduce a dense layer configured with a sigmoid activation function. This layer serves as the output layer and is designed for binary classification, allowing us to predict whether a given text expresses a positive or negative sentiment. To prepare our model for training, we compile it using the binary cross-entropy loss function, the atom optimizer, and accuracy as our evaluation metric. This setup will optimize the model during training and inform us of its performance during evaluation. Now let's implement the following code to train our sentiment analysis model on the IMDb dataset. In this step, we use the fit method of the model, where we pass our training data, xtrain and ytrain, along with important parameters like batch size and epochs. The batch size of 64 means we will process 64 samples before updating the model's weights, balancing performance and memory usage efficiently. By setting epochs to 5, we instruct the model to make multiple passes over the training data, allowing it to learn better each time. Additionally, we include validation data to provide the model with the test set xtest and ytest, which helps in monitoring its performance throughout the training process. After training, it's important to evaluate how well our model has generalized to unseen data. Now, let's see how we can implement this by making predictions on the test set. We achieve this by applying the predict method to the model, which returns the predicted probabilities. We threshold these probabilities at 0.5 to convert them into binary labels, which represent predicted classes. Finally, we use the classification report from the sklearn library to generate a comprehensive summary of the model's performance, showcasing key metrics such as precision, recall, and F1 scores. This report allows us to understand the strengths and weaknesses of our model in a nuanced way, which is crucial for real-world applications. Next, we will write the following code to utilize the T5 model for machine translation using the Hugging Face Transformers library. First, we load the T5 tokenizer and model, specifically the T5 base variant, which has been pre-trained for various tasks, including translation. By loading the tokenizer, we can convert strings into token IDs that the model can understand. Now let's prepare our input text, which indicates the translation task we want to perform. In this case, we aim to translate a simple English sentence into French. We then tokenize this input text, retrieving a tensor representation suitable for model input. The tokenizer's encode method not only transforms the text, but also formats it for processing in a batch. Next, we call the model's generate method, which handles the process of translation. After generating the output, we finally decode the result back into human-readable text using the tokenizer's decode function, skipping any special tokens that don't contribute to the translated message. By printing the translated text, we can confirm the successful translation of our input sentence, showcasing how powerful embeddings and this architecture can be for real-world language translation tasks. Next, we will implement a simple example of information retrieval using TF-IDF embeddings. First, we import the necessary libraries, Tfid vectorizer from sklearn for vectorization and numpy for numerical operations. We then define a small set of documents that we'll search through, which includes statements about natural language processing, machine learning, and deep learning. With our document set, we specify a user query that illustrates an inquiry about natural language processing. To convert our documents and the query into vector representations, we initialize a Tfid vectorizer. By fitting the vectorizer to our documents and the query, we create a TF-IDF matrix that captures the importance of each word in the context of our dataset. The last row of this matrix corresponds to our query vector. To determine how relevant each document is to the query, we compute the dot product between the query vector and each of the document vectors. This operation results in similarity scores indicating how closely each document matches the query. Lastly, we sort these scores and display the documents in order of relevance, highlighting the document with the highest similarity score to our query. Now let's implement a basic extractive summarization technique using sentence embeddings. First, we load the sentence transformers library and a pre-trained model, specifically All-Mini LM L6v2, which is adept at generating embeddings for sentences. This model allows us to leverage existing knowledge from extensive pre-training to understand the nuances of language. Next, we define a list of sample text paragraphs that we aim to summarize. By generating embeddings for these paragraphs, we create vector representations that encapsulate their meanings. After obtaining the embeddings, we calculate a single document embedding by averaging the paragraph embeddings, which provides a holistic representation of the content. Following this, we compute cosine similarities between the document embedding and the individual paragraph embeddings. This measures how closely related each paragraph is to the overall document. Now, we sort these similarity scores in descending order to identify the most relevant sentences. Finally, we iterate through the sorted indices, printing out the sentences along with their corresponding scores, allowing us to extract the key sentences that matter most in summarizing the document's core essence. In conclusion, embeddings have emerged as a cornerstone in the field of natural language processing, enabling exceptional applications from sentiment analysis to translation, information retrieval, and summarization. By representing text data as meaningful vectors, we can unlock a deeper understanding of language and the nuances within it. As we navigate through these applications, it is vital to remember that continuous developments in both model architectures and embedding techniques will only broaden our horizons further. The future is bright for natural language processing, and I encourage you to delve deeper into these fantastic applications and explore their possibilities. Thank you for joining me in this exploration of embeddings in NLP. Be sure to practice implementing these techniques. It is the best way to solidify your understanding. I hope to see you again as we continue to explore more exciting domains in natural language processing. Until next time. In today's lesson, we'll dive into the fascinating world of word embeddings, a crucial technique for representing text in a way that's digestible by machines. This knowledge is key for anyone interested in natural language processing. So far, we've learned about the powerful applications of embeddings, including sentiment analysis and machine translation. We explored how embeddings transform text into numerical vectors to enhance model performance and looked at practical implementations using frameworks like TensorFlow. Now, we will cover what word embeddings are, how they work, and why they are essential in the realm of AI. Now let's see how we can implement a simple representation of word embeddings using Python. We start by importing the NumPy library, which will help us perform numerical operations efficiently. Next, we create a dictionary called Word Embeddings, where we define the embeddings for 4 words: king, queen, man, and woman. Each word is associated with a NumPy array representing its vector in 2D space. To explore the relationships between these words, we define the getRelationship function. This function takes 3 word inputs, word 1, word 2, and word 3, and retrieves their corresponding vectors from the word embeddings dictionary. By applying a simple mathematical operation, subtracting the vector of word 1 from that of word 2, and then adding that of word 3, we can discover the relationship between these words. Finally, we call the getRelationship function with king, queen, and man to calculate a new vector that represents that relationship, and we print the resulting vector. This demonstrates how word embeddings allow us to perform calculations that reflect semantic relationships, showcasing the power of vector representations in natural language processing. The displayed scatter plot titled Word Embeddings and Their Relationships shows 4 annotated points with coordinates corresponding to the embeddings: king 0.5, 0.6, queen 0.4, 0.8, man 0.2, 0.3, and woman 0.1, 0.5, along the axes labeled Embedding Dimension 1 and Embedding Dimension 2. From the placement of the points, we observe 2 tightly related pairs. King and queen lie close together in the upper right region, while man and woman form another proximate pair lower and slightly to the left. Crucially, the vector from king to queen is equal and parallel to the vector from man to woman, queen minus king equals -0, 10.2, woman minus man equals minus 0, 10.2, which visually demonstrates the analogy king, queen, man, woman, a core example of how embeddings encode semantic offsets. The small Euclidean distances within each pair imply high similarity and correspondingly high cosine similarity, whereas distances across gender pairs, e.g., king versus man, are larger, reflecting different semantic roles. The higher second dimension values for queen and woman indicate that the second embedding coordinate contributes strongly to the feminine semantic component in this projection. Overall, the plot provides concrete visual evidence that simple vector arithmetic in embedding space recovers meaningful linguistic relationships and supports the earlier discussion about analogy and similarity measures. Now let's see how we can implement Word2Vec using the Gensim library in Python. We begin by creating a sample text corpus, which consists of a list of sentences where each sentence is represented as a list of words. This simple representation allows the model to learn from the relationships between words in various contexts. Next, we train our Word2Vec model on this corpus. We set the vector size parameter to 10, indicating that we want our word embeddings to be represented in a 10-dimensional vector space. The window parameter specifies the maximum distance between the current and predicted word within a sentence, helping the model focus on nearby words. By setting min count to 1, we ensure that even infrequent words are included in our model. Additionally, we employ multiple worker threads, defined by the workers parameter, to speed up the training process. After training the model, we can extract the embedding for a specific word, in this case, cat. By accessing the word vector directly, we can observe its numerical representation, which serves as a foundation for exploring word similarities and relationships in later applications. This functionality highlights the power of Word2Vec in uncovering semantic relationships through numerical analysis. Now let's see how we can compute cosine similarity using NumPy, which plays a crucial role in assessing the semantic similarity between word vectors. The cosine similarity function defined here takes two input vectors, vec A and vec B, and calculates the cosine of the angle between them. This is done by computing the dot product of the vectors and dividing it by the product of their magnitudes, which we obtain using the norm function from NumPy's linalg module. By leveraging this function, we gain a numerical representation of how similar the two words are based on their positions in the embedding space. Next, we define two example vectors, vector A and vector B, which correspond to the word embeddings of king and queen, respectively, retrieved from our previously trained model. These vectors serve as perfect candidates to illustrate the concept of semantic similarity. Finally, we calculate the cosine similarity for the two vectors and print the result, allowing us to quantitatively assess the similarity between king and queen. This implementation highlights how cosine similarity is a powerful tool in various applications, such as search engines and recommendation systems, where understanding relationships between words is crucial. Now let's implement a simple neural network model using TensorFlow that leverages pre-trained GloVe embeddings for sentiment analysis. In our model definition, we start with an embedding layer, where we specify the input dimension and output dimension based on our GloVe embedding matrix. By providing the GloVe weights to this layer, we initialize the embeddings with valuable pre-trained knowledge, setting trainable equals false to ensure the weights remain unchanged during training. This allows the model to utilize the rich information captured in the embeddings without introducing noise from further adjustments. Following the embedding layer, we add an LSTM layer, which is designed to capture the sequential nature of the text data, allowing the model to effectively learn from the context and order of words. We also incorporate a global average pooling 1D layer to reduce the dimensionality of the output while retaining essential information. Finally, we define a dense layer with a sigmoid activation function, which outputs the sentiment prediction. We compile the model using the Atom optimizer and a binary cross-entropy loss function, positioning it well for binary classification tasks such as sentiment analysis. Lastly, invoking model summary provides a comprehensive overview of the model's architecture, showcasing how it integrates various layers. As we explore deeper into word embeddings, we notice their pivotal role in transfer learning. Using pre-trained embeddings allows models to leverage valuable information without extensive training on massive datasets. For example, models like BERT and GPT use embeddings to build representations that understand context and relationships in a more human-like manner. That said, embeddings aren't without their challenges. They can inadvertently capture and amplify biases present in the training data. For example, if the data reflects societal biases, then the embeddings can encode those biases, leading to skewed models. This is a critical consideration in ethical AI development, and researchers are actively exploring ways to mitigate such issues. Now let's see how we can implement contextual embeddings using BERT from Hugging Face's Transformers library. First, we need to load the pre-trained BERT tokenizer and model. The tokenizer is responsible for converting our input text into a format that BERT can process, specifically into tokens that represent words or subwords. We initialize our tokenizer with the pre-trained BERT model, BERT base uncased, which is designed to handle a variety of natural language processing tasks. Next, we encode the input text, "The cat sat on the mat," using this tokenizer. This step transforms the sentence into input tensors that the BERT model can understand. The return tensors equals PT argument indicates that we want our data in PyTorch tensor format, which is essential for running our model. Once we have our tokenized inputs ready, we proceed to get the embeddings. Using the BERT model to process the encoded inputs allows us to retrieve a tensor containing the last hidden states. This tensor holds the rich contextual representations of each word within the sentence, encapsulating their meanings in relation to the entire context. Finally, we print the resulting tensor, providing us with a nuanced understanding of how BERT encodes the input text. To wrap things up, we've journeyed through the dynamic field of word embeddings, witnessing how they serve as the bridge between human language and machine understanding. We explored core concepts, practical implementations, and the ethical implications of using embeddings in AI. Today, we saw how word embeddings transform text into numerical representations, making it digestible for machines. We also learned how they help in building powerful models that have a real impact in various applications, enhancing performance across the board. As we move forward, embedding techniques will continue to evolve alongside the needs of data science and artificial intelligence, making them an exciting aspect of the ever-changing landscape of technology. Thank you for joining me in this exploration of word embeddings, and I look forward to diving into even more advanced topics in our next lesson. Contextual word representations are a cutting-edge advancement in natural language processing that allow AI models to understand language with remarkable nuance. In this lesson, we'll explore the significance of contextual embeddings and how they transform the way we handle word meanings. So far, we learned about word embeddings, from their definition to their generation methods like Word2Vec and Glo-v. Now we will cover contextual embeddings, their benefits over traditional embeddings, and their applications in real-world language processing tasks. Traditional word embeddings like Word2Vec and Glo-v provide a static representation of words, meaning that each word has a fixed vector regardless of the context in which it appears. For example, take the word bank. In a traditional embedding, the representation of bank remains the same whether it refers to a financial institution or the side of a river. This limitation can lead to ambiguity and inaccuracies in understanding the word's meaning based on context. The figure titled Comparison of Embedding Effectiveness presents a straightforward bar chart with two labeled bars, traditional embeddings at 50% and contextual embeddings at 90%. The y-axis runs from 0 to 100 and includes horizontal grid lines that make it easy to compare the bars' heights. Data labels positioned above each bar explicitly show the effectiveness percentages, 50% and 90%, emphasizing the quantitative gap. The pattern is clear and unambiguous. Contextual embeddings outperform traditional embeddings by 40 percentage points, nearly doubling measured effectiveness. From this visual, we can conclude that, for the metric depicted, contextual representations provide a substantially stronger and more reliable signal than static embeddings. The large separation between the bars indicates a consistent and significant advantage rather than a marginal improvement. Now let's implement the following code to utilize the BERT model for extracting contextual embeddings from our example sentence. We begin by importing the necessary components from the Hugging Face Transformers library along with PyTorch, which is essential for handling tensors and running the model. Next, we load the pre-trained BERT tokenizer and model using the FromPretrained method, which allows us to easily access the BERT architecture initialized with pre-learned weights. Following this, we define an example sentence. The bank can give you a loan, which contains the word bank that we aim to analyze. Now let's see how we can tokenize the input sentence. We use the tokenizer to convert our sentence into a format suitable for the model, specifying that we want the output as PyTorch tensors. Once tokenized, we can retrieve contextual embeddings by passing these inputs through the BERT model, ensuring we use a context of no gradient calculation to optimize performance. Finally, we extract the last hidden states from the model's output. This represents the contextual embeddings for each token in the sentence, allowing us to specifically isolate and analyze the embedding corresponding to bank based on its context within the phrase. By printing this embedding, we gain insight into how BERT comprehends the meaning of the word within the sentence. One significant aspect of contextual embeddings is that they contain distributed representations of word meanings, as opposed to the sparse vector representations seen in traditional embeddings. In sparse vectors, a word is often represented by a single one in a high-dimensional space, with all other dimensions filled with zeros, which can often lead to loss of semantic information. In contrast, distributed representations allow each word to capture a wide array of relationships within a rich vector space. This allows words to be represented by multiple active dimensions, preserving relationships not only with words that are similar, but also words that are related in other ways, enhancing the overall depth of understanding. This layered representation benefits downstream tasks and offers a more holistic view of how language operates. Now let's see how we can implement sentiment analysis using the BERT model, which is fine-tuned for sequence classification. We'll begin by loading the pre-trained BERT model specifically designed to classify sequences into one of three sentiment categories: positive, negative, or neutral. After that, we prepare our sample texts that represent different sentiments, ranging from enthusiasm to dissatisfaction. Next, we need to tokenize these inputs to convert them into a format suitable for the model. This involves padding the sequences to ensure uniformity and truncating longer sequences to fit the model's requirements. Once our texts are tokenized, we proceed to obtain predictions. By using the model without tracking gradients, we reduce computational overhead. The model generates logits, which are the raw scores for each sentiment class. Now we can retrieve the predicted classes by applying the softmax function and taking the index of the highest score for each input text. Finally, we will iterate through our original texts and print out the predicted sentiments, achieving a richer understanding of the sentiments conveyed in each statement. This process illustrates the power of contextual embeddings in analyzing sentiments with precision and depth. Through contextual embeddings, we also unlock the great potential of transfer learning. Pre-trained models can be adapted for various tasks by fine-tuning them with domain-specific data. This process not only accelerates development, but also enhances results in natural language understanding applications. As an added benefit, transfer learning reduces the amount of labeled data required, allowing models to generalize better and adapt to diverse datasets. Another fascinating application of contextual word representations is in machine translation. Take, for instance, the sentence, "He's banked on his experience." In each specific language, the phrase's translation depends significantly on its context. With traditional embeddings, translating such phrases can lead to misguided or clumsy translations. However, contextual embeddings provide accurate translations that respect the grammatical and semantic nuances of each language. Now let's implement a practical example of using BERT for named entity recognition. First, we load the pre-trained BERT model specifically designed for token classification tasks. It is essential to specify the number of labels corresponding to the different entity types we want to predict, which we set to 9 in this instance. Next, we prepare an example sentence that contains various named entities, such as organizations and locations. Once the sentence is defined, we tokenize it using the tokenizer associated with the BERT model. Tokenization is a crucial step, as it converts the raw text into a format that the model can understand and process effectively. With the tokenized sentence, we then proceed to obtain predictions from our model. This is done within a context that disables gradient calculations, ensuring that the process remains efficient and does not utilize unnecessary memory. After we receive the model's output, we use the argmax function to extract the highest predicted labels for each token in the input sentence. Finally, we create a loop that iterates through the tokens and their predicted labels, decoding each token back into its string form while displaying both the token and its associated predicted label. This approach allows us to see how BERT effectively identifies and classifies named entities within the context of the sentence. For those new to the concepts of contextual word representations, it is vital to recognize how this approach overcomes many limitations associated with traditional word embeddings. Contextual embeddings address challenges such as polysemy, syntactic variations, and semantic nuances by providing models with enriched representations. This empowerment leads to better performance in a wide range of natural language processing tasks, along with practical applications in areas like sentiment analysis, machine translation, and named entity recognition. As we wrap up this segment, it is essential to stay aware of the ethical considerations surrounding contextual embeddings. Just like traditional embeddings, contextual models can also perpetuate biases found in training data. Addressing these biases is critical to ensuring fair and equitable outcomes in AI systems that rely on these embeddings. To conclude, contextual word representations fundamentally change how language is understood by machine learning models, enabling nuanced comprehension of text based on context. From state-of-the-art models like BERT to their extensive applications in industry, the future is bright for these advanced NLP techniques. Stay curious, keep exploring, and continue on your journey into the fascinating world of natural language processing. Natural language processing, NLP, is an exciting area of artificial intelligence that focuses on enabling machines to understand and interpret human language. In this segment, we'll delve into advanced techniques for representing text in a way that machine learning models can comprehend and utilize for various applications. So far, we have learned about the evolution of word embeddings, the drawbacks of static embeddings, and the significance of contextual embeddings like BERT. Now we will explore various techniques used to represent text data for more effective natural language processing. Now let's see how we can implement tokenization using Python's Natural Language Toolkit, or NLTK, to transform our text into manageable units. First, we need to import the necessary components from the NLTK library and ensure we have the Punkt tokenizer models downloaded, which are essential for this process. Next, we will define a sample sentence about natural language processing, encapsulating the essence of the field. The sentence will then be passed to the Word2Vec function, which takes the text and splits it into tokens. These can be words, phrases, or punctuation marks. Finally, we will print the resulting tokens, allowing us to visualize the outcome. After executing this code, you can expect an output that will show individual tokens derived from the sentence, including both words and punctuation. This tokenization step is crucial as it lays the groundwork for further analysis and processing of the text, making it an essential component in any NLP task. Now let's see how we can implement TF-IDF using the TFID vectorizer from the Sklern library, which allows us to convert a collection of raw documents into a matrix of TF-IDF features. In this example, we begin by defining a small corpus consisting of 3 simple sentences that express our fondness for programming and using Python. Each of these sentences will serve as input for our TF-IDF transformation. Once the documents are established, we create an instance of TFID vectorizer. This vectorizer will process our corpus and compute the TF-IDF scores, which represent how important a word is to a particular document relative to the entire collection. Next, we call the FitTransform method on our vectorizer with the documents as an argument. This method performs the necessary calculations and returns a sparse matrix, TFID matrix, showcasing the TF-IDF scores for each term in the context of the 3 documents. Lastly, using the Torre method, we convert the sparse matrix into a dense array format for easier visualization and understanding. Additionally, the getFeatureNamesOut method retrieves the list of terms that correspond to the columns in our TF-IDF matrix, allowing us to relate each score back to its respective term. This implementation is crucial as it highlights how different words contribute to the overall content of the documents. The displayed horizontal bar chart titled Key Concepts in Natural Language Processing quantifies relative importance across 5 techniques: tokenization 10, TF-IDF 30, word embeddings 25, contextual embeddings 40, and bias evaluation 20. A clear pattern emerges. Contextual embeddings receive the highest importance score 40, substantially above tokenization 10, and notably above traditional embeddings 25. TF-IDF also holds a strong role 30, positioned between contextual embeddings and static word embeddings, indicating that classical feature-based methods remain valuable alongside neural representations. Bias evaluation with a value of 20 is a meaningful component, greater than tokenization but lower than embedding methods, signaling that fairness considerations are an integral part of the pipeline rather than an afterthought. From these values, we can conclude actionable priorities for model design. Invest most in contextual embedding technologies for representational power, maintain TF-IDF as a lightweight or complementary feature engineering approach, continue using word embeddings where appropriate, and incorporate bias evaluation early in development. The relatively low numeric importance of tokenization reflects its nature as a foundational preprocessing step, vital for correctness but not the primary driver of representational sophistication. So ensure robust tokenization while focusing resources on contextual modeling and bias mitigation. Next, we will implement a simple version of the Word2Vec model using the GenSim library to generate word embeddings. First, we define a list of sentences that our model will learn from. Each sentence is represented as a list of words, allowing the model to capture the context and relationships between them effectively. Now let's see how we can initialize the Word2Vec model. We create an instance of the model by passing our list of sentences, specifying the vector size to 100 dimensions, setting a window size of 5, defining a minimum word count threshold of 1, and opting for the skipgram model as g equals 0. This configuration helps the model to understand word associations based on how frequently words appear in similar contexts. After training the model with our sentences, we can examine the word vector associated with the word football. This step allows us to observe how the model represents the word in high-dimensional space. The result is a vector output that illustrates the relationships between football and other words based on their proximity in this vector space, providing insight into the underlying semantics captured during training. This demonstration serves as a foundation for understanding more advanced word embedding techniques in NLP. Now let's see how we can implement BERT to obtain contextual embeddings for our text. First, we import the necessary libraries, BERT Tokenizer and BERT Model from the Transformers library, alongside PyTorch, which will handle our tensor operations. The tokenizer is essential for encoding our input text, and we load a pre-trained model, specifically BERT base uncased, which is widely used for various NLP tasks. Next, we define a sample sentence that conveys a statement in natural language processing. We then utilize the tokenizer to convert this sentence into a format suitable for BERT, specifically a tensor representation. This transformation allows the model to understand the structure and semantics of the input. After preparing the inputs, we pass them to the BERT model. The model processes the input and returns outputs that include various state representations of the input tokens. Crucially, we extract the last hidden states from these outputs. This last hidden state encapsulates a rich, high-dimensional embedding of each token, reflecting their contextual meanings as influenced by the surrounding words. Finally, we print these last hidden states, which provide powerful representations that can be used for tasks such as sentiment analysis or language translation. Next, we will implement a basic sentiment evaluation function to illustrate how we can assess the sentiment of given sentences. This function checks for the presence of the word love in the text to determine if the sentiment is positive or negative, simplifying a more complex sentiment analysis process. For this example, we will use a list of test sentences that cover different sentiments. We define the evaluate sentiment function, which simulates behavior typical of a pre-trained sentiment analysis model by returning positive when the word love is present. Otherwise, it will return negative. Following that, we create a list of sentences to test, which includes statements about programming and general affirmations of rights. Now let's iterate through each sentence in our test list. For each sentence, we will apply our evaluate sentiment function and print out the resulting sentiment. This allows us to observe how our simplistic function reacts to varying contexts, providing insights into potential biases in model outputs. Ultimately, it's important to consider how such evaluations might reflect biases and influence interpretations in broader NLP applications. As we wrap up this insightful journey through advanced text representation techniques, it's crucial to remember the foundational steps we've covered. We started with tokenization, which is essential for breaking down text, moved on to numerical representation through methods like TF-IDF and embeddings, and then shifted towards advanced contextual representations using models like BERT. We also highlighted the significance of ethical considerations and bias evaluation in NLP models. So far, we have learned about techniques that allow us to convert raw text into numerical representations suited for machine learning models. Going forward, we may explore the integration of these techniques into specific applications and fine-tune models to enhance their performance. And I'll leave you with one last thought. Language is as rich and diverse as our imaginations, and the challenge lies in teaching machines to interpret that depth meaningfully. Let's keep experimenting and pushing the boundaries of what machines can understand. Embedding representation methods in deep learning have become a cornerstone for understanding language, enabling machines to grasp the nuances of human communication. These dense vectors are called word embeddings. So far, we learned about natural language processing, NLP, and its focus on enabling machines to understand human language, starting with the transformation of raw text data into numerical formats through techniques like tokenization, TF-IDF, and embeddings. We discussed advanced techniques such as contextual embeddings like BART, emphasizing the importance of ethical considerations and bias evaluation within these models. The methods covered prepare us for more effective applications in NLP, encouraging exploration and fine-tuning in our future lessons. Now, we will delve deeper into embedding representation methods and explore how they help us understand language in machine learning applications. Let's begin with the concept of word embeddings. Traditional representations of words often treat each word as a unique entity, leading to high-dimensional, sparse matrices that are not only computationally inefficient but also fail to capture the relationships between words. This is where embeddings shine brightly. Word embeddings represent words in continuous vector spaces, allowing us to capture the context and utility of words in relation to others. These embeddings help the machine to understand synonyms, antonyms, complete phrases, and even complex linguistic structures to some extent. The idea behind it is pretty simple. Similar words should have similar vector representations. Now let's see how we can implement a basic Word2Vec model using the Gensim library. First, we need to install the library to access its powerful embedding capabilities. Once we have Gensim installed, we begin by defining a corpus of sentences that we will use to train our model. In this case, we have a small collection of sentences related to machine learning and artificial intelligence. Next, we create the Word2Vec model by passing our sentences into it, carefully selecting several parameters that shape how our model operates. The vector size parameter specifies the number of dimensions for our word vectors, allowing our model to capture relationships in a meaningful way. The window parameter dictates how many words to consider around the target word, providing context during training. The min-count parameter ensures that only words appearing with a minimum frequency are included, filtering out noise from infrequent terms. Finally, the SG parameter is set to 1 to indicate that we are using the skipgram approach. After training the model, we retrieve the vector representation for the word learning and print it. This vector is a dense encapsulation of learning's contextual meaning based on its occurrences in the provided corpus, highlighting the utility of Word2Vec in understanding language. The displayed figure is a horizontal bar chart titled Key Embedding Representation Methods in Deep Learning, with the x-axis labeled Importance, Relative Scale, and the y-axis listing 5 methods: Word2Vec, GloV, BERT, FastText, and ELMO. Each method has a numeric importance value shown on its bar. BERT equals 40, Word2Vec equals 35, FastText equals 30, GloV equals 25, and ELMO equals 20. From these values, we can draw clear patterns. Transformer-based contextual embeddings, BERT, are rated highest, followed closely by Word2Vec, indicating strong continued relevance of predictive context models. FastText occupies a middle position, reflecting utility for subword information and rare word handling. GloV, a global count-based method, is lower but still notable. ELMO has the smallest relative importance in this comparison. The spacing between values highlights relative emphasis. BERT leads by a moderate margin, 5 points over Word2Vec, and there is a steady decline down to ELMO, indicating a spectrum from state-of-the-art contextual transformers to earlier and more specialized embedding techniques. Because the x-axis is labeled as a relative scale, these numbers should be interpreted as comparative emphasis rather than absolute measures. Nevertheless, the figure reinforces the lesson's point that modern NLP places particular significance on contextual, transformer-based representations, while traditional and specialized methods remain valuable for specific use cases. Now let's implement GloVe embeddings in Python. First, we need to install the GlovePython binary package, which provides the necessary functionalities to work with GloVe. Next, we'll create a small sample corpus from a list of sentences to fit our model. These sentences represent the context in which the words will be analyzed, serving as the foundational data for generating embeddings. We instantiate a corpus object and utilize its fit method with a specified context window to analyze word co-occurrences within the sentences. After building our corpus, we initialize a glove model, where we define key parameters like the number of dimensions for our word vectors and the learning rate. Following that, we fit the model using the corpus's word counts and specify the training epochs and threading options for efficiency. This process trains the GloVe model to capture the semantic relationships between words based on their co-occurrences. Finally, we can access and print the embedding vector for the word learning, illustrating how GloVe effectively represents its relationship with other words. This demonstration encapsulates how GloVe captures complex relationships in a global context, enabling machines to understand language intricacies better. Now let's see how we can implement BERT for extracting contextual embeddings using the Transformers library by Hugging Face. First, we need to install the library to access BERT and its tokenizer, which prepares our input text for processing. Once we have the library installed, we can load the pre-trained BERT tokenizer and model. In our code, we initialize the tokenizer with the BERT base uncased version, which handles the text input and converts it into the format that the model requires. After that, we load the BERT model itself from the same pre-trained source, setting the stage for our work with embeddings. Next, we define a sentence about natural language processing, which we will input into the BERT model. By using the tokenizer, we transform this text into a format understandable by the model while also indicating that we want to return the tensors for PyTorch. After passing the inputs to the model, we receive the last hidden states, which are the contextual embeddings representing each word in the input sentence. These embeddings now contain rich context because they are dynamically generated based on the input text, showcasing BERT's capability to understand and differentiate between meanings based on context. Lastly, we print these last hidden states to analyze the embeddings further. Now let's implement the following function to evaluate the biases present in our word embeddings. The evaluate bias function takes two words as input parameters, computing the similarity score between them using the model's word vector representation. This similarity score indicates how closely associated the two words are in the embedding space. To observe potential biases, we can evaluate pairs such as nurse and woman, as well as doctor and man. By checking the similarity scores for these pairs, we can identify any ingrained associations that might exist in the model's embeddings. If the score for nurse and woman is significantly higher than that for doctor and man, it may suggest that the model has absorbed societal stereotypes about gender roles. This practice of evaluating similarity scores is crucial in understanding the ethical dimensions of AI. Continuous assessments and adjustments based on such analyses can help us ensure that our models are fair and responsible, minimizing the perpetuation of existing biases in real-world applications. It's an essential step toward creating conscientious AI systems. As we wrap up our exploration of embedding representation methods, it's clear that embedding techniques significantly influence the way machines understand language. From traditional methods like Word2Vec and GloVe to advanced contextual embeddings with BERT, we've seen how these representations enrich the analysis and processing of human language. Understanding words solely in isolation is a bygone concept, and dynamic embeddings are the way forward. They don't just provide a representation, they encapsulate meaning, relationships, and context. Looking ahead, it's crucial to continue exploring methods to improve our models while remaining vigilant about ethical considerations and bias. By doing so, we can ensure that our advancements in NLP contribute positively to society. The journey of embedding representations is just the beginning, and there's a vast expanse of knowledge yet to discover as we venture further into AI, language modeling, and beyond. Keep experimenting, keep learning, and let your curiosity guide you into the exciting realms of machine learning and natural language processing. Natural language processing, or NLP, is a fascinating field that truly interplays between linguistics and machine learning. Today, we will dive into advanced techniques for representing text, which is essential for enabling machine learning models to understand and compute language nuances effectively. So far, we covered various embedding representation methods in natural language processing, emphasizing traditional models like Word2Vec and GloV, as well as advanced models like BERT, and discussed the ethical implications related to model bias. Now, we will explore more advanced NLP techniques and their practical applications in the realm of machine learning and AI. Now let's see how we can implement a simple transformer model using the Hugging Faces Transformers library. We begin by installing the necessary libraries, transformers for NLP tasks and Torch for tensor computations. With those installed, we import the BERT tokenizer and BERT model, which are essential for working with the BERT architecture. Next, we load a pre-trained BERT tokenizer and model, which enables us to leverage the power of BERT without needing to train from scratch. The tokenizer processes our input text, "The cat sat on the mat," converting it into a format suitable for the model. We then prepare the input tensors that BERT requires. After formatting our text, we perform a forward pass through the model to obtain outputs. Importantly, we utilize a context-aware approach by suppressing gradient calculations during this stage with Torch no grad, which enhances efficiency. The output of this model is the last hidden state, which encapsulates the contextual representations of the input words. By inspecting this hidden state, we can glean valuable insights into how BERT understands word relationships and context, showcasing the self-attention mechanism's effectiveness. The figure titled Key NLP Concepts and Their Significance displays a bar chart with 5 categories on the x-axis: Word2Vec, GloV, BERT, Transformers, and Ethics in NLP, and their corresponding significance scores on the y-axis measured out of 100. The bars show that transformers have the highest significance value at 95, followed closely by BERT at 90. Traditional embedding methods like Word2Vec and GloV register lower significance values of 80 and 65 respectively, indicating that while they remain relevant, they are regarded as less central compared to contextual models. Ethics in NLP is shown with a significance of 70, positioned between Word2Vec and GloV, which highlights that ethical considerations are seen as an important, though not leading, dimension relative to model types. From these numeric relationships, we can draw several conclusions relevant to our lesson. Transformer-based architectures, transformers, and BERT dominate perceived significance, suggesting they should be prioritized when aiming for state-of-the-art performance. Classical embeddings still retain practical value, Word2Vec at 80, for certain resource-constrained or interpretability-focused tasks. And ethics at a solid 70 must be integrated into model development and evaluation decisions rather than treated as an afterthought. The explicit data labels on each bar, 95, 90, 80, 70, 65, make clear the relative gaps. For example, transformers are 5 points above BERT and 30 points above GloV, which helps in prioritizing efforts for research, deployment, and resource allocation in NLP projects. Next, we will implement the code required to fine-tune our BERT model for sentiment analysis using the Hugging Face libraries. To start, we load the sentiment analysis dataset from the GLUE benchmark, specifically the misses subset, which is essential for training our model on relevant data. After preparing the dataset, we proceed to load the pre-trained BERT model specifically tailored for sequence classification, which allows us to categorize our input text into defined sentiment labels. Now let's define the training arguments that will guide our fine-tuning process. Here, we set parameters like the output directory for model results, the evaluation strategy to validate the model's performance at the end of each epoch, the learning rate for optimizing model weights, the batch size for processing training samples, and the number of training epochs to complete the training cycle. With these configurations in place, the next step is to create a trainer instance that brings together the model, training arguments, and the training and validation datasets. Finally, we execute the training process using the trainer, where the model fine-tunes itself on the sentiment analysis dataset. This iterative training adapts the BERT model to better understand and classify sentiments based on the provided examples. Now let's see how we can adapt a pre-trained BERT model for a new task using transfer learning. In this example, we begin by loading the BERT model specifically designed for question answering. This will serve as our starting point, allowing us to leverage the learned representations and knowledge from the original task. Next, we modify the classification layer of the model to fit the requirements of our new application, in this case, sentiment analysis. Here, we replace the existing classifier layer with a new linear layer that outputs the desired number of classes, allowing the model to adjust its predictions according to the new task's needs. It is important to note that this code snippet represents a high-level overview of the steps involved. In a practical implementation, we would also need to address additional aspects such as data preparation, training configurations, and hyperparameter tuning. This approach not only saves time by utilizing existing models, but also provides a robust foundation for fine-tuning with task-specific datasets, enabling us to achieve strong performance on new NLP challenges efficiently. Now let's implement a named entity recognition (NER) pipeline using BERT. We start by importing the pipeline function from the Hugging Face Transformers library, which simplifies several NLP tasks, including NER. Next, we load the NER pipeline with a specific pre-trained BERT model that has been fine-tuned on the Co-NLL03 dataset, designed specifically for tasks like identifying proper nouns. Once our pipeline is set up, we proceed to process a sample sentence. I went to the bank to deposit money. By passing this sentence into the NER pipeline, we generate a list of recognized entities along with their corresponding labels. Finally, we loop through the results to display the extracted entities. For each entity, we print out the word along with its classification, such as identifying bank as either a financial institution or a location, depending on the context provided in the surrounding text. This practical exercise in using NER showcases how models like BERT enhance our ability to interpret and clarify ambiguous language effectively, ultimately leading to more robust natural language processing applications. Now let's see how we can evaluate our model's performance on a validation dataset. To do this, we will utilize the classification report from the scikit-learn library, which provides detailed metrics that quantify the model's effectiveness. First, we define two arrays. White-true represents the actual labels for our validation dataset, while wipe-red holds the model's predicted labels. These arrays are essential as they form the basis for assessing how accurately the model classifies instances. Next, we generate a classification report using the classification report function, which takes white-true and wipe-red as inputs. This function computes a variety of performance metrics including accuracy, precision, recall, and F1 score, each offering valuable insights into how well the model handles different classes. The output of the classification report will highlight strengths and weaknesses in the model's performance, shedding light on areas that may require further improvement. This evaluation step is critical, as it informs us on how well our model generalizes and helps guide future iterations and updates to our training datasets. By regularly assessing model performance, we enhance our ability to refine and optimize NLP solutions effectively. To wrap things up, understanding advanced NLP techniques is fundamental for constructing effective machine learning models. We explored various text representation strategies, the powerful transformer architecture, fine-tuning techniques, the concept of transfer learning, addressing contextual ambiguity, and robust evaluation methods. All of these collectively enhance our model's capabilities to comprehend human language in a nuanced way. So if you're eager to see how you can implement these advanced NLP techniques in real-world applications, start experimenting with datasets and play around with the code samples provided. Diving into the practical side of these concepts will solidify your understanding and allow you to contribute meaningfully to the exciting field of natural language processing. Thank you for joining me, and I'll see you in the next session. In this lesson, we're diving into techniques for applying word embeddings in sentiment analysis. By the end, you'll be well equipped to take a corpus of text and use deep learning to analyze sentiments effectively. So far, we've explored natural language processing (NLP) and its intersection with machine learning, discussing various text representation methods such as Word2Vec and GloV, and advanced models like BERT and transformers. We've touched upon model fine-tuning, transfer learning, handling contextual ambiguity, and the critical importance of evaluating model performance. Now we will cover how to leverage these concepts specifically in sentiment analysis using word embeddings, allowing us to gain insights into public opinion and customer feedback by detecting emotional tones in text. The figure titled Performance of Word Embedding Techniques in Sentiment Analysis presents a horizontal bar chart with 5 labeled entries and corresponding numeric performance scores. Word2Vec 75, GloV 85, BERT 90, Transformers 95, and Sentiment Analysis 80. Reading the chart from lowest to highest, Word2Vec records the lowest performance score at 75, followed by the bar labeled Sentiment Analysis at 80, then GloV at 85, BERT at 90, and Transformers achieving the highest score at 95. Key patterns are immediately apparent. Contextualized transformer-based approaches occupy the top positions, Transformers 95, BERT 90, while static embedding techniques fall lower, GloV 85, Word2Vec 75. The numeric gaps are informative. A 5-point advantage separates Transformers from BERT and BERT from GloV, while Word2Vec trails GloV by 10 points, indicating consistent incremental improvements as the methods become more context-aware. Each bar also displays its exact score at the bar end, allowing precise comparison. From these values, we can conclude that, for the task and metrics represented here, moving from static embeddings to contextualized transformer architectures yields measurable gains in sentiment analysis performance, with transformers showing the highest effectiveness among the listed techniques. Now let's see how we can implement the loading of GloV embeddings into our application. We start by importing the necessary NumPy library, which will help us handle the numerical data effectively. Next, we create an empty dictionary called Embeddings Index, where we will store the words as keys and their corresponding vector representations as values. To read the GloV embeddings, we use a context manager to open the GloV file, ensuring it will be properly closed after we're done. As we loop through each line of the file, we split the line into components. The first part is the word, and the rest represent its vector values, which we convert into a NumPy array of type float32. This allows for efficient numerical operations later on. Each word vector is then stored in the dictionary we've prepared. Finally, we print out a message indicating the total number of word vectors loaded into the embeddings index. This snippet lays the groundwork for converting words into numerical representations that our sentiment analysis model will utilize, effectively bridging the gap between text and machine learning inputs. Now let's see how we can implement text preprocessing for our sentiment analysis task. The function preprocessText takes a string input and first converts the text to lowercase to maintain uniformity. This step is crucial as it helps in treating words like movie and movie as the same term. Next, the function removes punctuation and special characters using a regular expression, ensuring that only alphabetical characters and spaces remain. This cleanup helps in reducing noise in our data, as punctuation can often be irrelevant for sentiment analysis. Following the cleanup, the text is tokenized into individual words using the Word2Tokenize function from the NLTK library. This step is significant since it breaks down the text into manageable units for analysis. The resulting list of tokens provides a structured representation of our text data, making it easier for subsequent processing steps. For instance, if we input the sample sentence, "Absolutely loved the movie." It was fantastic, the output would be a clean list of relevant tokens. Absolutely loved the movie. It was fantastic. These tokens are now ready to be converted into their corresponding embeddings, setting the stage for deeper analysis. Next, we will implement a function to create an embedding matrix for the tokens we obtained from our preprocessed text. This function, getEmbeddingMatrix, takes 3 parameters: the list of tokens, the embeddings index we loaded earlier, and the embedding dimension, which is set to 100 by default. Inside the function, we first initialize an embedding matrix filled with zeros, where each row corresponds to a token. Then we iterate over the tokens. For each token, if it exists in our embeddings index, we populate the corresponding row in the embedding matrix with its vector representation from the embeddings index. This way, we ensure that each word is converted into a numerical format that can be easily processed by our deep learning model. Finally, we demonstrate how to use this function with an example. By calling getEmbeddingMatrix and passing in our tokens and the embeddings index, we generate the embedding matrix necessary for analyzing sentiment effectively. This matrix will later serve as the input for our model, providing crucial information about the relationships and meanings of the words in the context of sentiment analysis. Next, we'll implement a deep learning model using Keras to analyze sentiments based on our pre-trained embeddings. First, we define a sequential model that starts with an embedding layer. This layer utilizes our embedding matrix, which holds the word vectors we've previously created, and it's set to be non-trainable to preserve the quality of our embeddings. Following this, we add an LSTM layer with 100 units, which is crucial for capturing the sequential relationships within text data. This layer will learn to identify patterns over time, making it effective for sentiment analysis. After the LSTM layer, we introduce a dense layer with a single neuron and a sigmoid activation function, allowing for binary classification of sentiments as either positive or negative. Finally, we compile the model using binary cross-entropy as the loss function and the atom optimizer, which is popular for its efficiency and performance in training deep learning models. This setup positions us well to analyze textual data through sentiment classification, and we can verify the model's architecture by calling the summary method to see its structure and parameters. Now that we have our embedding matrix ready, the next step is to train our LSTM model using example labels to classify sentiment. We'll begin by creating some dummy binary labels where the values represent positive and negative sentiments. In this case, we simply define an array with specific labels for our samples, where 1 indicates a positive sentiment and 0 indicates a negative one. Next, we will train the model using the fit method, which connections the embedding matrix to the specified labels, thereby teaching the model to associate embeddings with their corresponding sentiments. It's crucial to reshape the embedding matrix to fit the expected input shape of the LSTM model. We accomplish this by modifying its dimensions to ensure it aligns with the model's requirements. We'll also define the number of epochs and batch size during this training process. Selecting a suitable batch size and epoch count is essential, as they will impact the model's learning efficiency and overall performance. As the model trains through these epochs, it gets better at correlating each word's embedding with its respective sentiment, improving its classification accuracy progressively. Now that we have trained our model, it's crucial to evaluate its performance to understand how well it classifies sentiments. Next, we will write the following code to generate predictions from our trained model and compare these predictions against the actual sentiment labels. We start by importing the classification report function from the Sklern metrics module, which provides detailed metrics like precision, recall, and the F1 score. In the code, we assume we have a separate list of true labels representing the actual sentiments of our dataset. After obtaining predictions from the model, we employ a threshold to classify them into binary labels. If a prediction is greater than 0.5, it is classified as positive, otherwise it's negative. Finally, we call the classification report function, passing our true and predicted labels to evaluate the model's performance comprehensively. This evaluation will give us insights into the model's effectiveness and help identify areas for improvement, ensuring that we accurately gauge how well our model distinguishes between positive and negative sentiments. Now let's implement the following code to address issues of class imbalance during the training of our sentiment analysis model. First, we utilize the compute class weight function from the Sklern utils library, which helps to balance the class distribution by determining appropriate weights based on the occurrences of each class in our dataset. By passing in the true labels, the function computes the necessary weights that will be used to give more importance to minority classes. Next, we convert these class weights into a dictionary format that Keras expects, ensuring that our model can utilize these weights during training. This adjustment informs the loss function to prioritize learning from underrepresented classes, helping to correct any bias that might exist in our model due to imbalanced training data. Finally, we train the model using the fit method, adding the class weight parameter to apply our calculated weights. This step enables the model to focus more on the less frequent classes, ultimately improving its predictive capability and accuracy across all sentiments, especially those that are underrepresented in our training dataset. In summary, we've explored techniques for applying word embeddings in sentiment analysis, beginning with preprocessing techniques to clean and tokenize our text, loading and utilizing pre-trained embeddings, and building a deep learning model to analyze sentiments. With the advent of powerful tools and techniques in natural language processing and deep learning, we can effectively extract insights from textual data, enabling organizations to understand public opinions and customer sentiments more effectively than ever before. Moving forward, I encourage you to experiment with different datasets and try fine-tuning your models even further. With practice and creativity, the possibilities with sentiment analysis using word embeddings are almost limitless. Thank you for engaging in this lesson, and I look forward to our next adventure into the world of artificial intelligence and deep learning. Language is an incredible ability that allows us to express complex thoughts and communicate with one another. Today, we will delve into analyzing text data using deep learning techniques. We'll explore various ways to preprocess textual data, build models, and gain insights from our analysis. So far, we've learned about the importance of word embeddings in sentiment analysis, preprocessing text data, and building LSTM models to classify sentiments. Now we will discuss applying deep learning techniques to analyze text data in greater depth. One of the first steps in analyzing text data is to preprocess it. Text data can be messy, containing punctuation, numbers, and other non-essential elements that can hinder our models. The preprocessing pipeline generally involves tokenization, normalization, and removing stop words. Tokenization splits the text into words or tokens, while normalization refers to converting text to a standard format, lowercase for consistency, for example. Afterward, we aim to remove stop words, which are common words like the, and is that do not contribute much meaning to our analyses. The displayed horizontal bar chart titled Key Concepts in Text Data Analysis Using Deep Learning ranks core pipeline elements by a numeric importance level along the x-axis, with the y-axis listing the concepts: tokenization, normalization, stop words removal, word embeddings, pre-trained models, and LSTM models. Each bar is labeled with its exact value: tokenization at 20, normalization at 25, stop words removal at 15, word embeddings at 30, pre-trained models at 35, and LSTM models at 50. The clear pattern shows a progressive emphasis from basic preprocessing, steps toward representation learning, and model choice. Preprocessing steps, stop words removal, tokenization, normalization, occupy the lower importance range 15-25. Embeddings and pre-trained models sit in the mid-range 30-35, indicating substantial contribution to downstream performance, and LSTM models are rated highest 50, highlighting that model architecture and sequence modeling are considered the most influential factor in this analysis. From these values, we conclude that while solid preprocessing is necessary, investing effort in high-quality embeddings and sophisticated sequence models yields larger gains. Therefore, the practical takeaway is to ensure preprocessing is reliable, but prioritize representation learning and model design when allocating time and resources. Now let's implement the preprocessing of our product reviews dataset using Python's NLTK library. First, we import essential libraries, including pandas for data manipulation and NLTK for natural language processing tasks. After ensuring that the necessary NLTK resources are downloaded, we load our dataset containing product reviews. Next, we initialize a Porter stemmer to reduce words to their root forms and create a set of stop words in English to filter out common words that do not add meaningful context. We then define the preprocessText function. This function takes a review as input, converts it to lowercase, and tokenizes it into individual words. Following tokenization, we eliminate any punctuation and remove stop words. The remaining words are then stemmed to their base form, ensuring a uniform representation of the text. Finally, we apply this preprocessing function to the reviews column in the data frame, saving the cleaned reviews in a new column named cleaned reviews. This step is pivotal as it prepares our text data for further analysis, directly impacting the effectiveness of our models. Now that we have our preprocessed text data ready, let's see how we can implement GloveV embeddings into our analysis. First, we'll write a function called loadGloveEmbeddings, which takes the file path of the GloveV embeddings as input. This function reads the embeddings file line by line, extracting the word and its corresponding vector. Each word is stored as a key in a Python dictionary, with the associated vector as its value. This allows us to efficiently retrieve the vector representations of words when needed. We'll then call this function to load the GloveV embeddings from the specified file. Next, we need to transform our cleaned reviews into vector representations that our deep learning model can process. We accomplish this by defining the function text2vector, which accepts text and the embeddings dictionary as arguments. This function splits the text into words, checks if each word has a corresponding vector in our embeddings, and calculates the mean vector of all words present. By doing so, we create a cohesive vector representation for each review. We will then use the pandas apply method to apply this function across all cleaned reviews in our dataset, storing the resulting vectors in a new column. This transformation is crucial for converting our text data into a suitable format for the deep learning model. Now let's define and compile our LSTM model using Keras, which will enable us to analyze our preprocessed text data effectively. First, we import the necessary layers from the Keras library. We set up a sequential model, which is a linear stack of layers. The embedding layer converts our input text into dense vectors of fixed size, allowing the model to learn word relationships. We specify the input dimensions and embedding dimensions, ensuring that the input sequences are consistently padded to enable uniformity. Next, we add a spatial dropout 1D layer, which helps prevent overfitting by randomly dropping a fraction of the input during training. Following this, we introduce the LSTM layer, which consists of 100 units and includes dropout and recurrent dropout to mitigate overfitting further. This layer is crucial for understanding the context in sequences of text due to its ability to remember previous information. Finally, we append a dense layer with a sigmoid activation function to produce binary output, facilitating the prediction of sentiment classes. After defining the structure, we compile the model using binary cross-entropy as the loss function and atom as the optimizer, while also tracking accuracy during training. This setup prepares our model for training on the labeled textual data. Now let's implement the code to prepare our data for training the model. We start by using the padSequences function to ensure all vector representations of our text are of uniform length, which is essential for feeding them into the neural network. This step involves specifying the maximum length of input sequences. In this case, we set it to input length. Following this, we separate our dataset into two subsets, features and labels. The feature set X consists of the padded sequences, while the label set Y contains the corresponding target classes we seek to predict. Next, we'll split our dataset into training and testing sets using the train-test-split function from scikit-learn. By allocating 20% of the data for testing and maintaining a random state for reproducibility, we ensure that our model is evaluated accurately on unseen data. Finally, we proceed to train our model with the fit method, where we set the number of epochs to 5 and specify a batch size of 64. This approach allows us to monitor the model's performance through the validation data, providing insights into its learning effectiveness as it trains. Now that our model has been trained, it's essential to evaluate its performance to ensure it's effectively classifying the text data. Next, we will write the following code to generate predictions for the test set using a threshold of 0.5, converting the predicted probabilities into binary class predictions. This approach allows us to classify whether a given instance belongs to a positive or negative sentiment. After obtaining the predictions, we will implement the classification report, which prints various metrics such as precision, recall, and F1 score. These metrics provide insights into how well our model is performing across different classes, highlighting any potential misclassifications that may need attention. Additionally, we will take a look at the confusion matrix, a powerful tool for visualizing the number of correct versus incorrect predictions made by the model. This matrix will help us discern specific issues, such as whether certain sentiments are being consistently misclassified. By analyzing these metrics and the confusion matrix reports, we can identify strengths and weaknesses within the model's performance, guiding further improvements in future iterations. Now let's implement class weights to enhance our model's performance in the presence of class imbalance. First, we import the class weight module from the scikit-learn utils package, which provides utility functions for handling imbalanced datasets. We then compute class weights using the compute class weight function, which balances the classes by evaluating their distribution in the training data. This allows the model to assign higher weights to underrepresented classes, ensuring that these examples have a greater impact during training. Finally, when training the model, we include the computed class weights as an argument in the fit method. This modification instructs the model to pay more attention to the minority classes during training epochs. By implementing class weights, we aim to alleviate the potential bias that can occur when a model is more exposed to certain classes, ultimately striving for improved overall classification accuracy. This approach is crucial for situations where certain classes are significantly underrepresented, enabling the model to learn better and yield more robust predictions on all classes in the dataset. In conclusion, analyzing text data using deep learning techniques requires a comprehensive understanding of preprocessing steps, embedding methods, model architectures, and evaluation metrics. By mastering these concepts, you can gain valuable insights from textual data and improve your classification accuracy significantly. So far, we've walked through techniques for data preprocessing, how to utilize word embeddings, and how to build deep learning models like LSTM for sentiment analysis. We've also addressed issues of model performance and class imbalance by implementing various strategies. Now we're at the point where we can delve into experimenting with different datasets or hyperparameter tuning for our models to further enhance their performance. Continuous exploration and experimenting are key to mastering the art of text data analysis. Stay tuned for our next lessons, where we'll apply all these techniques to new datasets and refine our models even more for impressive results. To understand the concept of embedding application and representation, we need to explore how we can efficiently represent complex data in a way that retains context while being manageable in size. Essentially, we want to produce vectors that are small, composed of real dense numbers, and that encapsulate the contextual relationships inherent in the data. By doing so, we allow machine learning models, particularly in natural language processing, NLP, to perform better when interpreting and generating human language. So far, we learned about the significance of language in expressing thoughts and the initial steps of analyzing text data using deep learning techniques. We explored preprocessing methods like tokenization, normalization, and stop words removal, as well as the use of word embeddings to improve model performance. We also discussed building and training an LSTM model, along with evaluating its performance and addressing class imbalance through class weights. Next, we'll focus on experimenting with different datasets and hyperparameter tuning to enhance our models further. Now, natural language processing requires an understanding of how words relate to one another in both meaning and context. This is where embeddings come into play, transforming words or phrases into numerical vectors that a computer can understand. The key advantages of these embeddings are that they use significantly less memory than one-hot encoding, and they can capture semantic meanings. When we represent words as vectors, we aim for dense representations. Unlike sparse vectors, which can contain a lot of zeros, dense vectors allow the model to discern relationships among words. Imagine if each word were translated into a point in a multidimensional space where the distance between points reflects semantic similarity. The closer two words are in this space, the more similar their meanings. To create embeddings, we can use techniques like Word2Vec or GloV, global vectors for word representation. These algorithms analyze a large corpus of text and develop a map of word relationships. Let's dive into an example using Word2Vec. The displayed bar chart titled Effectiveness of AI Agents Across Different Autonomy Levels presents 4 discrete categories on the x-axis: Level 0, Tool; Level 1, Research Assistant; Level 2, Collaborator; and Level 3, Scientist, and measures effectiveness % on the y-axis. Value labels above each bar show explicit effectiveness percentages of 10% for Level 0, 30% for Level 1, 50% for Level 2, and 70% for Level 3. The chart reveals a clear monotonic increase in effectiveness as autonomy rises, with roughly equal 20 percentage point increments between consecutive levels: 10 right arrow, 30 right arrow, 50 right arrow, 70. Numerically, the highest autonomy level, Level 3, is 7 times more effective than the lowest, Level 0, in this visualization, and none of the bars reach the full 100% scale. The y-axis is shown up to 80%, so there is room above the highest value. The distinct colors for each bar make direct comparisons straightforward. From these displayed values and their pattern, one can conclude that in this hypothetical dataset, increased autonomy is associated with steadily higher measured effectiveness, indicating a consistent upward trend across the 4 levels. Now let's see how we can implement the Word2Vec model in Python using the Gensim library. First, we need to install Gensim if it isn't already in our environment, using pip for installation. After that, we proceed by importing the necessary modules, including the Word2Vec class and the NLTK library for tokenization, which enables us to break down sentences into individual words. Next, we define a sample corpus comprised of several sentences that relate to natural language processing. To prepare the data for the model, we tokenize these sentences, converting them to lowercase, which helps standardize the input. Now let's create the Word2Vec model by calling its constructor and passing the tokenized sentences along with hyperparameters like vector size, which defines the dimensionality of the word vectors, and window, which sets the maximum distance between the current and predicted word. After training, we can retrieve the vector for a specific word, in this case, language, which represents the word in a multidimensional space suitable for further analysis and applications in machine learning. This process effectively captures the contextual relationships among words, providing a powerful tool for subsequent tasks. Now let's see how we can implement sentiment analysis using the embeddings we generated. First, we begin by ensuring that we have the necessary libraries, pandas and scikit-learn, installed for data manipulation and machine learning tasks. We'll load the sentiment data from a CSV file into a data frame. It's essential to provide the correct file path to access the data. Next, we define the sentence-to-vector function that converts each sentence into its mean word embedding vector. This function tokenizes the input text and retrieves word vectors for each token from our previously trained Word2Vec model. If a token doesn't have a corresponding vector, it defaults to a vector of zeros. Following this, we apply this function across the data frame's text column to create a new column of embeddings. After creating our embeddings, we split our data into features, embeddings, and labels, sentiment labels, and then divide them into training and testing sets. We proceed by training a logistic regression classifier using the training data. Finally, we evaluate our model's performance on the unseen test data and generate a classification report to assess accuracy, precision, and recall, showcasing how effectively our model can predict sentiments based on the embeddings. Now let's implement the following code to conduct hyperparameter tuning for our Word2Vec model. We define a list of possible values for two critical hyperparameters: vector size, which determines the dimensionality of the word vectors, and window, which defines the maximum distance between the current word and the predicted word within the context of a sentence. As we iterate through each combination of these hyperparameters, we create a new Word2Vec model instance for each setting. After generating embeddings for our text data, we prepare our dataset by splitting the embeddings and labels into training and testing sets. We then train a classifier, fitting it to the training data. The model's performance is evaluated using accuracy, which we compute by predicting the labels of the test set. Each combination of hyperparameters, along with its accuracy, is stored in the results list for later analysis. Finally, we print out the vector sizes, window sizes, and their corresponding accuracies, allowing us to compare the effectiveness of different configurations and determine the optimal settings for our model. This systematic approach to tuning hyperparameters is essential for enhancing the performance of our embeddings and, consequently, our NLP tasks. In conclusion, embedding application and representation is an intricate yet fascinating domain that combines mathematical techniques with contextual language understanding. By transforming text into actionable numerical vectors, we've opened the doors to improved machine learning outcomes. Through Word2Vec and its application in sentiment analysis, we've seen firsthand how embeddings can enhance model performance and lend richer interpretations to data. As you proceed with your projects, remember that continually experimenting with different datasets and tuning your hyperparameters will lead to more robust models. Don't hesitate to geek out over the nuances of word relationships, as they hold the key to making sense of vast amounts of textual information. Keep pushing the boundaries, and happy learning. In this final section, we will do a project challenge to apply what we have learned so far. Your task is to create a multi-agent system using AI agents and large language models, LLMs, that can autonomously help users plan their travel by predicting optimal travel times, finding suitable hotels, and generating personalized itineraries. You will design 3 distinct agents: a weather agent to analyze historical weather data, a hotel agent to search for hotels based on user preferences, and an itinerary agent to craft a detailed travel plan. You'll build a user-friendly web interface using Streamlit, where users can input their travel preferences and receive real-time results from your agents. Make sure to implement asynchronous programming so that your agents can operate independently, and don't forget to containerize your application with Docker for smooth deployment. All relevant resources, including the project details and guidelines, can be found in the GitHub repository linked in the description. Embrace this challenge to showcase your skills and creativity.